So you want to learn Unity. Smart move. Unity is one of the most in-demand gaming engines in the world, powering everything from indie games to AAA titles across every major platform. And if you're watching this video, chances are you're ready to start making games and not just play them. Well, this crash course is the perfect place to start. In this free Unity crash course, Luis Ramirez is going to guide you through the fundamentals of Unity and game development using C#. You're going to learn how to navigate the Unity editor, build your own scene, move your player, and even get started on your own RPG game. Yes, you're going to get started on your own game today. Now, why Luis? Because he has over a decade of experience in the game dev world and knows exactly how to make Unity accessible for beginners. He has a rare ability to teach technical topics clearly while also making them fun and engaging. By the way, if you enjoy this crash course and want to go deeper, Luis also teaches the complete Zero to Mastery Unity Bootcamp, a career-focused course where you'll continue building your own RPG game and even publish it when you're done. It covers everything, from beginner fundamentals to advanced topics like animations, combat systems, quest dialogues, and even scene management. You can check that out by clicking the link in the description or in the top right hand corner. One more thing, if you enjoy this crash course, please help me show Luis some love by dropping this video a like and leaving a comment with your questions, thoughts, or feedback down below. Also, feel free to share this video with anyone that wants to break into game development. Alright, that's it from me. Let me hand it over to Luis. Enjoy!
Meet Bruno. He's your boss at one of the biggest companies in the world, Keiko Corp. A few weeks ago, he went missing. While on a company trip, his flight suddenly went missing. It was all over the news. After a few days of search and rescue, Bruno was found to be safe and sound. Isn't that great? The story doesn't end there. He's come to you for a specific reason. He starts telling you an unbelievable story of how he wound up on an island. On this island, he fought monsters, helped a stranger that wore a pumpkin on his head, and defeated an undead skeleton. It's the wackiest story you've ever heard in your life. After he finishes rambling with his story, he comes to you with a job. You're the game developer expert in the company. He wants to share his experience with the world by creating a game based on his adventure. You can probably see where this is going. Your job is to create a game with Bruno as the main character. You tell Bruno, "No problem, I can do that." There's just one problem. You don't know how to create a game. Seems like it's game over for you. Not to worry, I'm here. In this course, we will create an RPG game with Unity. If you don't have a single clue on how to use Unity, you've come to the right spots. We'll start with the basics of creating a project. Soon afterward, we'll familiarize ourselves with the tools at our disposal for managing a project. With the basics alone, we can design beautiful levels. You'll be creating an island in no time. All games need characters. That's what we tackle next. Our characters will be able to run around the map through player control or with AI. Don't know how to code? That's fine as well. We'll go through the basics of programming. As we progress, you'll be able to practically apply this knowledge to create an AI system. In the end, Bruno will be able to fight monsters without fearing for his life. What else does a game need? A quest system sounds cool. Let's add that to our game. Bruno also mentioned something about a stranger with a pumpkin on their head. What if we could talk with this strange creature? That'll be covered too. Dialogue is a critical component of any game. In the end, we're going to end the adventure with a single, final, climactic fight. Make no mistake, creating this game is going to take a lot of work and effort. But just like Bruno, I have the utmost confidence in you. Don't worry, I'm here to walk you through every step of the way. By the end, you're truly going to be the Unity expert that Bruno believes you to be. Once you're ready, let's start working on our game. I'll see you in the following lecture. In this lecture, let's take a moment to talk about Unity. Before taking this course, you probably did research on various game engines. I may be a bit biased, but I consider Unity to be a great game engine for all skill levels. Out of the box, a complete suite of tools is available for developing 2D and 3D games, thus boosting productivity and saving time. Overall, it provides a solid foundation for developing professional and indie games. Unity is primarily aimed at developers. However, that doesn't mean it's exclusive to programmers. Far from it. There's a reason why Unity is popular among small teams and enterprise clients. Collaboration is a big selling point. Whether you're a writer, 3D modeler, texture artist, sound designer, or composer, Unity makes it easy for users with different backgrounds to collaborate on a game. In the resource section of this lecture, I provide a link to the official site for Unity. Before moving on to the next lecture, you must register an account. Throughout this course, we're going to be using assets from the official store. They cannot be downloaded unless you have an account, so you'll need an account to complete this course. Don't worry, it's completely free. There is a premium version of Unity. Fortunately, it won't be necessary to pay for Unity. The free version will suffice. Once you've got an account set up, we can begin downloading Unity. In the next lecture, we'll perform that step together. I'll see you there. In this lecture, let's install Unity on our machines. I assume you created an account from the previous lecture. If not, create an account before proceeding. In a minute, we're going to need one. First things first, let's download the hub. On the official site for Unity, navigate to Resources, Developer Tools. This link will bring you to a page for downloading Unity onto your machine. Scrolling through the page, we're presented with two options. The first option allows us to download a specific version of Unity. If you've used Unity before, you may have noticed that the team releases new versions frequently. It's not uncommon to download newer versions of Unity on a regular basis. For this reason, the Unity Hub was introduced for managing different versions of Unity. Let's download it. After downloading the program, install it on your machine. I've already installed it. The installation process is straightforward. Keep clicking Next until you've reached the end. Go ahead and install the Unity Hub. Pause the video if you need to. Great. Now that you've installed the Unity Hub, let's explore the interface. It should look something like this. The first step to using the Hub is to connect our accounts. Connecting your account is very simple. Just follow the instructions provided by the site. I'm going to sign into my account. You should do the same. I'll see you in a moment. Awesome. The hub has been connected. We can start exploring other areas of the interface. On the left side, there are 4 tabs. The first tab is called Projects. This tab displays a complete list of projects on your machine. If this is your first time using Unity, you may have an empty list. That's to be expected. However, if you have existing projects, they may not appear on the list. Projects created before installing the hub must be registered. Unity does not automatically scan your system for existing projects. Projects can be registered by clicking on the button. From the File Explorer, you can search for your projects. For this course, we're not going to import an existing project. We will be starting completely from scratch. Let's move on to the next tab called Installs. As I mentioned before, the hub can help you manage different versions of Unity. On this tab, you will be presented with a complete list of versions installed on your machine. If you don't have Unity installed, let's install it together. At the top right corner, click on Install Editor. A window appears to ask us to select a version. Unity's versioning is based on the year. As of the recording of this lecture, the latest version is 2022. This version is labeled with LTS. LTS stands for long-term support. Not everyone has the luxury of upgrading a project to the latest version. Moving to different versions can cause headaches. The Unity team tries to make the process as painless as possible, but not every scenario can be covered. While you may not need the latest features to continue using Unity, bug fixes and security patches are critical for any game. For this reason, Unity continues to support older versions. Older versions will not receive access to newer features. However, they will receive patches for bugs or security flaws. Older versions are supported for up to 2 years after the official release. For this course, we're going to be installing the 2022 version. Please don't install any newer versions. Newer versions may cause issues with the course. You're better off using the same version as me. Click on Install. Up next, we can install a set of modules. You can think of modules as extensions for the Unity editor. You're not forced to download everything all at once. Unity's editor can be extended with features as you need them. Let's go through the options. Firstly, we have the option of installing Visual Studio Community. This program is a text editor for writing code. For this course, we're not going to need it. Instead, we will be using a different editor for writing code. It's completely optional to install Visual Studio Community. I already have it installed on my machine for other purposes. Unity was able to detect it on my machine. However, don't feel pressured to download it. We won't be using it. Afterward, we can select various platforms. Once you're finished developing a game, the next step is to build and publish it. Unity supports various platforms, from Android to popular consoles, such as PlayStation. The simplest platform is WebGL. Select this module from the list. WebGL is the platform for browser games. In the future, we're going to export our game to the browser. Other platforms will not be explored in this course. After selecting a platform, let's click Install. The installation process may take a while. While it's downloading, let's continue our exploration of the Unity Hub. In some cases, you may have forgotten to install a specific module, or you may want to add support for a specific platform. You don't have to reinstall Unity. To the left of each version, there's a cog icon. If you click on it, you will be presented with the option of installing additional modules. This option will bring back the window for installing modules. You never have to worry about missing a module. Back in the hub, there's another tab called Learn. Unity has invested in educational content to help beginners learn more about Unity. I consider this resource to be invaluable. A wealth of information is available for various genres, platforms, and professions. I highly recommend checking out the resources from this section regularly. Lastly, we have a tab called Community. Unity has a blog to help you keep up to date with the latest features. In addition, there's a forum for discussion and help. Most of these links are self-explanatory. Hopefully, at this point, Unity has been successfully downloaded. You can view the progress of the download by clicking on the button at the bottom left corner. After Unity has finished installing, it should appear within the list from the Installs tab. After Unity is finished downloading, we can start using it. Once you're ready, let's start creating a game. I'll see you in the next section. In this section, our goal will be to explore the fundamental features of Unity. Understanding the basic building blocks will help you navigate any project. To get started, we need to create a new project. That'll be the goal of this lecture. If you haven't already, open the Unity Hub. From the Hub, navigate to the Projects tab. New projects can be created from the Hub by clicking on the New Project button at the top right corner. Unity will ask us to configure the new project. Starting from the top, we must select the Unity version. By default, the latest version should be chosen. If not, manually select it. Next, we must select a template. There are templates for 2D games, 3D games, VR games, etc. There are dozens of templates at your disposal. For this course, we're focusing on 3D development. That whittles down our choices. Typically, the most commonly used templates are 3D, 3D HDRP, and 3D UDRP. Let's talk about the differences. First things first, we must understand the idea of a render pipeline. Rendering is the process of drawing graphics onto a screen. Behind the scenes, Unity performs various operations to render graphics. It has to calculate the perspective, lighting, geometry, and textures of a shape. This entire process is referred to as the render pipeline. Surprisingly, Unity gives us the option of modifying this pipeline. This customizability allows us to tailor the graphics to our game. We are given control over the render pipeline. There are 3 pipelines in Unity. They're called the built-in pipeline, universal render pipeline, and high-definition render pipeline. All pipelines have their pros and cons. During the early days of Unity, there was only one pipeline available called built-in render pipeline. It's a very powerful pipeline that is suitable for a lot of games. There was just one problem. It was deeply integrated into the engine. Customizing the pipeline was difficult. Now more than ever, games are becoming more demanding. The original pipeline was starting to show its limits. For these reasons, Unity introduced 2 new pipelines called the Universal Render Pipeline and High Definition Render Pipeline. Alternatively, they can be referred to as URP and HDRP, respectively. URP is the simplest pipeline out of the 2. It's exceptionally performant and robust. In addition, it has dozens of customization options. This pipeline is perfect for games with low to medium graphic requirements. I wouldn't underestimate this pipeline. You can do some amazing things with it. HDRP is the most powerful pipeline. This pipeline was designed for AAA title games. If your game requires the absolute best graphics possible, this is the pipeline to go with. Keep in mind, these pipelines are not plug-and-play. While HDRP provides the most options, it can be difficult to navigate the pipeline. In most cases, you will be fine with the built-in or universal pipeline. Be warned, there is a downside to using the newer pipelines. Community support is limited. It's not uncommon to download assets from the community. The assets are compatible with the older pipeline but not newer pipelines. You must do research before installing a new asset. In addition, the newer pipelines are not well documented. If you need help, you will have to be willing to experiment. To keep it simple, we'll go with the built-in render pipeline. This pipeline can be selected by choosing the 3D template. One final note, it's entirely possible to switch to a different pipeline. For example, let's say you want to switch to the universal pipeline from the built-in pipeline. That's completely possible. Vice versa, you can revert to a previous pipeline. As I said before, the built-in pipeline will be more than enough for our project. Our game is not going to rely heavily on graphics. The default settings will be fine. Next, let's give our project a name. The name of our game will be called Bruno's Island Adventure. Lastly, we must select a folder for storing our game. This step is very important. Games can easily contain hundreds of files. It's recommended to dedicate a directory to your games. Mixing your games with other directories can cause headaches. Please select a directory that you will feel comfortable working in. After setting the directory, let's create the project. This process may take a while. Be patient. Pat yourself on the back. We've successfully created a new Unity project. The overall process is straightforward. In upcoming lectures, we're going to explore the interface. In this lecture, let's explore the editor interface. Initially, the interface may be overwhelming. We'll take it one step at a time. The first thing to understand is that the interface is divided into windows. Windows are the sections of the editor. The name of each window can be found in the top left corner of the respective window. For example, on the left side of the editor, we have the hierarchy window. In the center of the editor, we have a window called Scene. To the right, the window is called Inspector. Lastly, at the bottom of the editor, we have a window called Project. In some cases, we may not like the layout of the editor. Windows can be freely moved around the editor. For example, we may want the hierarchy window to sit to the right of the scene window. We can click and drag the window's name to move it around. There are different ways to modify the layout. For example, we can drag the window between the scene and inspector windows. As we do so, the hierarchy window attempts to snap into the desired location. The mouse can be released to finalize the movement. This process is known as docking. If you have a background in Photoshop or Premiere Pro, you may be familiar with this behavior. What if we don't want to dock a window? It's completely possible to undock a window by dragging it around. If the editor can't find an appropriate location to snap the window hovers freely. As you can see, the window hovers freely over the other windows. There's one last solution to dock a window. We can group windows to create tabs. For example, at the bottom of the editor, the Project and Console windows occupy the same space. We can click on either window's name to switch between them. Creating a tab of windows is easy. Let's drag the hierarchy window over to the inspector window. If we position our mouse on the dark bar, Unity allows us to group the windows. Upon releasing my mouse, the windows become grouped. We can switch between them by clicking their names. Great, we've got a new layout. However, it's not permanent. We may want to save this layout for the future. At the top right corner, there's a drop-down for changing between various layouts. By default, Unity offers a set of popular layouts among Unity devs. We can add our layout to this list by clicking on Save Layouts. After doing so, we must give our layout a name. I'm going to call our layout Example. Next, let's save it. After doing so, the layout was registered with the editor. If we need to revert the layout, we can do so without reorganizing the layout manually. This feature saves us a lot of time. For this course, the default layout is more than suitable. Creating a new layout was just an example. Let's switch back to the default layout. These are not the only windows available in the editor. There are additional windows that can be found under the Window menu item. For example, let's try adding the Animation window. A new window appears called Animation. Similar to other windows, we can dock, undock, or merge the window with other windows. In a future lecture, we're going to talk about animations. At the moment, the animation window is not necessary. We can close the window by right-clicking on the name of the window and selecting Close Tab. Great! That was a basic introduction to the layout of the Unity editor. In the next lecture, let's dive deeper into specific windows. In this lecture, let's discuss each window from the default layout. Before getting started, let's make a few adjustments to the interface. From the Edit menu, select the Preferences option. First, let's change the editor theme color. Your color scheme may not match mine. There are two color schemes available. Under the General section, there's an option called Editor Theme. We can select a light theme or a dark theme. For this course, I'll be using the dark theme. However, feel free to use the light theme. It's not going to impact our game. There's another setting we'll modify. If you're like me, you may have difficulty viewing the overall interface. The icons and text are too small. Luckily, Unity has an option for scaling the interface for readability. Next, we can override the scaling of the interface by clicking on the UI scaling page. On this page, we can override the current scaling. By default, it should be set to 100%. I'm going to bump the scaling to 150%. Feel free to use whatever you prefer. After changing the scaling, Unity must be restarted. I'm going to quickly restart my program. Great, the interface has been scaled. Hopefully, it's easier to read the icons and text. Let's start reviewing the windows. We'll start with the Project window. The project window displays a list of files for your project. To the left, we have a list of saved searches. By default, Unity provides examples of files you can search through your project. We can search for materials, models, and prefabs. In the future, we'll become familiar with these types of files. Below the search presets, there's a list of folders. Every project is going to have two folders called Assets and Packages. The Assets folder contains a list of files created by us. A majority of your time will be spent in this folder. We have complete freedom over the structure of the files in this directory. For starters, we're given a directory called Scenes. If we look inside, there's a file called Sample Scene. Scenes are files that contain information about a specific level in your game. For example, if you're creating a platformer, you may have various levels, such as an underwater level and a sky level. These levels would be considered as two different scenes. Scenes are not limited to levels. If you're creating a large game, you may have cinematic scenes. It's entirely possible to create a scene dedicated to playing a cinematic. Alternatively, a scene can contain a starting menu for a game. Whatever is in your scene will be viewable by the player. Out of the box, Unity creates a sample scene for our game. It's recommended to store scene files in a separate directory. However, this is just a recommendation. We can move the scene file into a different directory without breaking our game. For example, I can drag this file into the Assets directory like so. After doing so, the file was moved. As I said before, we have complete freedom over the structure of our folders and files. As long as they're inside the Assets folder, we're good to go. Most developers prefer to keep their scenes in the Scenes folder. To be consistent with the community, let's move the sample scene file into the Scenes folder. The next folder is called Packages. Unity is a modular game engine. There are dozens of features available from the engine. Each feature comes in the form of a package. We have the option of adding or removing packages from our game. For example, there's a package for creating cinematics or testing your game. All packages are placed inside this directory. This directory should remain untouched. Unity completely maintains it. Throughout this course, we're going to be adding packages. You can safely ignore this directory for the time being. There's one last thing I want to mention about the project window. At the bottom right corner, there's a slider for adjusting the icons of the files. In some cases, Unity allows you to preview models from the project window. Enlarging icons can help identify files. I prefer to keep icons as small as possible. That does it for the project window. The next window is called Console. It sits next to the project window as a tab. This window displays a list of messages generated from our game. The purpose of this window is to help us debug our game or notify us of errors. Once we begin programming, this window becomes incredibly useful. Moving along, we have another window called Hierarchy. The Hierarchy window displays the active content in a specific scene. As I mentioned before, we can have multiple scenes from within a game. The name of the scene is written at the root of the hierarchy. In this case, we're viewing the sample scene. The sample scene contains two pieces of content called the camera and directional light. These objects will be explored in future lectures. Let's look at the next window called Scene. The Scene window displays the content in your game in 3D space. We can freely edit content by moving or rotating them. We are given a few tools for doing so. Next to the Scene window is the Game window. The Game window is another preview of our game. It's similar to the Scene window with one big difference. We cannot edit the content in our game. The tools become unavailable. The purpose of the Game window is to give us a preview of our game from the player's perspective. Whatever we see in this window is what the player will see. Therefore, the Scene window is for editing the game, whereas the Game window is for testing the final product of your game. There's one more window called Inspector. The Inspector window allows us to edit the details of a specific piece of content. By default, it may be empty. We must select a specific object or file to view its information. For example, From the hierarchy, we can select the camera or light source to view its information. The inspector window will toggle the controls for the selected content. We're not limited to viewing the controls from the hierarchy window. We can select files from the project window too. For example, let's move into the scenes directory. After doing so, select the sample scene. As you can see, the inspector window can display information for a specific file. Scenes don't contain many settings. Overall, the inspector window is a popular window to have in your editor. Throughout this course, we're going to be heavily using all these windows. There's a reason they're part of the default layouts. The community considers them to be the most useful. Hopefully, this gives you a general idea of the interface. In upcoming lectures, we're going to start adding and editing content. When you're ready, I'll see you in the following lecture. In this lecture, we're going to create a game object. Before doing so, the question is, what is a game object? Understanding the idea of a game object is absolutely crucial. It's a fundamental building block in Unity game development. So, what is a game object? A game object can be thought of as a container. This begs the question, a container for what? The answer is anything. Initially, game objects are completely empty. They don't represent anything in our game. By themselves, they're not helpful. Unity gives us the power to extend game objects with custom behavior. We can load a 3D model with a game object, or we can attach audio to a game object. UI elements can be handled with game objects too. Essentially, anything inside your game is represented by a game object. It is a fundamental unit in your game's scenes. Let's learn how to create a game object. In the Unity editor, right-click anywhere in the hierarchy window. We are given a list of options for creating various objects. To get started, we're going to create an empty object. Click the Create Empty option. After doing so, a new object has been added to the hierarchy. If we were to look at the scene, nothing would be visible. That's to be expected. As stated earlier, game objects are completely empty. They don't have a visual or audible representation. If we click on the game object, we can view the details from the inspector. From the inspector, we can change the name of the game object. Let's set the name to My First Game Object. If you press the Enter key, the name will be updated. If you're on a Mac, this would be the Return key. After updating the name, the hierarchy window has updated the name to reflect the changes. In some cases, we may want to disable the game object. Next to the input for the name, there's a checkbox. Toggling this checkbox disables or enables the game object. This feature can help remove distractions while editing another game object. In some cases, you may need to test a game object without another game object causing interference. To be truthful, the game object we've created is dull. Let's try creating a game object with a 3D model. First, we should delete our current game object. From the hierarchy, select the new game object we've created. Next, press the Delete key to remove it from the scene. Great! Now we can create a 3D object. Unity offers basic 3D editing features. It wasn't designed to completely design models. Typically, designers will use other programs for creating models. Some examples of software are Blender, 3ds Max, and ZBrush. Models created from these programs can be imported into a game. So, why does Unity offer 3D modeling capabilities? If you're on a team, your designer may not have a model ready. It takes time to design a proper model for a game. Valuable time can be wasted if you're waiting for a model. Rather than wait for a model, you can use Unity's 3D objects to act as a placeholder. It's completely possible to swap logic from one model to another. That's not to say that you can't create a fun game with Unity's basic 3D objects. Generally, a lot of developers treat them as placeholders. In the hierarchy, right-click to open a menu. From the menu, select 3D Object Cube. Voila! We've got a cube in our game. The cube should be viewable from the scene window. If not, you can hover your mouse over the scene window. Next, press the F key on your keyboard. This action causes the window to focus on the selected game object. If we were to look at the inspector, the name of the object has been set to cube. Make no mistake, this is still a game object. Unity renames it on your behalf. You may wonder, is the camera and light source also a game object? The answer is yes. All content displayed under the hierarchy is considered to be game objects. We can create various types of game objects by right-clicking on the hierarchy. As you can see, we can create audio game objects, image game objects, video game objects, etc. In the next lecture, let's start interacting with the game objects from the scene. In this lecture, let's explore the tools from the scene window to interact with the game objects. We have a cube in our scene, but we haven't learned how to move around it. There are various ways to move around the scene. The simplest way is to use the View tool. On the left side of the scene window, there's a list of buttons. The button with the hand icon is called the View tool. Upon selecting it, we'll be able to drag the camera around the scene. This tool can only move around the scene. It can't rotate. To rotate, we must drag and hold the right mouse button. The icon changes to an eye. If we release the button, Unity reverts to the original tool. You can use these tools to help you move around the object. Keep in mind, we're not moving the object. The camera for the scene window is being moved. The object is completely still. If you feel too close to the object, you can move the mouse wheel to zoom in and out. As I do so, the zoom speed is very smooth and consistent. But look what happens when I start zooming in on the object. As I zoom deeper, the pace starts slowing down. It's incredibly noticeable. Behind the scenes, Unity will slow the zoom speed as you get closer to the object. It's to prevent users from accidentally zooming past the game object. Initially, this behavior may not seem bad. However, you're more likely to have dozens of game objects. You may want to switch from object to object. Switching to another object can become annoying. To reset the zoom, select the new object and press the F key. Repeating this process can be cumbersome. Luckily, there's an alternative solution for moving around the scene. We can use the WASD keys. On the scene, press the right mouse button. Next, try pressing the WASD keys. The W key moves you forward. The S key moves you backward. The A key moves you to the left. Lastly, the D key moves you to the right. In addition, we can use the Q and E keys to move up and down. As we move the camera with the keyboard, the camera can be rotated by moving our mouse around the scene. Unlike before, the speed of the camera does not get slowed down. The downside of this behavior is accidentally zooming past an object. Whenever I accidentally zoom past an object, I press the F key to reset the camera to the object. There's one last option for moving the scene camera. At the top right corner, there's a tool called the Scene Gizmo. First, let's understand the idea of a gizmo. Gizmos are visual elements that provide additional information about a game object. Gizmos are exclusive to the Unity editor. If we were to play the game, the gizmo would not appear for the player. It's purely for editing purposes. In this example, the Scene Gizmo gives us the ability to alter the orientation of the scene. Below the gizmo, we can change the perspective. By default, the orientation mode is set to perspective. This mode will display game objects as if the camera had human eyes. Objects positioned farther away appear smaller than objects closer to the camera. If we click on this option, the mode will change to orthographic. This mode was created for designers. Oftentimes, it can be difficult to view objects from a far distance. The orthographic mode displays objects as flat 2D objects. This can help designers understand a scene better. For this course, we're not going to need this mode. Let's switch back to the perspective mode. Above this option, we have a weird 3D object. It's a box with cones sticking out of it. This gizmo allows us to rotate the camera on different axes. We can rotate on the X, Y, and Z axis. Make sure not to click on the box. Otherwise, you may alter the orientation. This gizmo can be helpful for quickly rotating the camera without dragging your mouse around the scene. In a nutshell, this is how we can move around the scene relatively easily. I highly recommend playing around with the scene's camera to become comfortable with the movement. Throughout the course, we'll be moving around the scene a lot. Becoming comfortable with moving around will be beneficial. In the next lecture, let's start manipulating game objects with the other tools. In this lecture, let's manipulate game objects in our scene. There are other tools available from the scene window. Below the View tool, we have another tool called Move. Let's select it. Next, we can select the cube to move it around. There are two options for selecting an object. The first option is to select the object from the hierarchy. By doing so, a gizmo appears at the center of the cube. Not all gizmos are exposed immediately. Some gizmos will appear after selecting a game object. Before exploring the gizmo, let's look at the second option of selecting an object. If I were to click in a random area, the gizmo would disappear because we've deselected the object. I can click on the cube to select it. This action causes the gizmo to reappear. Great! The Move tool gives us the power to move game objects. As you can see, we can move the objects in the 3D space by their X, Y, and Z axis. The green arrow represents the Y axis. The red arrow represents the X axis. Lastly, the blue arrow represents the Z axis. Clicking on any of the arrows causes the shape to move in their respective direction. We're not limited to moving a shape across a specific axis. We can move it on two axes at the same time. At the center of the gizmo, there are three boxes. The green box moves the object on the X and Z axis. The red box moves the object on the Y and Z axis. Lastly, the blue box moves the object on the X and Y axis. Let's move on to the next tool. Under the Move tool, we have the Rotation tool. As its name suggests, this tool can rotate a specific game object. Upon selecting this tool, three circles get wrapped around the game object. We can hold and drag the red circle to move the object on its X-axis. The blue circle moves the object on its Z-axis. Lastly, the green circle moves the object on its Y-axis. Moving along to the next tool, we have the Scale tool. The Scale tool can modify the size of an object. The gizmo is three lines with cubes attached to the ends of the lines. The green line resizes an object's Y scale. The red line resizes an object's X scale. Lastly, the blue line resizes an object's Z scale. In addition, we can resize all scales at once by clicking the center cube. This portion of the gizmo scales the object on all axes. The next tool is called the Rect tool. Unlike the other tools, this tool is designed for 2D objects. Unity can create 2D and 3D games. However, 3D games can contain 2D elements. For example, UI elements are created as 2D elements. It's completely possible to resize a 3D object with the Rect tool. However, the process can be confusing. In a future section, we will create UI elements for our game. The Rect tool will come in handy for this part of the course. For now, we can ignore it. Afterward, we have a tool called Transform. This tool combines the Move, Rotate, and Scale tools. Normally, I don't use this tool. While convenient, I prefer to tackle each aspect of a game object individually. However, this tool is at your disposal if you need it. There's one more tool called Edit Bounding Volume. This tool is not going to be useful in this course. We're not going to explore it since we don't need to edit the volume of our objects. There's one last thing I want to mention. We can switch tools with keyboard shortcuts. The Q key selects the View tool. The W key selects the Move tool. The E key selects the Rotation tool. The R key selects the Scale tool. The T key selects the Rect tool. Lastly, the Y key selects the Transform tool. Memorizing these keys will be useful. As I stated before, we're going to be moving around game objects a lot. Learning these shortcuts will make you a productive game developer. That's about it for the tools for manipulating game objects. They're very simple to use. Once again, I encourage you to play around with the tools. I think it's time for an exercise. In the next lecture, let's tackle an exercise to help you become familiar with these tools. In this lecture, I have an exercise for you. We're going to create a robot. Before I throw the exercise at you, I want to teach you one more thing. In game development, there's something called the forward vector. The forward vector refers to the direction an object is facing or moving. This concept is crucial to understand. You should always establish which direction an object is moving. If you're developing a game with characters, the characters will have faces. It would be awkward if characters were facing in the opposite direction they were moving. Therefore, you should always consider where the forward direction is. Let's click on the cube with the Select tool. We have multiple faces on the cube. Before creating a robot, we must determine where the robot is facing. It's common practice to use the direction of the blue arrow as the forward direction. In this case, this side of the cube would be the forward direction. Dozens of developers consider the direction of the blue arrow to always be the forward direction. We're going to adopt this practice. Let's quickly adjust the cube. First, let's rotate the cube so that the blue arrow points toward us. Next, if the cube is tilted, adjust the tilt to be flat. We don't want our robot to look tilted. Lastly, if the cube's forward direction is too small, scale the cube. Keep in mind, we're going to create a robot. The face of the robot should look nice and even. Great! It's time for the exercise. I want you to create the face of the robot. In the scene, add 3 more game objects. 2 game objects should be spheres. These objects will represent the eyes. The last game object can be a capsule. This object will be used for the mouth. These shapes can be found under the 3D menu option for creating objects. Move, scale, and rotate the objects onto the robot to create a face. It doesn't have to be perfect or accurate. The overall goal of this exercise is to practice with the tools for manipulating game objects. You may also need to rotate around the game object for accuracy. Pause the video and good luck. Welcome back. If you are able to create the robot, that's great. If not, that's fine too. Let's try creating a robot together. As mentioned, we should create a robot with a face. The face will have 2 eyes and a mouth. To create the eyes, we'll use a sphere. From the hierarchy, right-click to open the menu for creating objects. Under the 3D menu, select Sphere. Firstly, let's move the sphere close to us. It should be in front of the cube. At this point, the cube or sphere should not be touching. Next, let's select the sphere. After selecting it, switch over to the Scale tool. The gizmo should appear for the sphere. From the center, I'm going to resize the sphere to be smaller than the cube. Keep in mind, this shape will represent an eye. It should be a decent size for an eyeball. After resizing the sphere, let's move it into the cube. Before doing so, let's verify the forward direction of the cube. We don't want the eye to appear in the back of the head. Click on the cube with the Select tool. The eye should be positioned on the side with the blue arrow pointing to it. I'm going to start moving the sphere with the Move tool. In this example, the shapes are overlapping with one another. The sphere should sink into the cube. We don't want the entire sphere to stick out. Just to make sure, I'm going to move the scene camera around the cube. This step is to make sure I'm happy with the depth of the eye. Awesome, we can start working on the second eye. I'm going to adjust the scene's camera to face the robot again. For the next step, we're going to take a slightly different approach. The eyes should be the same size. To avoid guessing, we can duplicate game objects. Let me show you how. From the hierarchy, select the sphere. Next, press the Ctrl-D keys on your keyboard. If you're on a Mac, the keyboard shortcut would be Command-D. This shortcut produces a duplicate game object. If we look at the scene, nothing seems different. The reason is simple. The second sphere holds the same coordinates, scale, and rotation as the original sphere. They're overlapping with one another. From the hierarchy, I'm going to select the second sphere. Next, switch over to the Move tool. We're going to move the second eye to the opposite side of the first eye. Once again, you do not have to be accurate. Try your best to position the eye. The last step is to work on the mouth. For the mouth, let's use a capsule. On the hierarchy, right-click to open the menu. Next, under the 3D Object menu, select Capsule. After creating the capsule, move it closer to the camera with the Select tool. It should be in front of the robot. Afterward, resize the capsule to be an appropriate size for the mouth. You can resize a game object with the Scale tool. Once you're satisfied with the size, move and rotate the game object into the robot. The mouth will appear below the eyes of the robot. Feel free to make additional adjustments until you're happy with the face. Be sure to move around the game object. The mouth should be as even as possible. Great! Let's look at the robot from a distance to view the final results. More or less, you should have something similar to what I have. It doesn't have to be 100% the same as mine. Before concluding the lecture, let's rename the shapes to accurately describe the objects. The current names are not useful. For the cube, set the name to Robot. Next, select the first sphere. Set the name to I1. The second sphere will be called I2. Lastly, the capsule will be called Mouth. This step is not necessary. However, it's never a bad idea to be organized. I encourage you to add more features to the robot. For example, you can add antennas. Alternatively, you can change the shape of the eyes or mouth. Instead of spheres, you can use cubes. The sky is the limit. If you decide to adjust the bot, post a screenshot in the Q&A section or the official Discord server. I would love to see what you come up with. Once you're finished toying around, let's keep exploring Unity. I'll see you in the next lecture. In this lecture, let's shift our focus to the Inspector window. We've largely ignored it. The Inspector window contains basic information on the selected game object or file. If you were to select any of the game objects from our scene, you would be greeted with various settings. Each setting is grouped under a component. Components play a huge role in Unity game development. What's a component? Components are the building blocks of a game object. They can add special behavior to a game object. For example, they can play audio, apply gravity, add collision detection, etc. Each component should aim to apply one specific behavior to a game object. However, game objects may require multiple features to be fully functional. Rather than relying on one component to achieving the desired behavior, we can utilize multiple components to create the final product. This is known as component composition. Let me give you an analogy. You can think of a component as a Lego block. Lego blocks come in various shapes, sizes, and colors. By themselves, they're not impressive. When you put them together, you can create amazing models. You can build animals, buildings, characters, and almost anything you can imagine with Lego blocks. This idea of putting together a set of blocks to create an object is known as composition. This definition can be taken over to Unity. Component composition is the idea of putting together various components to build a game object. By themselves, game objects are nothing special. We must add components to get the desired appearance and behavior. The Unity team encourages developers to apply components to build their game objects. Components are viewable through the inspector window. From the hierarchy, select the robot game object. Next, look at the inspector. Components are split into panels. Each panel will contain the settings for the relative component. For readability, we can toggle the component's appearance by clicking on the arrow next to the name. For the robot game object, we have a total of 4 components. There are the transform, mesh filter, mesh renderer, and box collider components. To the right of each component, there's a question mark icon. We can click on this icon to view the documentation for a component. The documentation dives deeper into the component settings. I highly recommend checking out the documentation for an unfamiliar component. This resource is incredibly valuable for beginner developers. Let's head back to Unity. Components may have additional hidden settings. They can be viewed by clicking on the 3 dots. The program I'm using to record this video cuts off the menu. Luckily, the same menu can be accessed by right-clicking on the component's name. Various options are available, from moving the component to removing it. We're not going to select these options. It's good to know where to find them. Components can be disabled. If we were to disable the game object, all components would become disabled. But we may not want to disable the entire game object. Instead of disabling an object entirely, we can disable a specific component to prevent it from affecting a game object. For example, next to the name of the mesh renderer component, there's a checkbox. Unticking this box causes the component to stop working. This feature can be useful for debugging. If a game object is not behaving as expected, you can toggle each component to find the root cause of the problem. I'm going to re-enable this component. One last thing. New components can be added to a game object by clicking on the Add Component button. This button can be found at the bottom of the inspector window. Out of the box, Unity supplies us with dozens of components. Feel free to explore these components. Throughout this course, we're going to explore these components and their settings. That's about it for components. In the next lecture, let's start diving deeper into some of the components available to us. In this lecture, let's talk about the most essential component of any game object. Every game object has a component called transform. Regardless of the game object, you're guaranteed this component. Unlike other components, this component cannot be removed. Let's check out the robot game object. As we learned previously, we have 4 components. All components are removable except the transform component. For example, I'm going to right-click on the mesh renderer component. As I do so, the option for removing the component becomes available. This option is available on almost all components. Let's check out the options for the transform component by right-clicking on it. As you can see, we have fewer options than before. So why is the transform component considered necessary? The transform component allows developers to move, rotate, and scale the game object. It's a standard feature required by all game objects. We're not forced to manipulate game objects with the tools from the scene window. The transform component can help us further refine our adjustments. For example, let's try adjusting the X position of the game object. In the input, write a random number. Almost immediately, the robot from the scene moved away from the other objects. It's awkwardly positioned in the game. Pressing Ctrl-Z will undo the change. If you're on a Mac, this command would be Command-Z. An alternative method of updating the values is by hovering your mouse over the label. For example, let's try adjusting the X position again. This time, my mouse is hovered over the X label. The mouse icon's appearance will slightly change. Two arrows are pointing to the left and right. We can click and drag to update the X position. One benefit of using the slider is previewing the changes in real time. Over to our scene, the robot game object accurately reflects the changes. Once again, this will break our design, so I'll undo the changes. Great! The transform component is very powerful. We'll be using it to help us move objects around our world. In the next lecture, let's continue our discussion of Unity. In this lecture, let's start modifying the appearance of our game objects with materials. At the moment, our robot feels dull. A lack of color makes it boring. An object's surface can be changed with materials. I think our robot would look better with different colors. In the project window, navigate to the Assets directory. Next, right-click in the window, go to Create, and select Folder. The name of the folder will be called Examples. This step is optional. However, we're going to be using this project to create a full-fledged game. Keeping our project organized will help us find files easier. It's considered good practice to get into the habit of organizing your files. For this demonstration, we're going to store example files in the Examples directory. Let's move into this folder. Next, let's right-click to open the menu again. This time, under the Create menu, select Material. The name of our material will be called Robot. Some developers like to affix the word material to the file's name. The purpose of doing so is to make it easier to search for the file. If a file contains a keyword, it'll appear in the search results. I don't think this is necessary since Unity has a shortcut. To the left, under the Favorites section, there's a shortcut for finding all materials in a project. By clicking on this option, a complete list of materials will be presented in the window. I find it easier to use this feature instead of using a long name. However, feel free to use whatever naming convention you prefer. I'm going to go back to the Examples folder. Inside this folder, let's click on the new material. In the inspector, we can modify the material. There are dozens of settings available. For this lecture, we aren't going to explore them all. Materials can become very complicated. To keep it simple, let's focus on a single setting called Albedo. The albedo setting refers to the color of a shape. Before modifying the setting, let's open the preview. At the bottom of the inspector, the name of the material is displayed. Next to the name, there are two horizontal lines. Whenever you see two horizontal lines, this symbol indicates that a preview can be opened. Let's click and drag to open the preview. You don't have to make the preview this large. I'm enlarging it for the sake of clarity. By default, Unity will display a placeholder model to give you an idea of how color affects a shape. After opening the preview, let's click on the Albedo Settings color picker. Using the color picker is similar to using a color picker in any other program. We can drag the selection to change the color. As we do so, the preview gets updated. For this example, I'm going to pick the color blue. If you have a specific color in mind, you can use the RGBA or hex code inputs to be accurate. After picking a color, close the color picker. The next step is to apply this material to the robot. There are 3 solutions to applying materials to game objects. The first solution is to drag the material from the project window onto the game object in the scene. As you drag the material around the scene, Unity provides a preview of the effect. Be sure to drag it on the correct object. You can accidentally drag it on the wrong game object. Once you've found the object, release the mouse to apply the material. This is the first solution. I'm going to undo the material. The second solution is to drag the material over to the robot object in the hierarchy. Unlike before, a preview does not get shown in the scene. The material gets applied after you've released the mouse button. One more time, I'll undo the change to the object. There's one final option to modifying the material of an object. From the hierarchy, select the robot game object. Next, in the inspector, there are 2 components called Mesh Filter and Mesh Renderer. Both components are necessary for rendering any 3D model. Let's briefly dive into the world of 3D modeling. Models have something called a vertex. A vertex refers to a single point on a model. The plural word for a vertex is vertices. Look at this example. The white dots represent a vertex. When vertices connect, they create an edge. Lastly, a flat surface is created when multiple edges are connected. We call this a face. The combination of vertices, edges, and faces is called a mesh. Meshes provide information on how a 3D model is constructed. Without a mesh, Unity or any other program won't be able to render a model on the screen. Typically, 3D objects will always have 2 components. The first component is the mesh filter. The mesh filter component will load mesh data for a game object. It does not draw the mesh onto the scene. There's one option called mesh. On the input, there's a button we can click on. This button opens a list of meshes in our game. By default, we have access to Unity's meshes. Switching to different shapes is possible without having to recreate the object. For example, I can change the robot's shape to a sphere. You don't have to use a sphere. This was just an example. I'm going to revert the shape to a cube. The second component is called Mesh Renderer. As we discussed before, rendering is the process of drawing a shape onto the screen. Therefore, we can assume the Mesh Render component will draw a mesh onto the screen. So, you may wonder, why am I spending so much time talking about meshes? It turns out that materials can be updated through the Mesh Renderer component. Looking closely, we have a section called Materials. Under this section, a list of materials can be applied to a game object. Multiple materials can be added to a game object. However, the mesh must support multiple materials. You can't force an additional material unless you have access to the original model. In this case, Unity's 3D objects support one material. We can click on the button to bring up a complete list of materials. Let's select the robot material from the list. The material has been successfully applied to the game object. Hopefully, this information was helpful. In most cases, I prefer dragging the material onto the object. If a 3D object is complex, I apply materials through the Mesh Renderer component. In the next lecture, let's tackle an exercise. In this lecture, I have an exercise for you. In our scene, we have a robot without colors for the eyes and mouth. The exercise for this lecture is to apply materials to these objects. Feel free to choose whatever colors you want. There's no wrong answer. Pause the video and give it a try. Welcome back. If you were able to add materials to the robot, that's great. If not, that's fine as well. Let's try it together. To save time, we can duplicate existing materials. In the project window, select the robot material. Next, press Ctrl D or Command D. We'll create 2 additional materials. Next, let's rename the second material to Eyes. Lastly, rename the third material to Mouth. For the Eyes material, let's change the albedo setting to yellow. I'm going to go for a lime yellow. Next, drag the Eyes material onto both eyes. Great, let's work on the mouth. Select the Mouth material. For this material, let's change the color to red. Lastly, let's drag it onto the Mouth Game object. I think our robot came out great. It's not an award-winning design, but it's definitely passable. In the next lecture, let's start grouping our objects. In this lecture, we're going to group objects to move them together. During a previous lecture, we moved the robot around. By doing so, the robot's eyes and mouth were positioned incorrectly. They do not move with the entire robot. To fix this issue, we must move objects individually. As you can imagine, it's highly inefficient to move objects in this manner. What if we had hundreds of objects? Unity solves this issue by grouping game objects as parents and children. In the hierarchy, drag the Mouth Game object around the hierarchy. As we do so, there are 2 possible responses from the editor. We can position the object below or above existing objects. Unity will draw a line to highlight the new position. However, we can also nest the current object into another object. If we hover our mouse over an existing game object, the background color of the object becomes highlighted. I'm going to nest the Mouth Game object into the Robot Game object. After releasing my mouse, the Mouth Game object becomes the child of the Robot Game object. You can identify children objects by their indentation. As a mini exercise, try moving the eyes into the Robot Game object. I'll give you a moment to try this out. Pause the video and give it a try. Let's try tackling the exercise together. It's as simple as dragging them into the Robot Game object like so. There are no limits on how many children objects can exist in a parent object. There's one major benefit to grouping objects. I'm going to select the Robot Game object. Afterward, I'm going to move the object with the Move tool. As I do so, the other objects move too. By being children of the Robot Game object, they share a relationship with the parent object. Updates applied to the parent object will be reflected in the children objects. This does not just apply to the object's position. Rotation and scale are affected too. While this feature can be useful, it does add a layer of difficulty. I'm talking about global and local space. To make things clearer, let's reset the Robot Game object. In the Inspector window, right-click on the Transform component. There's an option called Reset. Click on it. By resetting the Transform component, the coordinates and rotation are set to 0. The scale will be set to 1. It's considered standard practice to reset an object whenever it's added to the scene. While not required, resetting an object can make it easier to work with. Dealing with random numbers can become confusing. Throughout this course, we're going to adopt this practice. I highly recommend you follow this practice. You can't begin to imagine the number of problems that can arise when the transform component's values are all over the place. If the object has moved away from you, press the F key to bring it back into focus. You may need to rotate the camera to view the face of the robot. So far, nothing seems off, but let me show you something interesting. I'm going to select the mouth game object. From the inspector window, let's set the X position to 1. The position of child objects is considered to be in local space. What this means is that the coordinates are relative to the parent game object, not the global world. Check this out. I'm going to select the robot game object. This time, I'll set the X position to 1 from the transform component. Like before, all objects move with the parent object. However, let's take a look at the transform component of the mouth object. The X position continues to be 1. The robot game object can have an X position of 100. Children objects will not reflect the same coordinates. The parent object will occupy space in the global space, whereas children objects occupy space relative to the parent object. The mouth game object's X position will always be 1 unit away from the parent's game object. To get the true position of a child's object, you must add the parent's game object position with the child object's position. In this case, the mouth has a global position of 2 because 1 plus 1 is 2. This concept can be tricky to understand. For this reason, it's considered good practice for parent objects to have their positions reset. This way, it's easier to understand the child object's position. I'm going to move the mouth object back to its original position. I know this can seem confusing. It's something you'll have to practice with until it clicks. I recommend experimenting with the robot game object before moving on to the following lecture. Try discovering what happens when you rotate the parent and child objects separately. You may be surprised by the values saved in the transform component. In this lecture, let's look at a feature in Unity to help us reuse game objects. By default, every game object is considered to be a unique copy. If we have 2 game objects that look the same, they are not considered the same from Unity's perspective. Changes applied to one object will not be reflected in the other. Let's look at an example. Our game may have an army of robots. In the hierarchy, I'm going to create a duplicate copy of the robot game object by pressing Ctrl D. If you're on a Mac, the keyboard shortcut would be Command D. Next, the game objects may overlap with one another. Try moving the second robot next to the first object. Awesome, we have 2 copies of our robots. Initially, they share similar appearances. However, if we modify one object, the other object will not be reflected with those changes. On the second robot, I may want to change the size. Let's increase the scale with the Scale tool. As the scale increases, the other robot remains the same size. They're independent of one another. In some cases, I may want the changes to be reflected in all copies of the robot. Otherwise, we would have to repeat the changes. We can resolve our issue with something called a prefab. Prefab is short for prefabrication. The purpose of a prefab is to store the original copy of a game object. By storing a copy, we can reuse this copy in our game. Best of all, changes are reflected in all copies when the prefab is updated. Creating prefabs is simple. Before creating a prefab, let's delete the second copy of the robot. You can delete a game object from a scene by selecting it from the hierarchy. Next, press the Delete key on your keyboard. We're left with a single robot. This robot should be converted into a prefab. Prefabs can be created by dragging the game object from the hierarchy to the project window. Let's create the prefab inside the examples folder. After dragging the object, a couple of things will be different. Firstly, the icon has changed. Normally, the icon for a game object is an outline of a box. This time, the box is a solid color. Prefabs have different icons than regular game objects to help developers identify them. Next, let's select the prefab from the hierarchy. In the Inspector window, new options become available. The editor informs us that we're working with a prefab. Next to the text, there are buttons for opening the prefab. Let's avoid those buttons for now. By creating a prefab, the original copy will be tracked by Unity. We can drag the prefab into the scene or hierarchy to create a new copy of the prefab. For example, let's drag the robot prefab into the scene. As we do so, Unity displays a preview of the object. Very clearly, it looks the same as the first robot. In my opinion, it's difficult to position the prefab by dragging it into the scene. Dragging the prefab into the hierarchy is easier. The new robot may overlap with the first robot. Let's move it over with the Move tool. Great! We've got two copies of a prefab. The question becomes, how do we modify the appearance? Prefabs have a dedicated editing mode. We can enter this mode by double-clicking on the prefab from the project window. The scene window completely changes. Unlike before, we can't view other objects from the original scene. Unity switches from regular editing mode to prefab editing mode. This feature allows us to focus on a prefab in isolation. Like before, let's try increasing the scale of the robot with the Scale tool. Next, we can exit prefab editing mode by clicking on the arrow button at the top left corner of the hierarchy window. Would you look at that? Both game objects have been rescaled. They're referencing the original object. As long as we modify the prefab directly, the copies will copy the same modifications. This update does not just apply to existing objects. New objects will have the same modifications. For example, let's drag another robot prefab into the hierarchy. Move the object with the Move tool. As you can see, they all look the same. There's another method to enter prefab editing mode. In the hierarchy, there's an arrow next to each prefab. If we click this button, we'll be taken to prefab editing mode. This time, things are slightly different. The game object is not isolated from the rest of the scene. Unlike before, the other objects become faded, thus giving us an idea of how our changes will be reflected in our game. Other than that, there isn't a difference between this mode and the other mode. Let's rotate the object. Next, exit prefab edit mode. Once again, the changes have been applied to all objects. In some cases, we may want to modify a specific prefab without affecting other copies. We can freely modify a copy without entering prefab mode. For example, let's select the first robot. Next, adjust the game object with the Scale tool to decrease its size. You'll notice I'm not entering prefab edit mode. This step is optional. As I adjust the scale, the other copies remain unaffected. As long as we're not entering prefab edit mode, the updates are applied to one copy. But let's say that I want this update to apply to all copies. Unity gives us the option of applying the changes to the original copy. In the inspector, there's a drop-down at the top of the window. It's called Overrides. If we were to select this drop-down, we'd be given a list of differences between this copy and the original copy. There are two options at our disposal. We can click on Revert to reverse the changes. This action will revert the current copy to the original copy. The other option is called Apply. By clicking this option, the original copy will have the same modifications as the current copy, thus causing the other copies to also update. Let's click on this option. After doing so, the other robots become smaller. Cool, right? Prefabs are very flexible. Best of all, the changes will be reflected in all scenes. If we had another scene with these robots, The changes would be visible from those copies too. Prefabs are very popular among the Unity community. We'll be using them throughout the course. In the next lecture, let's cover some final topics before moving on to our game. In this lecture, I've got some additional topics to cover. These topics don't need a lecture of their own. We can cover them in a single video. Let's get started. First, let's talk about playing the game. For most of this section, we've ignored the game window. We can play our game by pressing the play button at the top of the editor. After pressing this button, Unity will process the scene. This process may take a while. It'll depend on the size of your scene. Once finished, Unity switches from the Scene window to the Game window. Unlike before, the gizmos and tools are unavailable. While the game is playing, we should adjust the aspect ratio. Above the preview, there's a drop-down for changing the aspect ratio. By default, this option may be set to Free Aspect. This means that your game can adapt to any size. However, it's unlikely that your players may be using a random aspect ratio. They may prefer a specific ratio. For our game, we're going to support HD gameplay. Let's select this option from the drop-down. Keep in mind, the aspect ratio selected by this window will not affect the final output of the game. This is purely for editing purposes. The actual dimensions of the game must be configured elsewhere. In a future lecture, we'll cover game publishment. For now, this setting will suffice. Let's stop the game from playing. Next, let's talk about the camera. If you weren't able to see the robots from the game window, chances are the camera is not pointing at them. Switch over to the Scene window. Next, select the main camera object from the hierarchy. A gizmo will appear. This gizmo gives us an idea of what can be seen by the camera. You can move and rotate the camera to adjust the view. For this lecture, we're going to leave the camera alone. I recommend moving the robots into the camera's view as opposed to moving the camera. At the bottom right corner of the Scene window, a preview becomes available. This preview is helpful for helping us understand what is captured by the camera. We can save ourselves the effort of switching between the Scene and Game windows. My camera is viewing the robots, so I'll leave them alone. I have one more topic to cover. While the game is playing, you should be careful of editing your game. For example, let's play the game again. While the game is playing, I'm going to switch to the Scene window. It's completely acceptable to modify the game while it's playing. This allows us to experiment with different settings. For example, let's move the first robot vertically. Next, switch over to the Game window. As you can see, the robot's vertical position has been adjusted. However, this adjustment is temporary. I'm going to stop playing the game. Back in the Scene window, the robot has been positioned back to its original location. Modifications made during play mode are temporary. Oftentimes, developers will forget they're in play mode. It can be annoying to have your changes reversed. There is a trick to preventing this issue from happening. Let's go back into play mode. Next, from the main menu, navigate to Edit Preferences. Click on the Colors page. There's a setting called Play Mode. We can adjust the colors editor while it's in play mode. This visual information can remind us that we're in play mode, thus preventing us from updating our game while it's in this mode. I'm going to change the color. As I do, the entire editor changes color. The exception to this color is the Game window. Amongst the community, there isn't a standard color for the setting. You can use whatever color you prefer. Some developers prefer the color red to indicate danger. I'm going to use a yellowish color. After selecting a color, close the Preferences window. Next, exit play mode. The color goes away. The theme refers to its original color scheme. Perfect. We can go back into play mode for the color to appear. Admittedly, the color is obnoxious, but that's the point. It's a reminder that we should exit play mode before refining our game's settings. Otherwise, they may be lost. That wraps it up for this lecture. In this section, we've covered the fundamentals of Unity. This knowledge will help you get started with navigating around the editor. In the next set of sections, it's time to work on the master project. Before doing so, let's delete the robots from the hierarchy. We don't need them anymore. I'm going to leave the examples folder in our game. In future lectures, we may need to cover additional topics related to our robots. For now, you can safely ignore the folder. Once you've removed the robots from the scene, let's continue our journey with game development. In this lecture, we're going to import assets for the game we're developing. The main focus of this course will be programming. There's not enough time to discuss other areas of game development, such as modeling, music composition, or animation. To save time, I've prepared a set of assets for developing our game. None of the files I provided have code. All code will be written by us. The game assets will be downloaded from the resource section of this lecture. You'll find a zip file. Unzip the contents anywhere on your system. A single file can be found called Game Assets. Unity is capable of importing and exporting assets. Before importing this asset, let me show you the export process. At the top of the menu, navigate to Assets, Export Package. A window appears with a list of files that can be exported from our project. After selecting your files, you can click the Export button to produce a Unity package file. This is how I created the asset files for this project. Now that we have an overview of the export process, let's import the assets I provided for this project. Importing assets is as simple as dragging the file onto the Assets folder. After a few moments, Unity opens a window with a complete list of files in the bundle. As you can see, there are dozens of files. Don't worry, we'll get an opportunity to explore them. By default, all files should be selected. Just in case, you can press the All button to force Unity to select all files. After selecting the files, let's click Import. In a few seconds, a new folder will appear in our project called Game Assets. During the process, you may have received a warning. If we switch to the console window, the warning states there was an identifier violation. This warning can be safely ignored. As long as the files get imported, you're good to go. Let's go back to the project window. Taking a peek inside the new folder, you'll find various files, from audio files to 3D models. Feel free to explore the files. Throughout the course, we're going to reference the files from this directory. Most of these files can be found online. The game dev community is very giving. Finding free assets online is easy. If you're curious about where I got these assets, check out the credits.txt file. It'll contain links to various resources for finding free assets. In the next lecture, let's begin designing our first level. In this lecture, let's discuss the various 3D model file formats supported by Unity. The goal of this section is to design a level. Before we do, it's essential to understand the types of files we'll be working with. If you're working with an artist, you may be handed various file formats. It can be confusing to decide which format to use. Let's explore the various formats supported by Unity. By default, there are 4 official formats for models called FBX, OBJ, DAE, and DXF. These formats can render 3D models. Each format has its pros and cons. Let's go through them together. First up is the FBX file format. FBX is the most popular format in Unity game development. The reason is simple. It's reliable, supports animations, textures, and almost anything you need in a model. The official Unity team recommends this format. Whenever possible, Unity recommends this format over other formats. The downside to FBX files is their file size. They're very large compared to the other formats. The second file format is called OBJ. I consider this format to be a decent alternative to FBX files. They're also reliable, but produce a smaller file size. The only downside to this format is the lack of support for animations. This format is perfect for objects that don't need to be animated. You may prefer this format for specific models, such as generic objects. The third file format is called DAE. It's similar to FBX, except it's open source. The FBX file format is a proprietary format by a company called Autodesk. If you're not a fan of working with a proprietary format, you may consider using DAE files. It's completely open source. The last format is called DXF. This is a very old format. It was designed for sharing files between different programs. Collaboration is always important for teams. This format is commonly used with CAD applications. It's not a format we'll be using. This brings us to the question, which format will we be using? The answer is FBX. Unity strongly recommends this format. It's the most flexible option despite the large file size. Generally speaking, the trade-off is worth it. In the resource section of this lecture, I provide a link to Unity's documentation on supported model file formats. I recommend giving it a read. It'll provide additional information on supported and unsupported file formats. If you were to look through the imported assets from this course, most of the files are FBX. We shouldn't have a problem using these models in our game. In the next lecture, let's explore how Unity imports our models. In this lecture, let's explore another type of prefab called a model prefab. As we know, prefabs are files that store the original copy of a game object. During the import process, Unity converts FBX files into model prefabs. They share similarities to regular prefabs, but there are some differences. Let's explore those differences. In the project window, open the Examples folder. We have a single prefab called Robot. Clicking on the prefab reveals the various components of the game object. A copy of the prefab does not need to exist in the scene. Prefabs are easily customizable. On the other hand, model prefabs don't have the same flexibility. In the Game Assets folder, open the Characters folder. Inside this folder, we have a list of FBX files converted into model prefabs. Immediately, you'll notice a difference between prefabs and model prefabs. Model prefabs have slightly different icons. The icon is a blue box with a line through the top face. Let's click on any of the model prefabs. In the inspector, the model's settings become available. We can modify the model, rig, animation, and materials. In most cases, you can leave these settings alone. If you're curious, the components can be found under the model's settings. However, there's one huge difference. Components cannot be added, edited, or deleted. Unity does not allow us to modify a model prefab's components. In addition, Prefab Edit mode is not available for model prefabs. Unity imposes these limitations for updating models. If you're working with an artist, they may want to adjust a model after it has been created. Changing the material, adjusting the proportions, or adding new animations are examples of what can change in a model. If they change the model, it must be re-imported for the changes to be applied in your game. Re-importing assets can cause your original settings to be overridden. For this reason, Unity restricts us from directly modifying the model prefab. But what if we need to add components? For this situation, we must create a prefab out of the model prefab. Sounds like a roundabout solution, but this is the recommended solution for freely modifying the model. Let's give it a try. I'm going to drag the Orc-A model into the hierarchy. Be sure to drag it into the hierarchy. Otherwise, the coordinates for the game object may be awkward to work with. Going forward, you should always drag models into the hierarchy and not the scene. Next, I'm going to drag the game object into the project window. We've created something called a prefab variant. Prefab variants are prefabs created from other prefabs. In our case, the prefab we created was based on a prefab model. There are a few ways of identifying a prefab variant. Firstly, the icon is a blue box with hatched lines on the left side. It is not a solid blue box like prefabs. The second way of identifying prefab variants is by clicking on the prefab. Under the name, there's a read-only setting called Variant Parent. This setting lets us know which prefab the current prefab is based on. Hopefully, this helps you identify prefab variants. If we were to scroll through the inspector, we're able to view a list of components. This time, we can freely modify the components. However, we can't modify the model settings. If we want to modify the settings, we must modify the model prefab. These changes will be reflected in our new prefab. As I said before, it's a roundabout solution, but this is typically how we work with model prefabs. I'm not interested in having a prefab of the orc model. I'm going to delete it from the hierarchy and project windows. In the next lecture, let's install a package to help us design our levels. In this lecture, we're going to install a package to help us draw a map. Before installing the package, let's explore why it may be necessary. In our project, open the Game Assets/Terrain folder. This folder contains various models for the terrain of our game. Players will be able to walk on these objects. For this game, we're going to be using 3D tiles for constructing a map. There are enough tiles for there to be variety in your game. In this file, search for a tile called Ground Grass Tile. Before moving the tile onto the scene, let's verify its appearance. Under the inspector, open the preview. The model should look like this. After verifying that you've selected the correct model, let's drag it into the hierarchy. Next, let's focus on the model by pressing the F key. We're going to need more than one tile. The tile doesn't have enough room for the player to walk on. I'm going to duplicate the model. Next, I'll move it with the Move tool. Using the Move tool can be difficult since the precision may not be accurate. We may accidentally create a gap or overlap with the other object. I'm going to undo the movement. There's a trick to moving game objects. We can hold the Control or Command keys to use grid snapping. This time, the movement of the game object moves in bigger increments. This behavior will allow us to accurately move the tile on the edge of the other tile. This process can be repeated for newer tiles. For example, I'll duplicate and move the tile 2 more times. While this technique is viable, it's not the fastest approach to building a tile-based map. It can be easy to make mistakes. If your map is large, it can take hours to fully flesh out a map. Luckily, Unity has a package for helping us build a tile-based map. Before installing the package, let's delete the blocks from the hierarchy. Next, navigate to Window, Package Manager. Packages are features that can extend the current capabilities of the editor. There are various packages available, from cameras to analytics. At the top left corner, there's a drop-down for viewing different lists of packages. The first option is called Unity Registry. This option displays a list of official packages created by the Unity team. The second option is called In Project. This option displays a list of packages installed in our project. The My Assets option displays a list of packages downloaded from the Unity Asset Store. If you don't have an account, you will be unable to view these packages. Lastly, the Built-in option will display a list of core packages that have been pre-installed with the editor. let's select the Unity Registry option. As you can see, there are dozens of packages at our disposal. In the search bar, let's search for packages with the name Tile. Two packages should appear called 2D Tilemap Editor and 2D Tilemap Extras. The 2D Tilemap Editor package adds an editor for the tilemaps, while the Extras package extends the editor with additional features. Both packages will be necessary. Let's install both packages. As you can probably guess, both packages are aimed at 2D games. However, our game is 3D. Truthfully, these packages were not designed for 3D games. We won't be able to use them to their fullest extent, but that's perfectly fine. The features available for 3D games will suffice. The installation of both packages should have been successful. In the next lecture, let's begin using them. In this lecture, it's finally time to start drawing the map. Everything we need is ready. The goal of this lecture is to begin drawing 3D objects into the scene. The Tilemap packages we've installed can create a grid where objects can be drawn on. Let's give it a try. In the hierarchy, right-click to open the menu. Under 2D Object, select Tilemap Rectangular. This option will create a game object with a component called Grid. If we look closely at the grid, the orientation is incorrect. The grid is going up and down. You can verify the direction of the grid by comparing it with the Scene gizmo. As you can see, the y-axis represents up and down. Our grid is oriented against the y-axis. Our players will not be climbing the map. The terrain should be flat. The orientation can be adjusted by modifying the grid component. In the inspector, set the Cell Swizzle option to XZY. The grid has become flat. Let's rename the name of the game object to Terrain Grid. Perfect! We now have a flat surface for drawing the terrain. Let's adjust the scene's camera by clicking on the y-axis cone from the Scene gizmo. This adjustment will give us an aerial view of the grid. Before drawing on the grid, we should find the center of the grid. This step is completely optional. You can draw a map anywhere in the world. However, developers like to use the 0, 0, 0 coordinates as a reference point. These coordinates are considered to be the center of the world. Using them as a reference can make game development easier. While having the grid selected, let's look at the position. As you can see, the grid has coordinates 0, 0, 0. Let's switch to the Select tool from the scene. The great thing about the Select tool is that the gizmo is always centered on the game object. Since the grid is positioned at the center of the world, so will the Select tool's gizmo. Here's what I want you to do. Adjust the scene's camera directly above the center of the world. Great. When we start drawing the tiles should be within the proximity of the center of the grid. Once again, this step is optional. However, establishing the center of the world can make it easier to figure out where things are positioned in the world. Using the 0, 0, 0 coordinates is a common practice. The grid is ready, and our camera is positioned above the grid. Let's look at the hierarchy. Typically, we would have a single game object. However, the Tilemap package has created nested game objects. The grid game object acts as a container for tilemaps. Multiple tilemaps can be added to a grid. This feature can be useful for layering multiple objects over one another. By default, a single tilemap was generated, but we're allowed to add more. For this lecture, we're going to have a single tilemap. Select the Tilemap game object. Let's rename it to Beach Tilemap. The next step is to draw the tiles. Under the Window menu, select the 2D Tilemap Palette option. The Tilemap Palette window becomes available after installing the Tilemap packages. This package provides a complete suite of tools for drawing tiles. This window provides options for adjusting the brush that we can use to draw tiles on the map. Let's merge the window with the Inspector window. Game objects can be drawn on the grid by using a brush. First, we need to configure the brush to use our game objects. At the bottom of the Tilemap window, we can change the brush. The settings for the brush may be hidden. Let's drag these settings to the top of the window. There's a drop-down for changing the brush type. The default brush option is for 2D objects. However, our tiles are 3D game objects. We can switch the type to Game Object Brush. This option will allow us to use 3D game objects. Next, we can assign a game object to the brush. Before doing so, we should convert the prefab models into prefabs. The reason is simple. As we learned, prefab models do not support additional components. In a future lecture, we're going to need additional components. To save time, we should convert the prefab models into prefabs for component support. In the Assets directory, create a new folder. The name of the folder should be called Tiles. To keep our project organized, we're going to keep the models separate from the prefabs. This folder is not mandatory. I just like to keep my project neat and tidy. Next, let's go to the Game Assets/Terrain directory. Search for the ground grass tile. Drag this object into the hierarchy. Afterward, let's reset the transform component by right-clicking on the component from the inspector. Select Reset. Resetting the objects before doing anything else is considered good practice. Having random values can cause issues. Afterward, drag the object from the hierarchy to the Tiles folder. Lastly, we can delete the object from the hierarchy. Great! We've got a prefab. The name of the object is incorrectly named. This tile will be used for drawing the beach. Let's rename it to Beach Tile. Let's start drawing the tiles. Back in the Tile Palette window, open the Cells option. The Cells option represents the game objects that are stored in the brush. We only need one cell. Inside the Element 0 option, we can configure the game object settings for this cell. There's an option called Game Object. Let's use our game object by dragging it from the project window to the input for the Game Object option. Alternatively, you could have clicked on the button to the right. This button will open a window for selecting a game object from our game. However, it can be challenging to find the game object from the list of objects. I prefer to drag and drop. The next step is to enable the brush. At the top of the Tile Palette window, there's a button called Paint with Active Brush. Click on it to enable the brush. One more thing before you start drawing. Directly under these buttons, there's an option called Active Tilemap. The brush will add game objects to the scene. It needs to know where the game objects can be stored. Opening the drop-down reveals a list of possible locations. In our case, the game object should be stored under the Beach Tilemap game object. Make sure this game object is selected from the drop-down. Time to draw. Let's start clicking on the grid to add objects. For this game, the size of our grid will be 22 by 22. Make sure you're drawing around the center of the world. As long as you're close, you're good to go. I'm going to draw the outer layer. Next, I'm going to add 2 more inner layers. Perfect. You may be wondering, why are we drawing the outer layer of the map? It's to be efficient. The whole island won't be a beach. The inner island will have an elevated terrain with grass, trees, and flowers. The player will not be able to see this portion of the map. I don't think there's a point in drawing the entire beach. If that doesn't make sense, don't worry. In future lectures, we're going to continue working on the map. It'll become clear as we keep working on the map. Pat yourself on the back. We've successfully drawn the beach for our game. Just to make sure, use the scene's camera to move around the map. Make sure there aren't gaps or awkward positioning. As long as the objects are positioned tightly against one another, you can consider the map complete. In the next lecture, let's begin modifying the appearance of our beach with textures. In this lecture, we will modify the beach tilemap to look like a beach. At the moment, the beach's surface is green. The color of the beach is entirely off. Let's modify the colors with materials. First things first, let's enter Prefab edit mode for the beach tile prefab. By entering Prefab edit mode, we can apply changes to all copies. Modifying the original copy will assure us of this effect. Next, let's create a folder for storing materials. In the Assets directory, create a folder called Materials. Afterward, let's create a material by right-clicking on the project window. Under the Create menu, select Material. Next, let's set the color of the material. Click on the Albedo color picker. I have a specific color in mind. Set the hexadecimal value to the following color: E6A E74. Feel free to use a different color. There are dozens of online tools available to help you find colors. After selecting a color, let's drag the material onto the top side of the block. Unlike before, this model has a mesh that accepts multiple materials. We can apply material to the top or sides of the model. A complete list of accepted materials can be viewed by selecting the game object, opening the Mesh Render component, and selecting the Materials option. As you can see, 2 materials can be accepted by this game object. Let's head back to the scene to view the changes. Awesome! The map is starting to look like a beach. Hopefully, this example gives you an idea of how powerful prefabs can be. We did not have to adjust every game object. Modifying a single prefab has caused all similar game objects to adopt our material. In the next lecture, let's create a second layer of the terrain. In this lecture, we're going to work on adding a second layer to the terrain. Unlike the beach, the second layer will be elevated off the ground. Before drawing the elevated layer, let's prepare the game object. The tile for the ground will be similar to the beach tile. The difference will be the colors. The top side of the tile will have grass. We already have a tile with this material. In the Game Assets/Terrain folder, we have a model prefab called Ground Grass Tile. We can do the same thing we did before. Drag the model onto the hierarchy, drag it back into the Projects window, and delete the model from the hierarchy. These steps will produce a prefab. However, there's another solution I want to introduce. This information may come in handy. Sometimes, we may want the materials given to the model prefab. To the left of the model, there's an arrow icon. We can click on this icon to view a list of files embedded with the model prefab. Models are embedded with their respective data. In this case, the embedded files are the mesh and materials. Mesh files can be identified by their icon. The icon is a grid, whereas materials have 2 circles. Alternatively, you can view the inspector. The type of file is wrapped in parentheses. The materials for a model prefab can be extracted. From the Project window, select the Ground Grass Tile Model Prefab. Next, in the inspector, switch to the Materials tab. There's a button called Extract Materials. Clicking on this button will cause the materials to be extracted from the model prefab. Embedded materials cannot be modified. We must extract them to modify the material. Let's click on this button. Unity will proceed to ask us where to store the extracted materials. Let's select the Materials folder from the Assets directory. After extracting the materials will not be embedded anymore. Let's head on over to the Materials folder. Voila! The grass material has become available. By extracting the material, we can easily modify it. However, there is one downside to this route. If we delete the material, our models may become broken. The models are linked to the extracted materials. You should be careful with handling them. Let's try using these materials. Go to the Tiles folder. In this folder, duplicate the beach tile prefab. Next, rename the prefab to ground grass tile. Let's enter prefab edit mode for this prefab. The last step is to grab the grass material. Apply this material to the top side of the tile. You may have noticed, but the sides of the shape have turned pink. Unity uses pink to highlight that a model is missing a material. Whenever you see this color, you must always remember to apply a material. Let's add the dirt material to the sides of the model. Next, let's enter prefab edit mode for the beach tile prefab. We're going to apply the same material to the sides of the block. Fantastic! We've got two tiles with their own distinct colors, a tile for the beach and a tile for the ground. In the next lecture, let's paint this tile into the scene. In this lecture, we're going to paint the grass tiles with the tile package. Unlike before, the grass tiles will be elevated. They will sit 1 unit higher than beach tiles. To get started, let's prepare a new tile map. In the hierarchy, right-click on the Terrain Grid game object. Do not right-click in an empty area of the hierarchy. Otherwise, Unity will create a new grid. We're not interested in a new grid. A single grid can store multiple tile maps. After right-clicking, select 2D Object, Tilemap, Rectangular. The new name of the tile map will be called Ground 1 Tilemap. Creating a new tile map is optional. On the other hand, it's considered good practice to keep your project organized. For the new layer, we will separate the grass blocks from the beach blocks. If we were to look inside the beach tilemap object, there are dozens of beach game objects. If you plan on redesigning the map, it'll be easier to search for a specific game object. Next, let's begin preparing the brush. Switch over to the Tile Palette window. We may need to update the brush to the Game Object brush. Otherwise, we will not be able to paint with game objects. Next, search for the Green Grass Tile game object. Drag the prefab to the Game Object option. Next, let's adjust the Active Tile Map. Set the Active Tile Map option to Ground 1 Tile Map. If you were to select the wrong tile map, the game objects would be nested in the wrong parent game object. After selecting the correct tile map, let's turn on the brush. Finally, we can start painting. Make sure you're viewing the grid from an aerial view. It'll be easier to paint on the grid. I'm not going to paint the entire map. There's an issue with the current setup. To understand why, I'm going to paint the lower left corner with a few game objects. The objects are being drawn into the scene. However, their positions are incorrect. If we were to zoom in, the grass tiles are not elevated. They sit side by side with the beach tiles. The reason is simple. By default, the overall grid has a Y position of 0. Therefore, all child objects will have a 0 Y position. To elevate the tiles, we must update the Y position to 1. Why 1? The height of the tiles is 1 unit. Therefore, their Y position can be set to 1. There are two solutions for tackling this problem. The first solution is to update the tile settings. Under the Tile Palette window, there's a series of settings called Offset. The offset settings allow us to change the default coordinates of the brush. Let's set the Y offset to 1. The Y-axis controls how high an object is. After setting the offset, let's enable the brush again. Next, let's adjust the scene camera to view the map from an aerial view. Lastly, let's begin painting. After painting a few tiles, we can zoom in to check their position. This time, the game objects are elevated correctly. This solution works, but I have one problem with it. If we go back to the Tilemap palette window, I'll switch to the Beach Tilemap. Switching to a different tilemap does not reset the Y offset. I may accidentally forget to reset the Y tilemap. If I wanted to adjust a tilemap, I would have to check the Y offset before painting. Otherwise, my game objects would have incorrect positions. I'm going to remove the grass tiles by undoing my actions. Next, I'll set the Y offset setting to 0. In my opinion, a better solution is to update the transform data of the parent tilemap. In the hierarchy, select the Ground 1 tilemap game object. Next, switch to the Inspector window. Under the Transform component, set the Y position to 1. By setting the parent game object's position to 1, child objects will also have a Y position of 1. Directly modifying the parent is easier than adjusting the offset. If we switch tilemaps, we do not need to remember to reset the offset. The tilemap editor will automatically add the objects to the appropriate tilemap. Therefore, child objects will inherit the correct positions. Let's give this a try. Head back to the Tile Palette window. Next, turn on the brush. View the map in an aerial view. Lastly, start painting. As you can see, the grass tiles continue to be elevated. This time, we don't have to set the offset. That's not to say that using the offset is terrible. I like to use the offset for a few objects. However, if I'm painting an entire tile map, I prefer to set the tile map's position. Let's paint the entire inner area of the map like so. Great! Hopefully, you understand why I left a blank space in the middle of the island. There isn't a reason for beach tiles to exist in the center. The player won't be able to see them. They would get overshadowed by the grass tiles. Just to make sure, move around the scene to verify that every spot was covered. Alternatively, you can use the hierarchy to toggle the visibility of a game object. Next to each game object, there are two icons. You must hover your mouse over the hierarchy to view these icons. The eye icon will hide or show the game objects. I'm going to temporarily hide the Ground 1 tilemap game object. As I toggle the visibility of this game object, it becomes clear that we filled it in correctly. The hand icon will lock a game object. This option prevents us from accidentally clicking on a game object. While an object is locked, we cannot move it around the scene. That does it for this lecture. In the next lecture, let's begin drawing on the ground. In this lecture, I have a small exercise for you. We're going to paint grass on the grass tiles. The second tile map needs more life. Adding grass and flowers will help our game feel more alive. In the Game Assets folder, there's a folder called Nature. Open it. If you were to search through this folder, you'd come across various vegetation models. We're going to paint these game objects onto the tile. There are two options for performing this task. Firstly, we can drag and drop the game objects onto the scene. However, this approach can take a while. We can speed up the process by using the Polybrush package. This package is an official package by the Unity team. For this exercise, I want you to install this package. For your convenience, I'll write the name of the package on the video. Pause the video and install this package. Welcome back. If you are able to install the package, that's great. If not, that's fine as well. We'll install it together. From the top of the editor, navigate to Window, Package Manager. On the drop-down, select Unity Registry. Next, search for a package called Polybrush. Lastly, install it. After installation, the package will recommend a set of shaders for demonstrating the power of the Polybrush tool. This step is entirely optional. For this course, we're not going to install the samples. They're not necessary. Great, the package has been installed. In the next lecture, let's try using it to add flowers and grass to the tiles. In this lecture, let's start using the Polybrush package to paint game objects onto our tiles. There is one thing to know before getting started. Only one mesh can be painted on at a time. Therefore, we can't paint on multiple game objects at once. Luckily, the tiles are prefabs. We can paint on our prefab to apply the paint job to the other tiles. From the project window, search for the ground grass tile prefab. Next, enter prefab edit mode. I recommend adjusting the camera to look at the top of the tile. We're not going to be painting the sides. Next, let's open the Polybrush window. At the top of the editor, click on Tools. Under the Polybrush menu, there's an option called Polybrush Window. Click on it. Let's merge the window with the Inspector and Tile Palette windows. The Polybrush tool offers a variety of modes for painting models. There are a total of 5 modes. The first mode is called Sculpt mode. This mode can add or remove pieces from an existing mesh. You can use this mode to sculpt hills or holes. The next mode is called Smooth mode. If you decide to sculpt a game object, you may have jagged edges. The Smooth mode can smoothen the sharp corners and edges on your mesh. Afterward, we have the Paint Vertex Colors mode. This mode will paint a mesh with a specific color. This mode is an alternative solution to using materials. As we know, materials get applied to the entire surface. In some cases, models may support multiple materials. However, if a model doesn't support multiple materials, you can try using this brush. This brush allows you to paint specific areas in a model. Subsequently, we have the Placement mode. This mode will paint game objects on an existing game object. In a moment, we'll be using this mode to paint grass. The last mode is called Texture Paint mode. It's similar to the Color mode. However, you can paint textures instead of singular colors. This mode gives you the power to add more detail to a game object. Let's try using the Placement mode. You can activate a mode by clicking on it. The button will become highlighted to indicate it's active. You can disable a mode by clicking on the button again. There are quite a few settings available. Before getting into them, let's create the palette. At the bottom of the window, there's a box called Current Palette. In this box, we can add a list of game objects that can be drawn by the brush. In the project window, navigate to the Game Assets/Nature directory. Search for the Grass Model Prefab. Drag the model prefab from the project window to the palette. We're not creating a prefab from the model. The reason is simple. There aren't plans to extend the model with components. Not all objects have to be prefabs. It's perfectly fine to use it as is. The palette should display a preview of the object. If it's hard to view, you can adjust the size with the option above the preview. We can drag the preview size slider to enlarge the image. Let's add additional models. Above the grass object, there are 3 flowers, a red, purple, and yellow flower. Add these objects to the palette. Next, we must enable these objects on the brush. At the bottom right corner of the preview, there's a checkbox. Click the checkbox for the grass. We can toggle between different objects to place on the brush. Above the palette, there's another preview called Brush Loadout. This preview displays a list of game objects that will be drawn on the game object. Using this brush is similar to painting in real life. In the real world, you may have a palette with multiple colors, but you may not want to use all the colors within a single paint stroke. You're able to select what object should be added to the brush as you paint on a model. We're ready to start painting. If you hover your mouse over the tile, 2 circular outlines will appear on the screen. In some cases, you may not be able to see the brush. For the brush to appear, a game object from the hierarchy must be selected. Otherwise, you will not be allowed to start brushing. Just click on the game object from the hierarchy. After you've got the brush sorted, let's check out the gizmo for the brush. The brush is represented by 2 circles. Objects will be drawn between the circles. These circles can be adjusted through the brush's settings. In my opinion, the brush is too large. Under the Polybrush window, there are 2 settings called Outer Radius and Inner Radius. The outer radius setting affects the outer circle, whereas the inner radius setting affects the inner circle. Let's lower both settings. There's an alternative solution to adjusting the radius of both circles. Let's hover our mouse over either setting. Unity has tooltips for most of its settings. It can be a great way to learn more about a setting. According to the settings, we can adjust the radius by holding down the Control or Shift keys while scrolling with the mouse wheel. It may be easier to use this shortcut. You will be able to visualize the radius in real time. After adjusting the radius, let's paint on the tile's surface by clicking and dragging. The brush will randomize the position of the grass. During this process, you may not be happy with the results. Feel free to undo the changes by pressing Ctrl-Z or Command-Z. This part of the process is purely experimental. There are no right or wrong answers. Keep brushing on the surface until you're satisfied. Make sure you're not painting on the sides either. Great, I'm happy with this result. Let's add the flowers. We have the option of painting multiple objects at once. However, the brush will paint one object at a time. Adding too many objects to the brush can produce undesirable results. We want more grass than flowers. In the Polybrush window, uncheck the grass object. Next, add all flowers to the brush. Let's repeat the painting process. Once again, feel free to undo the placement of the flowers. You may need to repeatedly paint and undo until you're happy with the results. After finishing, let's exit Prefab Edit mode to view the final product. The second tile map should be covered in grass. That's awesome! We've successfully added more life to the map using the Polybrush tool. We could have dragged and dropped the vegetation onto the tile. This solution is just as effective. However, you may feel comfortable with letting the program randomize the locations. Either way, both options are at your disposal. Before moving on, let's close the Polybrush window. We're not going to need it anymore. Right-click on the name of the window. Next, select Close Tab. In the next lecture, let's continue working on our map. I'll see you there. In this lecture, let's take a moment to get into a discussion on game design. Designing a game can take just as long as programming one. There are numerous decisions to be made. We can tackle this subject from various angles. To get started, let's think about where the camera will be facing. The camera should follow the player. However, in which direction should it be facing the player? I think the camera should be looking at the forward direction of the blocks. If we were to select any of the blocks, they would have the same forward direction. As we discussed before, it's considered standard practice to use the blue arrow as the forward direction. Let's adjust the scene camera to look in the same direction as the blue arrow. During the development of our game, we should always consider where the camera is pointing. Otherwise, we may have inconsistencies during gameplay. Now that we've established the camera's direction, let's start thinking about the player's starting position. For this game, the player should start on the beach. After all, the game's premise is Bruno being stuck on an island. He'll likely start from the beach. We're going to position him in the lower right corner. It'll be a while until we add the model for the player. Therefore, let's create a temporary placeholder for the player. This step is optional, but can be helpful. If we know the player's starting position, we can design the game around that location. In the hierarchy, right-click on an empty area. Select Create Empty. Rename the object to Player Placeholder. Next, let's reset the Transform component by right-clicking on the Transform component. Select Reset. By using the Create Empty option, an empty game object will be created. It's the most basic game object that can be created. Moving the game object may be a challenge. Without visual information, it can be difficult to determine its location. One solution may be to use a 3D object. This solution works, but there is an alternative solution you may want to consider. We can use a custom icon. For example, let's select the Directional Light game object from the hierarchy. Next, press the F key to focus the sun. This game object is not viewable by the player. If the player looks at this object, they won't see anything. But what about the sun icon? Unity adds the sun icon to help developers find this object from the scene. It's purely for editing purposes. It's not uncommon to have game objects without visual information. At the same time, we may need to know the location of these objects from within our scene. Unity allows us to assign icons to a game object. Let's select the Player Placeholder object. Next, under the Inspector window, there's an option for the icon. By default, Unity supplies us with various icons for a game object. I'm going to use the blue diamond icon. Next, let's position the placeholder in the bottom right corner of the map. Hopefully, the icon will help you identify the location of the game object as you move it around. Don't worry about accuracy. In a future lecture, we'll delete this game object from the game. Its purpose is for our reference as we're designing the level. Let's add more placeholders. The game is going to have a cave, a treasure chest, and an NPC. I'm going to zoom away from the map. Afterward, let's view the map from an aerial view. The icon is small. However, this gives us an idea of the player's starting location. Based on this position, we can decide where to position the other locations. For this game, I'm going to position the cave in the top right corner. The treasure chest will be positioned in the top left corner. Lastly, the NPC will appear at the bottom left corner. As an exercise, I want you to create placeholders for each of these locations. Once again, the position of the placeholders doesn't have to be perfect. They will be deleted with real game objects. Pause the video and give it a try. Welcome back. If you were able to add the placeholders, that's great. If not, that's fine as well. Let's try adding them together. The first step is to create the game objects. To save time, let's duplicate the first placeholder. Select the player placeholder object. Next, duplicate this object 3 times. For the second copy of the object, rename the object to Cave Placeholder. Change the icon to a green diamond. Next, select the third copy. The object should be renamed to Treasure Chest Placeholder. The icon for this object will be updated to a yellow diamond. Lastly, select the last game object. Set the name to NPC Placeholder. Change the icon to an orange diamond. The placeholders are ready. As mentioned before, the cave to the dungeon will appear at the top right corner. The cave's entrance will be accessible from the second tile map. Let's move the placeholder to this location. Great! We can move the next placeholder. The treasure chest will appear at the top left corner of the map. Let's move the placeholder to this location. Lastly, the NPC will appear at the bottom left corner. Move the placeholder to this location. Upon zooming out and switching to an aerial view, we are given a better idea of the game. In this corner, we have the player's starting location. This corner will be the cave. The next corner will be the treasure chest location. Lastly, the bottom corner will be for the NPC's location. As we design the map, we can tailor the design to these locations. Hopefully, this information helps you lay out the game. Adding placeholders with custom icons can be a great way to reference specific locations while designing the map. In the next lecture, let's continue designing the map. In this lecture, let's draw the cave with a new tile map. This step is entirely optional. However, it'll give us an opportunity to practice drawing tile maps. Before getting started, let's explore the tiles available to us. In the Game Assets/Terrain directory, search for a model called Stone Grass Tile. For the third tile map, we're going to use this model. It should help the cave stand out. Here's an exercise for you. Create a third tile map. This tile map should position blocks above the second tile map. Therefore, the offset of the Y position should be 2. Before drawing the tiles onto the tile map, this block should be converted into a prefab. In addition, there's a tile called Stone Cave Tile. This tile should act as the cave entrance. I want you to add this tile to the third tile map. As for the location of the tiles, they should be positioned near the cave placeholder. I'm going to zoom the scene to this location. Add the tiles around this location. I wouldn't add too many tiles, just enough tiles for the cave's entrance. In future lectures, we're going to be adding more objects to the scene. You should leave room for other objects. Alright, pause the video and good luck. Welcome back. Hopefully, you were able to add the cave's entrance. If not, let's try adding the entrance together. First, let's create prefabs from the models. Drag the Stone Grass Tile model to the hierarchy. Reset the transform component. Do the same for the Stone Cave Tile. Next, drag both objects into the Tiles folder to create prefabs. Lastly, delete the models from the hierarchy. The tiles are ready. We can proceed to create the tile map. In the hierarchy, right-click on the Terrain Grid Game object. Don't click in another area. Otherwise, the tile map will be created in the wrong location. Let's select the 2D object Tilemap rectangular option. Next, let's rename the new tilemap to Ground 2 Tilemap. Lastly, the transform component should be updated. The tiles should be drawn above the first grounds. Therefore, the Y position should be set to 2. Almost done. The last step is to draw the tiles. Switch over to the Tile palette window. Set the active Tilemap option to Ground 2 Tilemap. Next, change the brush to Game Object. Afterward, drag the stone grass tile prefab into the Game Object input. Before drawing, the offset input should have values of 0. Otherwise, the offset will affect the position of the tile. After performing those steps, turn on the brush. I'm going to draw these tiles in the top right corner. The size of the tile map will be 2 by 4. On the bottom row, I'm leaving an empty space. This tile will be occupied by the cave tile. Let's try switching to the cave tile. Drag the cave prefab over to the Game Object input. Next, draw the cave entrance into the missing spot. Great, we're finished. Let's move around the scene to verify the tiles are positioned correctly. Everything came out great except for the cave. The entrance is not showing. The reason is simple. It's rotated incorrectly. We can fix this issue by manually rotating the object. Switch over to the Select tool. After switching to this tool, select the cave tile. Under the Inspector panel, let's adjust the transform data. Set the Y rotation to 180. That should fix our issue. Great! The cave entrance has been created. In a future lecture, this cave will be functional. Players will be able to walk into the cave to move on to the next level. I know I flew through the lecture. These steps shouldn't be new to you. If you were confused by what we did, check out the earlier lectures for a refresher on drawing tiles. Before ending this lecture, we can safely remove the cave placeholder. It's not necessary anymore. With the addition of the cave, the placeholder has become redundant. Delete it from the hierarchy. In the next lecture, let's keep working on the map. In this lecture, let's add a slope for the player to walk on. Currently, I'm viewing the map from an aerial view. This is what we have so far. At the moment, the player doesn't have a way to get from the beach to the first ground level. Therefore, they will not be able to reach the cave's entrance. To address this issue, let's add a slope. I'm going to zoom in near the player's location. The slope's location will be near the player. In fact, let's replace the third tile from the right on the bottom row of the second tile map. With the Select tool, select this tile. Next, delete it. For this problem, I've provided a model for creating a slope. In the project, navigate to the Game Assets/Terrain folder. Search for a game object called Ground Grass Slope Tile. Try tackling the solution as an exercise. We've performed this process multiple times. Before drawing this tile onto the tile map, convert it into a prefab. Pause the video and good luck. Welcome back. Let's try adding the slope. Most of the steps will be familiar to you by now. We're going to quickly go through the process. First, let's create a prefab. Grab the Ground Grass Slope tile. Drag the model to the hierarchy. Next, reset the transform component. Afterward, drag the object into the Tiles folder to convert it into a prefab. Delete the tile from the hierarchy. Next, switch to the Tile Palette window. Under the Cells section, drag the Ground, Grass, Slope Tile prefab into the Game Object field. We're almost finished. The next step is to set the active tile map. Change this option to Ground 1 Tile Map. The last step is to turn on the paintbrush and paint the tile in the empty tile slot. After painting the tile into the correct location, the rotation will be off. We can fix this issue by rotating the object on its y-axis. Select the object with the Select tool. Next, switch to the Inspector window. Set the Y rotation to 180. Awesome! The ramp has been created. Players will be able to walk up the ramp. If we look ahead from the ramp, the cave is aligned with it. If your cave isn't aligned with the ramp, that's perfectly fine. You may have positioned your tiles in different locations. That's not going to change the gameplay. In the next lecture, let's keep working on adding tiles. In this lecture, we're going to add more tiles. This time, we're going to automatically rotate them as we draw them on the tile map. So far, we've encountered two situations where the tile was rotated incorrectly. Rotating a single game object is not a problem, but what if you need to rotate multiple game objects at once? It would be convenient if the brush could rotate the objects as they're painted on the tile map. Turns out, that's completely possible. Before getting into it, let's find out what we're painting. From the ground tile, the edge of the tiles ends abruptly. The sides of the tiles are completely flat. It feels lazy. In the Game Assets/Terrain folder, I've provided tiles for the sides of the ground. The name of the model is called Ground Grass Edge Tile. Let's quickly convert this into a prefab. Drag it into the hierarchy, reset the transform, drag it back into the project window, and delete the copy from the hierarchy. These are steps we've repeated before. Next, let's update the tile palette. In the tile palette, add the game object to the brush. Next, set the active tile map to Ground 1. Awesome. Let's try painting the bottom side of the map. After drawing a few tiles, you'll notice a big problem. If we zoom in, the tiles are incorrectly rotated. By default, the edges are facing the opposite direction. We should rotate these objects before drawing the other side. However, updating each object would be annoying. Let's undo this action. Before drawing the tiles, we can adjust the orientation of our game objects. Under the Tile Palette window, there's a section for modifying the transform properties. We can change the offset, scale, and orientation. The orientation refers to the rotation of the object. Let's set the Y orientation to 180. By setting the rotation, all objects will be reflected with this orientation. Let's give it a try. Paint the tile onto the bottom half of the tile map. Taking a closer look, the tiles are correctly rotated. Awesome! We can start painting the other sides. In the orientation, set the Y rotation to 90. This rotation value will cause the tiles to look to the right. Let's paint the tiles on the right side of the tile map. Once more, let's update the Y rotation. This time, the value will be 270. Paint the tiles on the left side of the tile map. Lastly, change the Y rotation 0. Paint the top side of the tiles. To verify our work, let's move around the scene. Everything should have a tight fit. We've successfully rotated the tiles. In the next lecture, let's finish the design of our map by adding corners to the tile map. In this lecture, we're going to finish the design of our map. There's a lot we can add to the map. However, I don't want the course to get too repetitive. We will add one more tile before moving on to other topics. Currently, I'm viewing the corner of the second tile map. There is a weird gap appearing between the edges. I think it's awkward. I've provided a model for addressing this issue. In the Game Assets/Terrain folder, search for a model called Ground Grass Corner Tile. Similar to the previous lecture, the corner will be applied to different areas of the tile map. By default, the orientation of this tile will always be the same. We must rotate it for each corner. Try tackling this problem as an exercise. Paint the model in the corners of the tile map. Each time, you will need to rotate it. Pause the video and good luck. Welcome back. If you were able to tackle the exercise, that's great. If not, let's try tackling it together. First, we should change the model prefab into a regular prefab. Drag the model into the hierarchy, reset the transform, drag it into the Tiles folder, and delete the object from the hierarchy. Perfect, the tile is ready. Next, let's switch over to the Tile Palette window. Drag the Ground Grass Corner Tile prefab into the Game Object field. Change the active tile map to Ground 1. Lastly, turn on the brush. If you haven't already, update the scene to look at our map from an aerial view. We're going to paint the top right corner of the tile map. Paint a single tile into the corner. The tile should be perfectly positioned in the corner. Next, let's work on the bottom right corner. In the Tile Palette window, set the Y orientation to 90. Move the camera to the bottom right corner. After doing so, paint the tile. Let's do the same for the bottom left corner. This time, the orientation should be 180. Paint the tile into the corner. One more tile to go. For the top left corner, set the orientation to 270. Lastly, paint it into place. We're finished. As always, move around the scene to verify the placement of the tiles. This concludes this section of the course. In an hour, we were able to design a cool map. We could improve the design by adding more details. However, I'm happy with this result. In a future section, we'll get an opportunity to refine the map. Before ending this lecture, let's reset the orientation of the brush. In the Tile Palette window, set the Y orientation to 0. I think it's time to start programming. When you're ready, I'll see you in the next lecture. In this lecture, let's talk about game assets. Generally, you have two options for finding game assets. You can hire an artist to create them, or you can find free assets online. For this course, all assets can be found online. Let me show you where I found the assets for this project. Check out the resource section of this lecture for links to each site. For the tiles, we're using the Nature Kit from Kenny. Kenny is a popular resource for free game assets. You can browse the site for additional assets. The assets I've provided are a slimmed down version of the original package. I didn't want the package to be too large. If you're interested in the whole package, you can download it from here. Before using a free asset, you should always check the license. Some assets have requirements for using them. For example, all assets from Kenny are licensed under CC0. You can check out the resource section of this lecture for a link to this license. This license is popular among free game assets. Assets with this license are considered to be public domain. We're allowed to copy, modify, or distribute an asset without permission. We can even incorporate an asset into a commercial game. Therefore, it's safe to use these assets in our game. In addition to this asset pack, we're using another asset pack by a creator called K. Lewisburg. K offers character models, which we're using in our game. Similar to before, these assets are licensed under the CC0 license. I've included these characters with the package for our game. Same as before, I'm not including everything, only what we're using. You can check out this creators page for additional characters. Even though these assets are completely free, I encourage you to donate. They are constantly uploading new assets. Without their work, it would be harder to create a game. Alright, in the next lecture, let's get into programming. In this section, we're going to learn about C#. Before getting into Unity, understanding the basics of C# will put us in a good position to create games. It's vital that we're all on the same page. First things first, let's talk about the idea of a programming language. We need a way to communicate with our machines. This is where a programming language comes into play. A programming language will allow us to give instructions to our machines. We can instruct our machine to send an email, watch a video, or make a character jump on the screen. There are various languages available. It can be difficult to decide which language to use. Choosing a language will depend on what you're trying to accomplish. Some languages specialize in specific areas. Other languages are versatile. C# is an example of a general-purpose language. Mobile and desktop applications can be developed with C#. Creating servers is another popular reason to use C#. It's one of the most popular languages around. It ranks 5th in popularity due to its versatility. Another plus is that it's developed and designed by Microsoft. They're constantly updating and supporting C#. But why should we choose C#? Our choices are limited. In fact, it's our only choice. In the past, 3 languages were supported by Unity. However, the development team for Unity has decided to focus their efforts on C#. Most resources assume we're using C#. If we want to learn Unity, we need to learn C#. That isn't to say there aren't benefits to learning C#. By learning C#, you can explore other options. If game development isn't your cup of tea, you'll be able to transfer to a different sector in the tech industry. Lastly, C# is easy for beginners. There are hundreds of resources available, including documentation. If you don't have any experience with programming, that's perfectly fine. I've designed this course with the beginner in mind. Everything will be explained as we progress through this course. So, where do we start? We'll start by learning the syntax and fundamentals. In the real world, languages have rules on how they're written and spoken. Similarly, programming languages also have rules on how they're written. The technical term for the rules of a language is called syntax. Communicating with the machine requires learning the rules of the syntax. For most of this section, we're going to step away from Unity. After becoming comfortable with the fundamental concepts of C#, we'll get back into Unity for game development. Otherwise, learning as we go may be difficult. If you're ready, I'll see you in the next lecture. In this lecture, let's install a text editor for writing code. Writing code can be performed with any text editor. We can use Notepad or even a Google document. However, there are editors dedicated to writing code. These types of editors have features for debugging and helping us write code. In most cases, you should download a text editor specializing in writing code. In regards to Unity game development, there are 3 popular choices. The most common choice is Visual Studio. In the resource section of this lecture, I provide links to the editors mentioned in this lecture. During installation, the Unity Hub recommended this editor to us. Visual Studio is an editor for writing applications with C#. Not only does Microsoft manage the C# programming language, but they also have an editor for writing it. There's another editor called Visual Studio Code. It shares a similar name to Visual Studio. On top of that, this editor was created by Microsoft. Sounds confusing, right? Two editors created by the same company with similar names. What's the difference? Visual Studio was launched over 2 decades ago. It's Microsoft's oldest editor for writing code. Over the years, it has established itself as an editor for writing C# code. As the years went by, the web grew exponentially. Unlike desktop applications, websites were written with different programming languages. Rather than extending Visual Studio, Microsoft introduced a new code editor with support for creating websites. Originally, Visual Studio Code was a product aimed at web development. However, developers realized 2 things. Firstly, Visual Studio Code is easier to extend with custom extensions. Secondly, the development experience is more pleasant than Visual Studio. Every day, developers are switching from Visual Studio to Visual Studio Code. For this reason, we're going to use Visual Studio Code. It's beginner-friendly and ships with minimal features. Let's download and install it. I've already installed Visual Studio Code on my machine. This installation process is straightforward. Keep clicking Next until you've reached the end. While Visual Studio Code is downloading, let me mention another popular editor called Writer. Writer is a code editor developed by an independent private company. Unlike other editors, this editor costs money. It's up to you to decide whether it's worth the price. I've met a handful of Unity game developers who use Writer. After installing Visual Studio Code, another program must be downloaded. As mentioned before, Visual Studio Code was intended for web development. Out of the box, support for other programming languages is not available. In the resource section of this lecture, I provide a link to download the .NET platform. Our code must be transformed into machine code. Machines are not able to understand code until it has been transformed. The .NET platform is a tool for transforming C# code into machine-readable code. From the page, download the SDK. Do not install the runtime version. Be sure to install the SDK relevant to your operating system. Once again, I've installed this program on my machine. I will not be going through the installation. The process for installing this program is similar to installing Visual Studio Code. Keep clicking Next until reaching the end. We're almost finished. The next step is to force Unity to open Visual Studio Code. Open the project we've been working on. Under the Edit menu, click on the Preferences submenu item. Click on the External Tools section. There's a setting called External Script Editor. This setting will instruct Unity to open Visual Studio Code when writing code. Change this setting to Visual Studio Code. It's possible that this option may not be available. If it isn't, you should restart the Unity editor. Alternatively, you can click on the Browse option to search for the program. After setting the editor, Unity is ready to work with Visual Studio Code. The last step is to configure the code editor. In the next lecture, let's handle this step. In this lecture, let's configure Visual Studio Code for the best development experience. To get started, open Visual Studio Code. This is what it should look like. By default, it's going to open a random directory. We should point the editor to our project. At the top of the menu, navigate to File, Open Folder. I want you to point the editor to the project. I'm going to quickly do so. On the left side, we are presented with a list of files and folders available in our project. There are more folders than previously shown by the Unity editor. Let's quickly go over these directories. The first directory is called VS Code. This directory contains settings for Visual Studio Code. Unity creates this folder to hide prefabs, scenes, and other various files. This feature prevents programmers from accidentally breaking a file not meant for them. Our focus should solely be on writing code. The next directory is the Assets directory. We're already familiar with this directory. It contains the custom files for our project. If you were to look through it, you would be unable to find the models or prefabs from the project. As mentioned before, they're hidden from us, which is perfectly fine. The third directory is called logs. This directory contains a list of messages generated by Unity during development. We can view the files from this directory to check for errors or warnings. Afterward, we have a directory called packages. This directory contains a list of packages installed in our project. We can safely ignore it. The last directory is called user settings. This directory contains the settings for the Unity editor. Overall, we can ignore most of the directories. Throughout the course, we're going to be working from within the Assets directory. Everything else is managed by Unity. Let's start configuring Visual Studio Code. To the left of the editor, there are 5 buttons. Click on the Extensions button. It should be the last button. Visual Studio Code is extensible. We can install extensions to enhance the behavior of the editor. I have a few extensions installed because I use Visual Studio Code for professional work. You do not need to install these extensions. Most of them are for web development. In the search bar, search for an extension called C#. Microsoft develops the C# extension. It adds support for the C# language in the editor. Let's install and activate this extension. Next, search for an extension called Unity Code Snippets. Code snippets are a feature for quickly writing code. You can think of it as autocomplete for programming. Rather than typing a long line of code, Visual Studio Code can help us finish the line by offering recommendations. This extension extends the list of recommendations by adding Unity-specific code. It'll help boost productivity. Let's install it. We're finished. I know there was a lot to go through. Taking the time to configure our environment will provide the best development experience. In the next lecture, let's start writing code. In this lecture, let's create a C# file with Unity. This process is pretty straightforward. In the project window, navigate to the examples folder. To keep our project organized, we'll be working from within this directory. Right-click in the window. Under the Create menu, select C# script. By default, the file's name will be called New Behavior Script. Let's rename this file to Robots. Typically, C# files must have the CS extension. However, Unity will automatically add this extension on your behalf. You do not need to include it. We can open this file by double-clicking on it. Unity should open Visual Studio Code with our file. Initially, Unity will provide us with boilerplate code. We can safely empty the file. Throughout this section, we will create this file from scratch. This is one way of creating a file. An alternative solution is to create the file from Visual Studio Code. However, there are some problems with this approach. Let's give it a try to learn about potential issues. From within the Assets/Examples directory, right-click the folder to create a new file. The name of our file will be called anotherexample.cs. Take notice of the file name. File names should not have spaces. In addition, words should always be capitalized. It's common practice to follow this naming convention for files. We'll be adopting this practice for our game. So, there are 3 things to be aware of. Firstly, we must add the CS extension for the file. Without Unity, we must always remember to add the extension. Otherwise, our C# script will not be recognized. Secondly, the file is completely empty. Previously, to help us get started, Unity scaffolded code. By creating the file manually, we must write the code ourselves. Lastly, the file will not be recognized by Unity. Unity keeps track of our files. However, if a file is created outside of Unity, it will not be registered with our game. Luckily, we can force registration by switching to the Unity editor. Let's quickly switch over. As we do so, a new window will appear. For a brief moment, Unity will scan our project for new files. If it detects a new file, it'll attempt to register it. Normally, this process should go smoothly. Registering our file is an important step. If a file is not officially registered with a project, you may experience issues. Not all features will function properly. I always recommend switching to Unity after creating a file in Visual Studio Code. Alternatively, you can create your scripts from within Unity. By doing so, you should encounter fewer issues. In the following lecture, let's start writing code. In this lecture, let's create a namespace for our game. Namespaces are entirely optional. You can create a game without ever using custom namespaces. On the other hand, you might want to consider using a namespace to keep your project organized. Let's explore why. First, let's understand the concept of a namespace. Namespaces are a feature in C#. Therefore, they're not specific to Unity. You can carry this knowledge to other areas. A namespace can be thought of as a virtual folder for your code. Code organization is considered to be a huge priority for developers. If you've ever spoken with an experienced developer, one of the pain points of development is organization. Unorganized code is difficult to work with. If you're creating a small game, it might not seem like a big deal. Once you start working on medium to large size games, it can become a nightmare to manage thousands of lines of code. To understand why, let's talk about folders. On your system, you may have folders for your music, pictures, and videos. Technically, you can store various file types from within a single directory, but that would be inefficient. Finding files would take a while. Most people will organize their files into folders. The most significant advantage of using folders is reusing file names. For example, let's say we are wedding photographers. Every wedding has a cake. To keep our project organized, each wedding may have a folder with a file called cake.jpg. These are duplicate file names. If these images existed within the same folder, our system would not allow them to have the same file name. However, since they're in separate directories, we can repeat file names without conflicts. This is the advantage of using folders. Without folders, we would have to be creative with our file names. The same idea applies to programming. Namespaces are the solution for organizing the names in our code. You can think of them as virtual folders for your code. We may want to repeat names. Unfortunately, most programming languages do not allow duplicate names, which can force us to be creative with our names. By using namespaces, we can avoid these types of conflicts. For example, let's say we had a combat system in our game. Combat implies there are two characters fighting each other. Both characters may have an action called attack. With namespaces, we can refer to the action as attack. Otherwise, we would have to use names like player 1 attack and player 2 attack. Namespaces are an optional feature of C#. In general, they're heavily adopted within Unity and the programming community. It's in our best interest to start creating namespaces. In the next lecture, let's create a namespace. In this lecture, let's create a namespace. It's very easy to use them. In Visual Studio Code, open the robot.cs file. For the rest of this course, you should always have Visual Studio Code open. We're going to be writing code regularly. Previously, we cleared the contents of this file to start from scratch. At the top of the file, type the following: namespace. After typing the namespace keyword, the name gets highlighted by the editor. This behavior is worth noting. In C#, there are words reserved by the language. If we type these words, the program will perform a specific action. The word namespace is known as a reserved keyword in the language. In the resource section of this lecture, I provide a link to a list of keywords. There are numerous keywords under the language. Don't worry, we'll be going through most of them. Feel free to read up on each keyword as we learn them. Let's go back to our editors. Be careful when writing code. If you were to write a reserved keyword, the program might perform an action that you didn't intend for it to do. In this case, we're interested in creating a namespace. After typing the namespace keyword, we need to provide a name for our namespace. There are a few rules for writing names from within our code. Alphabetic, numeric, and underscore characters are allowed from within a name. On the other hand, special characters or spaces are not allowed. As long as we follow these rules, we shouldn't encounter errors in our program. It might seem ridiculous, but there are various naming conventions offered by the community. To be more specific, there are 3 common naming conventions. The first naming convention is called camel casing. Words are strung together without spaces. For readability, each word is capitalized except for the first word. The second naming convention is called snake casing. All letters are lowercase. In addition, words are separated with an underscore character. Lastly, we have a naming convention called Pascal case. It's similar to camel casing. However, all words are capitalized, including the first word. The question becomes, which naming convention do we use? All naming conventions are valid. Neither Unity nor C# will throw an error for being inconsistent with your names. For namespaces, developers prefer to use Pascal casing. But why? Pascal casing is considered to be a standard set forth by Microsoft. Therefore, most developers prefer to follow Microsoft's lead. In the resource section of this lecture, I provide a link to an article by Microsoft with more info. This article provides extensive information on the naming conventions for namespaces. For the game we're developing, we will not be following all rules. The game is going to be reasonably small. I don't think there's a point in over-engineering the final product. Throughout this course, I will try my best to point out best practices. At the end of the day, you have complete freedom with the naming conventions of your code. Let's head back to the editor. After the namespace keyword, the name of our namespace will be called RPG. Lastly, add a pair of curly brackets. We've successfully created a namespace. Anything written inside the parentheses will belong to this namespace. We're not done yet. We'll be writing a lot of code. Namespaces can be organized into nested namespaces. You can think of them as nested folders. After the name of our namespace, add the following: .example. The dot acts as a separator. It's similar to a / character for directories. Once again, this step is optional. However, it's going to be easier to organize our code with nested namespaces. A common practice among Unity developers is using the genre or the game's name as the first namespace. The second namespace is the name of the folder. In our case, we're using rpg.example. We're finished with our namespace. In the next lecture, let's start creating objects. In this lecture, we're going to talk about objects. Understanding objects are absolutely crucial. Everything we write and do revolve around objects. We'll start the discussion on this subject by understanding object-oriented programming. What is object-oriented programming? In the English language, we have a generic term for objects in the world called things. Books, cars, keyboards, and toys are considered things. It's a generic category for items in the real world. In the programming world, the technical term for things is objects. An object can be almost anything: buttons, characters, platforms, checkboxes, and anything that appears on the screen is an object. I'm oversimplifying the term, but that's generally what it means. Object-oriented programming, also referred to as OOP, is the idea of creating objects for storing data and functionality. Every C# application is written with objects. We won't get far if we can't create objects. By creating an object, we can write the logic for a component in our games. But why objects? Why does C# care so much about objects? Scaling is the biggest challenge faced by developers. A couple of lines of code aren't hard to manage. However, the more ambitious your project is, the more complex your code can get. How do you manage thousands of lines of code? The answer is with objects. Objects allow your code to be reusable and isolated. Dozens of features come with objects that allow for interesting design patterns to be implemented. These patterns make it easier to manage your games. The price of object-oriented programming is the learning curve. It can be difficult to wrap your head around some of the concepts. Lucky for you, you're taking this course. Now that we understand what objects are, we can begin to create them. We'll start in the next lecture. I'll see you there. In this lecture, we're going to write a class. A class is a blueprint for creating objects. It's not the actual object itself. In the real world, we have blueprints for houses and other things. They're instructions for how to build something. In the programming world, classes can be considered blueprints for objects. It gives our machine instructions for creating an object. In your editor, open the robot.cs file. Let's create a class for our robots. Inside the file, type the word class. There are a few things worth noting. Firstly, the class keyword is indented. This formatting is common practice. Code written from within curly brackets is referred to as a block of code. A block of code should always be indented. It's not necessary. C# won't throw errors for unformatted code. However, this formatting practice is meant to help developers visualize the hierarchy of code. This class is defined inside the namespace. Therefore, it should be indented to help us understand that. Here's a general rule of thumb. Anytime you add curly braces, the code inside them should be indented. The second thing worth noting is the class keyword. It's highlighted with the same color as the namespace color. We have another reserved keyword on our hands. The class keyword will instruct the program to create a class. After typing this word, we need to give our class a name. The name of our class will be called Robot. Lastly, add a pair of curly brackets. Once again, code written inside the curly brackets will be indented. Curly brackets help our program understand what code is related to our class. Anything we type inside these curly brackets will be associated with this class. If we type code outside the curly brackets, they won't be a part of the class. We're finished. We've successfully created our first class. It doesn't do anything, but that's fine. As we progress through the lecture, we'll add more logic. Our goal was to simply create a class. There are two things worth mentioning. The name of the class is Pascal cased. Microsoft recommends using Pascal casing for the name of your classes. For the rest of this course, let's follow this naming convention. Lastly, the name of the class matches the name of the file. This convention is extremely important to understand. Unlike before, this step is not optional. Unity expects most C# files to have a class with the same name. The names are case sensitive. If we were to use a different name, we might encounter errors. For this reason, developers will use Pascal casing for their file names. If your file names are formatted incorrectly, I recommend adjusting them before moving on. In the following lecture, let's add data to the class. In this lecture, let's explore the idea of a variable. At the moment, our code doesn't do anything. I think it would be interesting if we started to store data in our objects. C# allows us to store data within an object with a feature called variables. A variable is a way to store information in an object. For example, let's say we created a character in a game. We can store the stats of a character in a variable, such as their health, speed, and defense. We can define as many variables as we want in a class. A common analogy is to think of variables as empty boxes. Within these boxes, we can store anything. C# is considered to be a statically typed language. What does that mean? Sounds like a loaded term. In general, programs must store data. They can store numbers, addresses, and other miscellaneous information. If we're working on a program, we'll most likely be dealing with many changes to our data. This is especially true for video games. If you have a character that moves, their position is an example of data we would store in a variable. Their position can constantly change. Thus, our variables are continually being updated. We may encounter issues whenever updating data. The position of a character should be stored as a number. But what if we accidentally update the position to the name of the character? How is your game supposed to respond to that? It would result in errors. Accidentally assigning the wrong value to a variable is a common mistake. Types prevent this issue because it tells our program or game the type of data that can be stored in a variable. If we attempt to store text in a variable that only accepts numbers, our program will prevent this process from happening. It can even tell us ahead of time. Nothing is worse than building a game and playing it for a few minutes, only to find we stored the wrong type of data in a variable. By setting the data type, Visual Studio Code can catch errors ahead of time. It's a huge time saver. Data types refer to the type of data stored in a variable. You can think of it as a way to categorize data. There are various types of data available. For this course, we're going to focus on 4 data types. They're called int, float, string, and bool. Int is short for integer. It allows us to store whole numbers. Float can also store numbers, but with decimal values. Afterward, the string data type can be used for storing multiple characters. Lastly, the bool data type is short for Boolean. It can store the state of something. There are only 2 possible values for a Boolean value. They're true or false. For example, we can store the state of an item. Has the player used an item already? We can store that type of information as a Boolean value. In the resource section of this lecture, I provide a link to a complete list of data types available. Initially, this may feel overwhelming. Luckily, you can get away with using a handful of data types. Throughout the course, we're going to be using 4 data types from the list. Enough talk. Let's create some variables. In the next lecture, let's start writing variables for our robots. In this lecture, let's create a set of variables. As mentioned before, we'll explore the most commonly used data types for game development. They're integers, floats, strings, and booleans. To get started, open the robot.cs file from our project. Inside the robot class, let's create our first variable. To get started, we'll start with an integer. Integers are a data type for storing whole numbers. For example, we may want to store the age of our robot. In the class, type the following: int age =5, semicolon. Let's dissect this line of code piece by piece. Firstly, we're setting the data type. This step is always required. C# must know the type of value we're storing in a variable. For integers, the data type is called int. As you can see, this keyword is reserved by the language. Next, we must provide a name for a variable. The rules for naming variables are the same as namespaces and classes. There's one difference. It's considered standard practice to use camel casing instead of Pascal casing. Once again, this standard is set by Microsoft, which we'll be adopting. After setting the name, we're adding the equals character. The technical term for this character is called the assignment operator. Sounds complicated, but it's super simple. It allows us to set the value of the variable. In this case, the variable's value is 5. The last piece is a semicolon. In the English language, sentences must be ended with a period. A period indicates the end of a sentence. New sentences can be written after the period. For programming languages, we are giving instructions to a machine. The machine is unaware of when an instruction ends. Without ending the previous instruction, a new instruction cannot run. The semicolon character denotes the end of an instruction. This brings us to the question, why don't we add semicolons to the namespace or class? Blocks of code do not need semicolons. C# is smart enough to understand that the closing curly bracket is the end of the instruction. For everything else, we must add semicolons. Awesome! We've created our first variable. Let's create 3 more. The second variable will be a float. As a reminder, floats are a data type for storing numbers with a decimal value. For this example, let's store the price for building the robot. Type the following: float price equals 99.99f semicolon. Similar to before, we're setting the data type at the beginning of the line. Next, we're adding the name. Lastly, we're setting the value. There's one difference between floats and integers. The letter F must be added at the end of the number. It's a weird behavior of C#. Our decimal value will not be recognized without this character. 2 more variables to go. Storing text must be stored in a string. Type the following: string name equals McBot, semicolon. The value for the variable is wrapped with double quotes. Do not use single quotes. Otherwise, you may receive an error. In C#, text is considered to be a string. Why do we call it a string? The logic behind the name is strange. Text is made up of characters that are strung together, hence string. Within the double quotes, we may write anything we'd like. This includes reserved keywords. Strings can freely use reserved keywords without consequence. Therefore, we can type the word class inside a string. The C# programming language will not attempt to create a class. It understands that this word is part of the string. There's one more variable that we'll look at. Add the following code: bool is turned on equals false, semicolon. Booleans are a data type for storing one of 2 values, true or false. They're handy for storing data that can be on or off. Booleans are popular because they require less memory than other data types. Therefore, using Booleans over different data types can be more performant. Congrats! We've created a set of variables. At the moment, they don't do anything besides store values. In the next set of lectures, let's try using them. In this lecture, let's take a moment to talk about comments. So far, we've written over 10 lines of code, nothing we can't manage. However, as our code base grows, we may have difficulty keeping track of our code. Comments can help us by adding notes. Comments can be thought of as notes for our code. You can use them as reminders or as a way to document your code. Let's quickly explore the syntax. At the top of the file, we created a namespace called rpg.example. If another developer encounters this line of code, they may be curious about the namespace. We should leave a note for them. Above this line of code, add 2 / characters. 2 / characters create a comment. After these characters, we can freely type anything. This includes gibberish. Comments are not processed as code by Unity or C#. They'll be ignored entirely. This behavior gives us complete freedom over the contents of a comment. Let's write the following note. RPG is the main namespace for our game. This type of comment is referred to as a single-line comment. As the name suggests, the comment only applies to the current line. If we were to break the comment into multiple lines, we would get an error. The next line of code is not considered a comment. To break the comment into multiple lines, we must add the / characters for each line. There is an alternative type of comment called a multi-line comment. Above the variables, add the following characters: ****/. Multi-line comments use different characters. The first pair of characters denote the beginning of the comment. The last pair of characters denote the end of a comment. Similar to before, we can write anything from within the comments. Let's add the word variables. Unlike single-line comments, we can have as many lines as possible. As long as the text appears between the characters, the text is considered to be a comment. Let's add =sign characters below the word. It's important to close the comment. Otherwise, the language may assume the entire file is a comment, which isn't what we want. That's comments in a nutshell. They can be helpful for larger files with dozens of lines of code. You can use them to leave notes for yourself or other developers. In the next lecture, let's keep exploring classes. In this lecture, let's create a constructor method for our robot. As a quick recap, classes are blueprints for creating an object. So far, our code does not get executed until an object gets created. Right now, objects based on our class will have 4 variables called age, price, name, and isTurnedOn. That's great, but we may need to do more than define variables. We may want to execute additional logic upon creation. This is where constructor methods come into play. A constructor method is a block of code executed upon creation. Defining a constructor method is fairly simple. Below our variables, add the following code: robot. Methods must be defined in a class. In addition, the name of a method follows the same naming rules as namespaces, classes, or variables. It's recommended to use Pascal casing for method names. In this case, the name of our method is called robot. This name is not flexible. Constructor methods must have the same name as the class name. Otherwise, the logic written in the method will not be executed. After setting the name of a method, we must add a pair of parentheses and curly brackets. We're going to ignore the parentheses. They're necessary for constructor methods. However, they will be covered in another lecture. Let's shift our focus to the curly brackets. Within these curly brackets, we can write the logic for this method. Code written in the curly brackets will be executed when the object is created. Let's cover some terminology before moving forward. The process of creating an object from a class is known as instantiation. We're not limited to creating one object from a class. An unlimited number of objects can be created from a class. A specific copy of an object is known as an instance. You may hear these words from time to time. Understanding them is key to programming. You can think of it like this. The robot class can be considered a blueprint for building a robot. If we created 10 robots, we would have 10 objects. A specific robot would be referred to as an instance. As mentioned before, constructor methods are executed upon instantiation. This behavior gives us the opportunity to run additional logic. For example, let's try turning the robot on. In our class, we have a variable called isTurnedOn. By default, the robot will be turned off. Let's turn them on by setting this variable to true. Variables can be updated anytime. We're not restricted to the initial values. Updating a variable is similar to creating a variable, with one exception. The data type does not need to be included. It only needs to be included upon creation. As a side note, some developers refer to creating new variables as a declaration. Whenever creating a variable, you can say declaring a variable. Creating and declaring are interchangeable terms. Back to the logic of the constructor method. We can write as many lines of code as we'd like. For now, let's leave our code as is. So far, we've written about 20 lines of code. I think it's time to start running our code from Unity. In the next set of lectures, let's start preparing our class for Unity. In this lecture, we're going to add access modifiers to our code for accessibility. As it stands, Unity will not be able to access our class, properties, or methods. If we attempt to add our class to Unity, we may receive errors. Let's resolve these issues. First things first, what are access modifiers? For simplicity's sake, I will provide a simplified definition. Access modifiers can be a complicated topic to deal with. An access modifier changes the accessibility of a class, property, or method. Let's look at an analogy. Buildings can have dozens of doors. Some doors can have locks. Other doors don't have locks. Doors without locks are accessible to everyone. Anyone can open or close the door. They don't need a key or permission to enter a specific area in a building. On the other hand, if a door has a lock, a key is required to access a room. There are more restrictions in place to access different areas of a building. This idea of applying restrictions to rooms in a building can be applied to classes. Unity is a program outside of our class. If we give our class to Unity, Unity will attempt to access the data from within our class. By default, our data is privatized. Therefore, Unity will encounter issues with our class. To resolve this issue, we must update the accessibility of our class with an access modifier. Let's give that a try. In the resource section of this lecture, I provide a link to a complete list of access modifiers. There are 6 modifiers available. However, we're not going to need all 6. The most commonly used modifiers are public and private. We can safely ignore the other modifiers. These modifiers are available for advanced use cases. I recommend checking out this page after finishing this lecture. It'll provide more detailed information. Let's head back to the editor. Access modifiers can be applied to classes, properties, and methods. First, let's apply a modifier to our class. Add the public keyword to the class. The public keyword allows a class to be accessed from anywhere. Generally speaking, you should always add the public keyword to your classes. Otherwise, Unity may have a difficult time trying to create an instance. The public keyword should always appear before the class keyword. The order of keywords does matter. This applies to all access modifiers. Next, let's apply access modifiers to our variables. Let's add the public keyword to the age variable. The access modifier must always appear before the data type. Let's try using a different modifier. This time, add the private keyword to the price variable. Unlike the public keyword, the private keyword will prevent access to a variable from outside the class. We can freely access the variable from within our class. However, if we had another class attempt to access the price, an error would be produced. The program would reject the attempt to access the price. As a mini exercise, try making the name privately accessible. As for the Boolean, make it publicly accessible. Pause the video and give it a try. Good luck! Welcome back. Were you able to add the keywords? If not, that's fine. Let's try it together. For the name, add the private keyword. Lastly, for the Boolean, set the modifier to public. It's as simple as that. We're almost finished. The last step is to update the constructor method to be publicly accessible. If it isn't, Unity may have difficulty running the method. Let's add the public keyword. Perfect. We've updated the accessibility of our code. Unity shouldn't have a problem accessing our class or its data. In the next lecture, let's keep working on the class to be loaded from Unity. In this lecture, let's finalize our class by inheriting properties from another class. Inheritance is considered to be an advanced topic. It's a powerful feature for sharing code from one class to another. So, what is inheritance? Inheritance is a feature in C# for sharing properties and methods from one class to another. This feature was introduced to help developers reuse code. Reusing code is a big topic in programming. As developers, we should avoid writing duplicate code. Luckily, C# has a few features for helping us reuse code. Inheritance is considered to be one of its solutions. The question is, why do we need inheritance? As far as Unity is concerned, we have a plain class. It will not allow us to attach the class to a game object. Classes must have a set of properties and methods to be recognized by Unity. One solution would be to manually add these features. However, that would take forever. This is where inheritance can be useful. To save time, Unity has a class called MonoBehavior. In the resource section of this lecture, I provide a link to this class. The purpose of this class is to allow our classes to be usable from Unity. On this documentation page, there's a complete list of properties and methods. This information will be available from our class. We can use them as if they were originally created in our class. To understand, let's try inheriting from this class. In your editor, open the robot.cs file. After the class name, type the following code: :unity engine.monoBehavior. The colon character instructs the program to inherit data from another class. After this character, we must specify the name of the class. In this case, we're inheriting data from a class called MonoBehavior. Before accessing this class, we're accessing a namespace called Unity Engine. We're not the only ones who can use namespaces. Unity creates namespaces for its features. The Unity Engine namespace is defined by Unity. Before accessing Unity's class, we must access them from their respective namespace. The dot character acts as a separator. You can think of it as accessing a file from a specific folder. After inheriting data from a class, we can use variables from it. For example, in the robot method, set a variable called enabled to true. The enabled variable is not defined by us. If we were to look through our file, it does not have a definition. Regardless, we're able to use it. Thanks to inheritance, variables from the MonoBehavior class are accessible from our class. They can be used as if they were defined in our class. You can refer to the documentation for a complete list of variables. I'm going to remove this variable. For this example, it's not necessary to modify the MonoBehavior's variables. Unfortunately, we have one problem with our class. To be more precise, the MonoBehavior class has a variable called name. Our class also has a variable called name. As you can imagine, this creates a conflict. To resolve our issue, let's comment the name variable. This behavior is important to understand. We can't have duplicate variable names. Otherwise, the language will complain. After adding the comment, the error goes away. Great, we're getting close to finishing our class. In the next lecture, let's simplify our code. In this lecture, let's update the robot class to be readable. As we learned, we're inheriting the variables from the MonoBehavior class. Before inheriting the variables, we must access the class from the respective namespace. This goes for other classes defined by Unity. We must always type Unity Engine before every class. In my opinion, this makes our code slightly unreadable. I don't think it's a good idea to constantly type the namespace. Fortunately, C# has a feature for making our code readable. At the top of the file, add the using keyword. The using keyword allows us to reference a namespace from our file. By adding this keyword, we can add a namespace. Let's add the Unity Engine namespace. Next, let's remove the Unity engine namespace from the class. Our code will still work. The using keyword allows developers to reference classes from a specific namespace without typing the entire namespace. The program will assume a class can be found within a referenced namespace. In this case, Unity will search for the MonoBehavior class from the Unity engine namespace. It's common practice to add a list of namespaces at the top of the file. This feature makes our code readable. In the next lecture, let's attach this class to a game object. In this lecture, let's add the robot class to a game object. We haven't had the opportunity to test our work. I think it's time to verify our code is fully functional. We should enter Prefab edit mode. Let's double-click on the robot prefab. Next, select the robot game object from the hierarchy. It should be the parent object of our prefab. Under the inspector, we can add our class as a component. Believe it or not, all components are classes. The transform component is a class. So are the mesh filter and mesh renderer components. Unlike our class, these classes are created by Unity. We can add our class like any other component. Click on the Add Component button. Search for the robot class. As you can see, our class appears on the list. If our class didn't inherit the MonoBehavior class, Unity would not allow us to add the class to the game object. Select this class from the list. Just like that, the class becomes a component. If we look closely, our variables have been converted into fields. Public variables can be modified by the editor. If a variable is private, Unity will not be able to modify our variables. This is a big difference between public and private variables. You'll notice something strange. The isTurnedOn field is checked. Our variable is set to false. Unity does not check the box for false values. So, why is the box ticked? The reason is simple. Upon adding the class as a component to a game object, Unity will create an instance of our class. As we learned, constructor methods will run when a class is instantiated. Therefore, the variable gets updated to true. Thus, the box gets ticked. Let's try proving this behavior. Switch back to Visual Studio Code. Let's apply a comment to the isTurnedOn variable from within the robot constructor method. Next, head back to Unity. The changes won't be applied because Unity has already created an instance from our class. We can force a new instance by removing the component. Right-click on the name of the robot component. Select Remove. Lastly, add the robot class again. This time, the checkbox is left unticked. By not updating the variable from within the constructor method, the variable is left alone. Perfect. We've successfully created our first class. In almost an hour, we created a class with custom data and methods. It took a while, but it was well worth the effort. In the next set of lectures, let's expand on our class by adding more features, such as custom methods. In this lecture, let's create a custom method. So far, we've learned about constructor methods. Constructor methods are blocks of code that are executed upon instantiation. They're great for setting up a class. On the other hand, we may want to break our logic into different blocks. Luckily, we're not limited to constructor methods. Custom methods can be defined for outsourcing additional logic. For example, let's create a custom method for applying a discount on the price of the robot. In your editor, open the robot file. At the bottom of the class, define a method called CalculatePrice. Similar to before, let's add the public keyword. Unlike constructor methods, we must add a special keyword to custom methods. Before the name of the method, add the void keyword. Methods must specify the return value. We'll talk about return values in another lecture. For now, add this keyword to prevent Unity from throwing an error. Inside the body of the method, we can do whatever we want. For this example, let's try applying a discount to the price of the robot. C# supports all mathematical operations. We can add, subtract, multiply, and divide numbers. Let's set the price variable to the following value: price minus price asterisk 0.1f. A few things are worth mentioning. We're wrapping the second half of the equation with parentheses. According to the rules of math, this portion of the equation will be evaluated before subtracting from the price. In this example, we're grabbing 10% of the original price. After grabbing a percentage of the price, we're subtracting the value from the original price. As a reminder, the f character must appear after a decimal value. Numbers with decimal values must always have this character. Otherwise, our number would not be recognized. Lastly, the asterisk character can perform multiplication. Our method is ready. The next step is to call it. By default, custom methods will not run. We must call a method for the logic to be executed. Calling a method is another way of saying to run the block of code. In some cases, you may hear developers say, invoke a method. Either way, we must manually tell Unity to run this method. We can do so by typing the method's name followed by a pair of parentheses and a semicolon character. Let's run the method from the robot method. Before testing our code, let's update the access modifier of the price variable. Currently, the price variable will not be viewable from the Unity editor since the accessibility is set to private. Change the modifier to public. Great, let's head on over to Unity. If you're in Prefab edit mode, exit this mode. The script won't run until we re-enter Prefab edit mode. Upon entering Prefab edit mode, the price should have been updated. Let's click on the root game object to view its components. As you can see, the price has been changed from its original value. That's awesome. We've outsourced the logic for applying discounts in another method. We do not have to immediately apply a discount. Our custom method can be called any time to change the price. This feature gives us flexibility. In the next lecture, let's try customizing the behavior of our method with parameters. In this lecture, let's update the calculate price method with a custom discounts. We may not always want to apply the same discounts. As it stands, the same discount will always be applied to the price. Methods can accept custom values called parameters. You can think of them as variables for a method. Let's give them a try. In the calculate price method, we can define parameters from within the parentheses. Inside the parentheses, variables can be created. Let's create a variable called discount with the float data type. Unlike before, we're not providing an initial value for the variable. The value for this variable can be set when the method is called. After adding this parameter, an error will be thrown by our editor. A red squiggly line appears below the calculate price method. Let's read the error. There is no argument given that corresponds to the required formal parameter discount of robot.calculatePrice. The error states that we're not setting the value for the discount variable. The question is, how can we set a value? Values can be set for a variable from the method's invocation. Inside the robot method, we can set the variable from within the parentheses. Let's pass in 0.1f. Here's what's happening. Whenever we call the CalculatePrice method, a new variable gets created called discount. The value of this variable will be based on the value passed into the parentheses from where the method was called. Keep in mind, the discount variable is only accessible from within the method. Unlike the price variable, we can't use the discount anywhere else. It's local to the respective method. Let's try using this variable by changing the decimal value with the variable like so. We're not limited to a single parameter. Multiple parameters can be added to a method. Let's take our method a step further by adding support for quantity. Parameters can be separated with a comma. After the first parameter, add a comma. Next, add a parameter called quantity with the integer data type. Inside our method, wrap the equation with a pair of parentheses. Next, multiplying the result by the quantity variable. We're almost finished. The call to the CalculatePrice method must be updated. Let's pass in 2. Time to test our code. Save your work, and then head on over to the Unity editor. If you're in Prefab edit mode, exit the mode. Lastly, enter Prefab edit mode for the robots. If we look at the inspector for the robot game object, the price has been updated. This time, the discount and quantity variables have affected the final price. Awesome! Parameters are a feature for customizing the behavior of a method. If we call the same method, we can pass in completely different values to change the price. They're going to be incredibly useful in the future. In the next lecture, let's keep exploring features related to methods. In this lecture, we're going to explore another feature of methods called return values. Sometimes we may need a value calculated by a method. By default, the calculated value gets stored in the price variable. We may not want to always store the value in one variable. In some cases, we may wish to store the value in a different variable. One solution would be to update the variable from within the CalculatePrice method. However, that would be inefficient. The method should be more flexible. We can resolve our issues by returning the value. Let me show you how that's done. First, we must specify the type of value that will be returned by our method. The return type must be specified before the name of the method. If we don't plan on returning data from a method, the data type must be set to void. The void data type represents nothing. We are required to always specify the return type for our methods. The exception to this rule is the constructor method. For any other method, the return type is required. Since we're trying to return the calculation, let's set the return type to float. After setting the return type, we must return a value. Let's replace the price variable with a keyword called return. The return keyword instructs the program to return the value written after it. In this case, the return value will be the calculation. Our method will wait for the calculation to be complete before returning the result. However, the price variable will not be updated anymore. We can keep the same behavior by updating the robot method. Instead of just calling the CalculatePrice method, we can set the price variable to return the value of the CalculatePrice method. Here's what will happen. By calling the CalculatePrice method, C# will run the code from within the method. The value calculated from the method will be exposed outside of the function. Capturing the value can be done from where the method is called. In this case, the value gets captured and stored in the price variable. There are a few things to keep in mind when returning values. Firstly, we're limited to returning a single value. Secondly, the return value must match the return type. The CalculatePrice method's return type is float. Therefore, the return value must have the same type. Using return values can be a useful feature. Our method doesn't need to care about how the value gets used. A value is returned, and that's it. Let's try checking our work. If we did everything, the same result should appear within the Unity editor. Switch back to Unity. Next, enter Prefab Edit Mode. Select the Robot Game object from the hierarchy. As we can see, the price variable has been updated with the return value from the Calculate Price method. It's the same behavior as before. This time, we do not need to update the method. We can simply swap the variable that's storing the price. Alternatively, a new variable can be created for storing the new price. Overall, return values can be helpful in quickly using a value outside of the method. In the next lecture, let's try using the new price to change our robot's behavior. In this lecture, let's control the flow of logic with conditional statements. So far, we've been executing code immediately. We may not always want this to be the case. Specific pieces of code should be executed when a condition is met. For example, if the player is within proximity of an enemy, the enemy should chase the player. If a player's health drops below 0, the game should end. Performing actions based on a condition is known as control flow. Let's update our robot to check the new price. At the moment, we're immediately applying the discount. Before applying the latest price, we should verify the price isn't too low. Otherwise, we may not be able to make a profit. Inside the script, let's assign the return value to a new variable. Rather than updating the price variable immediately, we'll store the new price in a temporary variable. After confirming the price is not too low, we'll update the price. Set the variable name to new price. Next, set the type to float. Unlike before, we're not declaring the variable from the class level. Instead, it's being defined from the method. The main difference is the accessibility of the variable. By defining a variable on the class level, the variable is accessible to all methods, whereas variables defined from within a method are only available from the method. Next, let's try updating the quantity to 1. It'll be easier to keep track of the price when there's one robot. After defining the variable, add the if keyword. The if keyword creates a conditional statement. Conditional statements are lines of code that perform a check based on a condition. We can write the condition by adding a pair of parentheses. Within these parentheses, add the following code: new price greater than 75F. I'm introducing a new operator called a comparison operator. In the resource section of this lecture, I provide a link to a complete list of operators. As their names imply, comparison operators will compare two values. There are a total of 4 comparison operators. They're mainly used with numbers. After performing a comparison, the operator will create a Boolean value. We can use this Boolean value from within our conditional statements. Let's head back to Visual Studio Code. Conditional statements may only accept Boolean values. For example, if we were to remove the latter portion of the conditional statement, an error would get produced. In this example, we're passing in a float value, which is not accepted by C#. Let's revert the condition. Luckily, comparison operators create Booleans. If the new price is greater than 75, we can consider the new price to be safe. Add a pair of curly brackets. Code written inside the curly brackets will be executed when a condition is truthy. Let's set the price variable to the new price variable. What if the price isn't greater than 75? In this case, we should reject the new price. This step is optional. If an if condition fails, we're allowed to create a default response. After the if statement, add an else statement with curly brackets. The else statement will run when the if condition fails. There's one rule for using else statements. They can only be added after the if statement. If we attempted to write code between both statements, we would get an error. The order of statements does matter. Inside the else statement, let's add a method called print. This method doesn't exist within our class. Luckily, it's a method defined in the MonoBehavior class. Thanks to inheritance, we have access to it. It'll output a message to the console. The message can be configured by passing in a string. Let's output the following message: price is too low. The print method is beneficial for debugging code. We can output custom messages to help us track changes and behavior from our class. Let's give our code a test. Switch over to Unity. Next, enter Prefab edit mode for the robot. As we do so, the price gets updated. That's great! We can rest easy knowing the price will never fall below a threshold. Disasters can be avoided when someone tries to apply a discount lower than anticipated. The code from the else statement never gets executed. Let's try triggering it. Head back to the text editor. Inside the calculate price method, set the discount to 0.7. Next, head back to Unity. We're going to exit and enter Prefab edit mode for the robot. This time, things are different. If we look at the price, the original price has not changed. This means the if block was never executed. What about our custom message? The print method will display the message from within the console window. This window can be found next to the project window. As you can see, the message from the else block gets rendered. That's perfect. We can be made aware of errors before they get out of hand. This information can help us by reminding us to use a more reasonable discount. Before ending this lecture, there's one final thing I want to mention. You may receive an error from Unity regarding an unused variable from our class. If you encounter this error, you can safely ignore it. It's not going to break the game. One last thing. Unity may forget to clear the console when files are updated. You can manually clear the console by pressing the clear button. This button removes all messages from the console. Be sure to clear the console during updates to your codebase. Otherwise, you may receive messages from older versions of your code. In the next lecture, let's cover an alternative solution for writing messages to the console. In this lecture, we will explore another class for logging messages into the console. Debugging code can be a tedious process. The most helpful tool at our disposal is the console. We're not limited to logging custom messages. Variables can be logged in the console. So far, we've explored the print method for logging values. There's a class in Unity for logging messages called Debug. In the resource section of this lecture, I provide a link to this class. This class has various methods for logging values into the console. Let's explore the different methods. Switch over to your code editor. In the robot method, we're using a conditional statement to check the price. If the price is too low, we're rendering a message to the console with the print method. Behind the scenes, the print method uses the Debug class to write a message. Unity has provided the print method as a shorter way to access the Debug class. Unfortunately, the print method does not give us the flexibility to change the color of the text. Changing the color can help other developers understand the severity of a problem. Let me show you what I mean. Below the print method, run the debug.log method. The debug.log method is the most common method available in Unity. it writes a message to the console. It performs the exact same action as the print method. Whenever possible, I prefer to use the print method over the debug.log method. There are 2 points worth mentioning. Firstly, the print method is only available with the MonoBehavior class. If you have a class that does not derive from the MonoBehavior class, you will not be able to write messages to the console. In these cases, you can fall back to the debug.log method to print messages. Secondly, we're accessing the log method from a class called debug. You can hover your mouse over this portion of the code to identify the class. Looking closely, the debug class can be found in the Unity Engine namespace. Luckily, since we're referencing the Unity Engine namespace at the top of the file, we do not need to include it. Typically, we would write the method without the class name. However, this behavior is only possible when the method exists within the same class. This is why we can run the calculatePrice method without referencing the robot class. The robot method is allowed to call methods from within the same class. Since the log method can be found in a different class, we must write the name of the class before calling the method. The dot character allows us to access a method or property from within a given class. Similar to the print method, the log method accepts a string. Let's write the following message: price is too low. Next, let's run another method called debug.logWarning. The log warning method will write a message to the console with a warning icon. In a moment, we will get an opportunity to view the differences between these methods. Let's write the same message as before. Afterward, let's explore one last method. It's called debug.logError. This method produces a message in the console with an error icon. Same as before, let's use the same message. There are other methods available from the debug class. However, these methods are the most commonly used methods from this class. Let's check out the result by switching to Unity. Before entering Prefab Edit mode, I recommend switching to the console window. After doing so, clear the console by pressing the Clear button. The console shouldn't be cluttered with messages from previous attempts. After clearing the console, enter Prefab Edit mode for the robot. If we switch to the console, dozens of messages get logged. Scroll to the top to view the first few messages. Newer messages always appear at the bottom of the console. The first 2 messages should be from the print and log messages. As you can see, they both have the same appearance. The question is, how can we tell the difference? Below the message, Unity provides the name of the method that wrote the message. The first message was generated by the Unity Engine.MonoBehavior print method, whereas the second message was generated by the Unity Engine.DebugLog method. Up next, we have the messages from the log warning and log error methods. Unlike before, they have different icons. Aside from that, they're very similar. None of these methods will disrupt the player from playing the game. The purpose of these methods is to help us debug our game. So, which method should we be using? Initially, you may be interested in sticking with the debug.log method. However, it can be useful to diversify your usage of each method. Generally speaking, developers will use the debug.log method for helpful information. The debug.log warning method can be used for rendering potential problems with your game. Lastly, the debug.log error method can be used for rendering game-breaking problems. Warning messages are considered to be less critical than error messages. I prefer to use warnings for potential issues only. There's one last thing I want to mention. If we were to click on any of the messages, a small box will appear at the bottom of the console. This information is referred to as a stack trace. A stack trace is a list of methods executed to produce the message. It's possible that we may call the same methods multiple times in various files. The problem can occur from any of these files. To help us track down the error from a specific file, Unity will provide a stack trace. The specific file is listed from within the stack trace, thus helping you pinpoint the exact location of where an error occurred. Let's examine the stack trace. The stack trace provides the exact path to the file name. At the end of the file name, we're given the line number. Hopefully, this information will be helpful with debugging your games. Throughout the course, we'll get an opportunity to use the Debug class to help us create our game. In the next lecture, let's explore a few more features before going back into game development. In this lecture, we're going to start using generics to make our methods flexible. Let's take a look at the else condition of the robot method. As we learned, the print method was introduced as a shorter way to write the debug.log method. It's not uncommon to create methods for calling other methods for the purposes of writing less code. Sometimes, you may have to repeat long lines of code. Outsourcing a single line of code into a method can be a great way to save time and readability. Let's try creating a custom method for logging messages to the console. This way, we do not have to type debug.log. At the bottom of the class, define a public method called log. The return type will be void. Inside the list of parameters, let's add a parameter called message. Its type will be string. Lastly, let's log the message parameter with the debug.log method. All we're doing is creating a shorthand method for logging values into the console. Let's give our method a test. Back in the robot method, let's add comments to the other messages. You can apply comments to multiple lines of code by highlighting them. Next, press the Ctrl/keyboard shortcut. This shortcut will automatically add comments to each line of code. We're adding comments to prevent the console from being cluttered. We're shifting our focus to the custom method. Next, below the else block, run the log method with a custom message. Nothing complicated so far. Let's take it a step further by logging variables. The debug.log method accepts additional types. We can log numbers, booleans, etc. Let's try calling the log with the age variable. Next, call the method again with the isTurnedOn variable. In our first attempts, the editor was fine with calling the method. For the other attempts, errors are thrown. If we hover our mouse over the age variable, the error states the following: cannot convert from int to string. The error is self-explanatory. C# is a strict language. If our method expects a string, we're limited to passing in strings. Passing in a value with a different data type than the data type assigned to the parameter will cause an issue. In this case, we're attempting to pass in an integer instead of a string. There are two solutions for resolving this issue. One is better than the other. Let's try the incorrect solution. Scroll to the log method. Let's create 2 copies of this method. For the first copy, set the name to log integer. Next, change the parameter's type to int. For the last copy, set the name to log boolean. Lastly, set the type to bool. In total, we have 3 methods for logging values with different types. Back in the robot method, change the second method to log integer. Lastly, change the last method to log boolean. After performing those updates, the editor is happy. Any errors have gone away. This solution works but is not scalable. The C# programming language has dozens of types. In addition, it's possible to create custom types. Unity introduces additional types, which we'll be exploring throughout the course. For every type, we must add a new method. As you can imagine, it would be annoying to create a new method for each type. Our solution is not scalable. Generics were introduced to address these types of issues. A generic can be thought of as a placeholder for data types. Instead of assigning a single type to a variable, generics allow our data to have different types, hence the word generic. Let's implement a generic on the log method. First, remove the log integer and log boolean methods. They won't be necessary. Next, after the log method name, add a pair of angle brackets. Generics can be added to a method by adding a pair of angle brackets. From within these brackets, we must provide a name for the placeholder. Let's set the name to placeholder. After creating the placeholder, we can apply this type anywhere in the method. This includes the method's parameters. Replace the string type with the placeholder type. By using a placeholder, the type of the variable can be swapped with various data types, such as strings, booleans, or integers. Back in the robot method, change the method to log. After changing the methods, the errors do not get produced. C# is able to replace the data type with the data type of a value passed into the method. This process is automated for us. There is a way to manually set the type. If a method has a generic, we can add angle brackets to the method invocation. For example, let's add the type for the age. Next, we can set the type of the variable passed in. This step is entirely optional. If we hover our mouse over the last log method, the generic is already applied. The program detected the type for the isTurnedOn variable. It automatically sets the generic for us. Let's try testing our code. Switch over to Unity. Next, enter Prefab edit mode for the robots. Under the console window, the messages have been logged. With generics, we can create methods with flexible types. For this course, we're not going to be creating generics. However, we will be using generics from other methods. It's good to know how they work. Before I end this lecture, there's one more thing I want to mention. Switch back to the text editor. The name of our generic does not need to be placeholder. Any name is valid. It's common practice to use the letter T as the name. It's short for the word type. In most examples, you will find developers adopt this practice. This includes the Unity team. Just be aware of that when reading documentation. In the next lecture, let's move on to the next topic, which is attributes. In this lecture, let's explore one more feature of C# called attributes. Attributes are an advanced feature in the language. We won't be covering the creation of attributes. It would take a while to discuss the concepts. However, we will learn how to use them. Unity offers various attributes to help us develop games. To begin this discussion, we need to understand the idea of compilation. For the sake of simplicity, I'll be simplifying the explanation of compilation. There's a lot that goes into compiling a program. So, what is compilation? In an earlier lecture, we discussed the idea of machine code. Naturally, computers can't understand C#. C# is considered to be a human-readable programming language. Programming languages were invented to make writing code easier. Regardless, our code needs to be transformed into machine code. The process of transforming our code from one language to another is called compilation. In some cases, some developers consider C# to be interpreted. Either way, our code is being transformed into machine code. After our code has been transformed, it can be executed. So, you may be wondering, why is this important to know? Attributes are designed to provide information to the compiler. They can do so much more. However, this is primarily what they're used for. Let's look at an example. Like I said before, we're not going to create attributes. That would take too much time. Luckily, C# and Unity provide dozens of attributes for handling the most common tasks. For example, let's say that only one robot can be sold at a time. In the script, we have a method for calculating the price with the quantity. It doesn't make sense to include the quantity in the price. One solution would be to update the method. However, there's one problem with this approach. What if we shipped our code to production before the new policy? It's not uncommon to update code after a game has been released. If we were to update a method, we could break our game. So, what is the solution? Rather than updating the current method, we can create a new method. Let's create a copy of the calculate_price method. Rename it to apply_discount. Remove the quantity parameter. Lastly, let's update the return value to not use the quantity parameter. So far, we have two methods for performing similar calculations. Other developers might be confused. Which method should they use? What if they use the wrong method? This scenario is where an attribute can save the day. There's an attribute called obsolete. This attribute allows us to mark a method as depreciated. Before using this attribute, we should reference the namespace for this attribute. At the top of the file, add a using statement. The name of the namespace is called system. The obsolete attribute is defined by the .NET platform. Attributes from this platform can be found under the system namespace. It's not specific to Unity. Head back to the calculate_price method. Above this method, add a pair of square brackets. Inside these brackets, add an attribute called obsolete. Attributes can be applied to a method by adding a pair of square brackets. The name of attribute should be inserted in these brackets. In this case, we're applying the obsolete attribute to the calculate_price method. The compiler will warn developers who attempt to use this method. If we were to scroll to the robot method, a yellow line would appear below the calculate_price method. According to the error, our method is obsolete. This information is helpful, but it can be improved. It's considered good practice to provide an alternative solution. We should recommend developers to use the apply_discount method. Back at the calculate_price method, attributes can accept data like methods. This step is optional. If an attribute supports additional configuration, we can add a pair of parentheses after the attribute's name. For the obsolete method, we can pass in a string that'll act as a custom message. Let's write the following message. Calculate price is deprecated. Use apply_discount instead. Next, let's check out the error again. This time, the message from the attribute appears from within the error. Adding this information helps developers migrate from the old method to the newer method. It can also prevent developers from accidentally using an older method. Overall, attributes can be helpful for communicating with the compiler. In turn, external programs can use this information to help us write programs. Throughout the course, we'll get plenty of opportunities to explore additional attributes. Before ending this lecture, I'm going to comment the entire class body. Do not add comments to the class itself. We're left with an empty class. This class may throw errors from the Unity editor. To prevent this issue from happening, we're disabling the code since we're finished with the robot class. In the next lecture, let's cover some final topics. In this lecture, let's update our editors to format our code. So far, we haven't established many rules for formatting our code. Formatting standards is a highly opinionated topic. If you ever work with a company, they're likely to have a few standards in place. At the beginning of this section, we installed an extension to help us write C# code. This extension has a formatter. Rather than constantly formatting our code, we can force the editor to format our code during saves. Let's check it out. In Visual Studio Code, navigate to File, Preferences, Settings. At the top right corner, there's a button for opening the settings file of the editor. If you hover your mouse over it, the tooltip should say Open Settings JSON. Click on it. The interface for modifying settings will modify this file. That begs the question, why aren't we using the interface for enabling formatting? By using the interface, formatting will be enabled for all languages. However, we can only apply a single formatter. We may want to use different formatters for various languages. I consider it to be a good idea to apply formatters to a specific language. Unfortunately, the interface does not provide this option. Therefore, we must directly edit the settings file. If you're not familiar with JSON, that's fine. Let's quickly discuss what it is. JSON is another language. Unlike a programming language, it's designed for storing data. Features such as conditional statements or functions are unavailable. JSON is regularly used for storing settings for a game. Alternatively, you can save player data into a JSON file. Visual Studio Code uses JSON for storing the settings of the editor. It's not hard to modify the settings. JSON follows a key value format. Inside this file, each setting is wrapped with quotes. Afterward, we have a colon character for separating the name of the setting from the value. To the right, we have the value of the setting. Multiple settings can be separated with a comma. Your file may not look like mine. I've modified my settings for web development. Copying my settings is not necessary unless you plan on getting into web development. Let's add new settings. At the bottom of the file, add a comma at the end of the last setting. Next, add a setting called C#. The name should be wrapped with double quotes and square brackets. Settings for specific languages can be created by writing the name of the language. In this case, we're applying settings to C#. After the colon character, add a pair of curly brackets. The curly brackets allow us to group settings. Within these curly brackets, add a new setting called editor.tab_size with a value of 4. Indentation is important for formatting our code. A majority of Unity developers use an indentation of 4. Next, add a setting called editor.formatOnSave with a value of true. This setting will instruct the editor to format the file on saves. Lastly, add a setting called editor.defaultFormatter. The value will be the following: ms-.net tools.c#. The value is the ID of the extension by Microsoft. You may be wondering, how do you get the ID of an extension? Let's check out the C# extension. Switch over to the Extension tab and search for the C# extension. On the page for the extension, there's a sidebar with additional information. Under the More Info section, there's a field called Identifier. This value represents the ID of the extension. By setting the default formatter setting to the extension's ID, Visual Studio Code will hand our code to this extension. From there, this extension will handle the formatting. Let's try testing the extension. Be sure to save the settings before proceeding. Next, open the robot file. Let's try writing poorly formatted code. For example, we can move the opening curly bracket to the same line as the namespace. Technically, this line of code does not produce an error. our code will work as it did before. If we were to save the file, the extension should automatically move the curly bracket into the correct position. Awesome! We've enabled formatting for our code. If your file is not being formatted, you may need to restart the editor. In the next lecture, let's wrap things up by talking about the documentation. In this lecture, let's take a moment to explore the documentation by Microsoft for C#. In the resource section of this lecture, I provide a link to their documentation resource. Initially, you may feel overwhelmed by the documentation. Microsoft manages multiple products for developers. C# is just a single product from the suite of products available. The documentation houses the technical documentation for all products. It can feel cluttered. To find the documentation related to C#, you can scroll to the Product Directory section. From this list, there's a link to the C# documentation. Let's click on it. On this page, we are given links to various topics, from fundamentals to advanced techniques. There's a wealth of information at your fingertips. In my opinion, the most useful section is called C# Language Reference. This section contains info on the supported operators and keywords available in the language. I find myself viewing this section the most. On the bottom left corner, we have a link to download the full documentation as a PDF file. For those of you who aren't on a stable internet connection, it doesn't hurt to have a local copy of the documentation. Either way, it's good to know where you can find the documentation. I highly recommend bookmarking this resource. It'll come in handy throughout your development career. With that out of the way, we've learned the core fundamental concepts of the C# language. There are dozens of additional topics we could cover, but I think it's time to get back into game development. Let's try applying the concepts taught in this section. Along the way, we can pick up additional techniques and concepts. When you're ready, I'll see you in the next lecture. The goal of this section is to move the player around the map. In this lecture, we will install the Input System package to help us detect input from various controllers. Through this system, we can support controllers from Xbox, PlayStation, and Nintendo, not to mention keyboard and mouse. Other controllers can be supported too. Before installing this package, I want to mention an alternative system. Unity has two solutions for accepting input from a controller. They're called Input Manager and Input System. Both solutions accomplish the same goal. So, what's the difference? The Input Manager is the old solution for handling controllers. For a few years, it was considered the de facto standard for handling input. Unfortunately, it did not scale. As new controllers are introduced into the ecosystem, our code must be updated to handle them. Cross-platform support was challenging. Overall, the Input Manager was not easily scalable. The Input System was introduced to address the issues with the original solution. Not everything is sunshine and roses. There are trade-offs for using the new Input System. Let's weigh the pros and cons. Firstly, the Input System can easily support multiple controls. As you'll see in a future lecture, we can add support for a new controller within minutes. Secondly, we can switch between different input mappings. For example, we may want the controller to move the player and control the UI. Both are easily possible without accidentally causing a conflict. Lastly, the input system is event-based instead of poll-based, which can potentially overload a system. If none of these points make sense, that's perfectly fine. As we progress through the section, each point will become clear. So, what are the downsides? Firstly, the input system has a slightly higher learning curve. It can be intimidating to get started. Secondly, there are fewer resources available for learning more. While the input system has been around for a few years, some features aren't highly documented. You may need to rely on trial and error to get the desired behavior. Luckily, you're taking this course. I'll walk you through every step of the way. By the end of the section, you'll become comfortable with the input system to integrate into your own games. For this course, we will incorporate the input system into our game. Soon enough, it'll become the standard solution for games. By default, the new system is not installed with Unity. We must install it as a package. Navigate to Window Package Manager. Next, from the drop-down, select Unity Registry. Search for a package called Input System. During installation, you may be asked to enable support for external controllers. If you don't select this option, you will be unable to add support for devices other than the keyboard and mouse. Select Yes. Upon selecting this option, the editor will restart. Great! The package has been installed. If you were to view the package's info, a new section called Samples may appear. Unity provides examples to help you learn more about the input system. For this course, we're not going to need these samples. You can safely ignore them. In the next lecture, let's try using the new input system. I'll see you there. In this lecture, two concepts must be understood before writing a single line of code. The input system introduces actions and action maps. Let's quickly review these concepts. First, we'll start with actions. An action describes the behavior performed by the player after pressing a button on the controller. In your game, you may have multiple actions. For example, players can walk, run, jump, and swim. If you have a combat system, attacking or defending can be considered an action. Actions aren't limited to gameplay. Typically, games have menus. Interacting with menus may come with its own set of actions. Some examples would be moving around a menu, selecting an option, or moving a slider. If pressing a button on a controller causes the game to behave differently, we can consider it an action. Next, let's talk about action maps. An action map is a group of actions, plain and simple. Grouping actions can be beneficial. By using action maps, the same button can be reused for different actions. Unity can help us switch between different action maps, making it easier to prevent the player from performing the wrong action. Examples of action maps would be swimming, driving, or using a menu system. All actions must be associated with an action map. In most games, you will likely have at least two action maps, one for the player and another for the menu system. In the next lecture, let's create a set of actions for controlling the player. In this lecture, it's time to create actions and action maps. The process is very simple. To get started, we must create an input action asset. Actions are stored in a single file. By keeping it in a file, we can reuse our actions across multiple scenes. To keep our project organized, let's create a folder for storing the core files of our game. In the Assets directory, create a new folder. The name of the folder should be called Core. Next, open the Create menu. Under this menu, search for an option called Input Action. Click on this option to create a new input action asset. Let's set the name to Game Controls. This file will contain the entire list of actions that can be performed within our game. We can edit the list by double-clicking on the file. A new window should appear called Input Actions. Let's merge this window with the Scene and Game windows. This window allows us to modify an input action asset. It's split into 3 sections. We have action maps, actions, and another section for additional settings. The first step is to create an action map. As mentioned before, all actions must be associated with an action map. We can press the plus button to create a new action map. After pressing this button, we must assign a name. Let's set the name to Gameplay. Our first action map will be related to the player. We can click on the action map to begin adding actions. By default, we are provided an action for demonstration purposes. It's safe to delete this action from the action map. Next, we can add a new action by pressing the plus button. The name of our action will be called Move. Nested inside the action is a binding. Bindings won't be reviewed in this lecture. Let's remove the binding from the action. Congrats! You've created your first action. Let's create the rest of our actions for our game. The game we're developing will have a combat system, health system, and dialogue system. Let's define actions for each of these systems. Press the plus button again. This time, the name of the action will be called Interact. In a future lecture, the player will be able to talk with NPCs. To initiate a conversation, the player must press a button on their controller. This action will be associated with this part of the game. Next, let's create another action for attacking called Attack. Add another action for healing called Heal. Let's add one more action to pause the game. The name of the action will be called Pause. Lastly, you can delete the bindings from each of these actions. There's one last step before moving on. Keep in mind, the actions are stored in a separate file. The Input Actions window provides an editor for modifying the file. Like most files, we need to save the changes. At the top of the window, click the Save Asset window. Alternatively, you can check the Auto Save option. Either solution works. After saving the asset, we can move on to the next step. In the next lecture, let's take on an exercise. In this lecture, it's time for a short exercise. So far, we've created an action map for the player. In addition to the gameplay, we're going to add a menu. The menu system should be functional through a device. Players should be able to select and move around the system with their controllers. Therefore, we should create a separate action map. Reusing the current action map doesn't make sense. Players should not be able to heal or attack while moving around on the menu. Here's the exercise. Try creating a new action map. After creating the action map, define 3 actions called Navigation, Interact, and Unpause. You should be able to handle this exercise without a problem. Pause the video and give it a try. Good luck! Welcome back. Hopefully, you are able to add the new action map. If not, let's go through the solution together. As mentioned, the first step is to create an action map. Press the plus button to add it to our asset. The name of the map will be called UI. Next, delete the default action. Afterward, create 3 actions called Navigate, Interact, and Unpause. Lastly, delete the bindings from the action. Awesome! Be sure to save the asset. If you don't have autosave turned on, you must manually save the file. We have successfully created the action maps for our game. An action map for playing the game and another for the menu system. In the next lecture, let's start working on bindings. In this lecture, let's start setting the action type for our actions. From my experience, students tend to get confused by this concept. I'll try my best to explain it. If you have questions, be sure to ask in the Q&A section of the course. Here we go. An action type determines the process Unity goes through to track your actions. Sound complicated so far? Let's dig deeper into the definition. Controlling the player is not as simple as it seems. You need to consider the following. Does the player need to press the button once for an action to be performed? Do they need to perform button smashing? Or do they need to hold a button for an action to be continuously performed? Based on your answer, you can easily choose an action type. Choosing the right action type will make it easier to achieve the desired gameplay behavior. There are 3 action types. They're called button, value, and pass-through. Each has its pros and cons. Let's go through each of them. The simplest action type is the button type. This type will listen for a button pressed once. I'm putting an emphasis on the word single. The button type does not care if the player holds down a button. Once the button has been pressed, the action is initiated. It is not initiated again until the button has been pressed a second time. This behavior is perfect for most scenarios. For example, a player can pause a game with a single button press. It would be awkward to force the player to hold down a button for the game to remain paused. In addition, this behavior can be desirable for games with button smashing. Mario Party has mini-games that require the player to repeatedly smash a button to win. Choosing the button type will be based on what you're trying to achieve in your game. The next 2 types are called value and pass-through. They're very similar to one another. Unlike the button type, these types will listen for a continuous button press. This behavior may be desirable for moving players. Players should move as long as a button is pressed. This brings us to the question, what's the difference between value and pass-through? Unity performs a process known as disambiguation. Alternatively, you may hear this process referred to as conflict resolution. Disambiguation is the process of deciding which controller should trigger an action. The input system supports multiple devices at once. If the player has 2 controllers tied to their system, how does Unity know which controller should trigger an action? Behind the scenes, Unity performs a few checks to make this decision. Disambiguation is performed with the value and button types. However, it's not performed with the pass-through type. If multiple devices are triggering the same action, all of them will cause the action to be activated. This behavior is the most significant difference between pass-through and the other types. Overall, here's a table summarizing what's possible with each type. Technically, you can use value and pass-through types to handle single button presses. However, it's common practice to use the button type. Hopefully, this summary helps you understand the differences between all types. Keep in mind, I've given you a simplified explanation of action types. If you're interested in a technical explanation, check out the resource section of this lecture. I provided a link to the official documentation page for action types. Feel free to check it out for more info. Let's head over to Unity to apply action types. For this course, we're going to be using the button and value action types. It's uncommon to use the pass-through action type. That's not to say it can't be helpful. There are use cases for this action type, which won't be explored in this course. The other types will be suitable for most scenarios. Disambiguation is preferred for most games. For example, what if a player drops one of their controllers? Or what if a player's pet steps on a controller they're not using? This could cause the game to behave unexpectedly. With disambiguation, this process can mostly be avoided. Let's go set the action types for each of our actions. Starting with the move action, set the action type to value. For movement, players should continuously hold down a button. It doesn't make sense to force players to repeatedly press a button to move. As long as they're holding down a button, they'll be able to move. Next, let's set the interact action to button. Players should be able to initiate dialogue with an NPC with the single press of a button. Let's use the button type for the attack, heal, and pause actions. Awesome! The actions for the gameplay action map are ready. Let's configure the UI actions. For these actions, they can all be set to button. Typically, menu systems require the player to press a button for each interaction. However, in some cases, you may want to allow continuous pressing. For our game, we're not going to go that far. The button type will suffice. We're one step closer to moving the player. In the next lecture, let's begin applying bindings to each action. In this lecture, it's time to add bindings to our actions. At the moment, none of the buttons on our keyboard causes the player to move or attack. The next step is to add a binding to each action. A binding is a specific button pressed on a device to trigger an action. The input system supports the most commonly used devices for playing games. Keyboards, gamepads, and mobile devices are supported with the input system. We can even use pens. Interestingly, we're not limited to a single binding for an action. Multiple bindings can be added to an action from either the same or a completely different device. This practice is common in games. For example, Celeste is a game with 2 buttons for jumping, dashing, and grabbing. While not required, it can be helpful to bind multiple buttons to a single action for flexibility. Let's try binding the actions for our game. We'll start with the gameplay action map. Adding a binding is easy. The move action will be skipped for this demonstration. Unlike the other actions, the move action will require a complex setup. In the future, there will be a lecture dedicated to this action. Therefore, let's start with the interact action. This action will handle initiating a dialogue with an NPC. To the right of the action, press the plus button. Under this button, a drop-down should appear with various options for adding a binding. Let's select the first option. The other options will be discussed in another lecture. This option will allow us to add one binding to the respective action. Under the settings, there's a field called Path. The Path field must be set to the button for activating the action. If we were to view the drop-down, we'd be given a complete list of buttons that are supported. We're not limited to our current device. Various devices from other consoles can be used. Searching through this list can be cumbersome. Luckily, we can press the Listen button to help us find the respective button. After pressing this button, press the E key on your keyboard. Almost immediately, the E key is presented as an option. Let's select it. Great, we've bound the E key to the interact action. If the button does not work, you can manually search for the key with the search feature. I've got an exercise for you. Bind the rest of the actions with keys from your keyboard. For this game, we're going to use the space key for attacking, the Q key for healing, and lastly, the escape key for pausing. Unlike the other keys, you may have trouble with the escape key. I'll let you figure it out yourself. As usual, I'll walk through the solution after you've attempted the exercise. Pause the video and good luck. Hopefully, you were able to bind the keys to their respective action. If not, that's alright. Let's walk through the exercise together. For the attack action, add a new binding. Under the Path field, listen for the space key from the keyboard. Next, let's repeat this process for the heal action. This time, the key we're listening to is the Q key. Lastly, we can do the same for the pause action. Unlike the other actions, binding the escape key is not so easy. By default, if we press the escape key while listening for an input, the Path field will close. Unfortunately, there isn't an easy fix for this. It's the default behavior of Unity. Hopefully, they will fix this problem in a future release. For now, we must manually search for the escape key. In the search bar, search for the Escape option. After finding it, select it from the list. Perfect. The actions have been successfully bound. What about the UI action map? In a future section, we're going to work on a UI system. Once we reach this section, we'll start binding keys to this action map. For now, it's fine to leave it empty. As for the move action from the gameplay action map, let's start working on it. After all, that's what this section is all about. In the next lecture, let's get into a discussion on composite bindings. In this lecture, we're going to work on the move action from the gameplay action map. Before we do, we must understand the concept of composite binding. Thus far, we've been using regular bindings. They're perfect for actions that require a single button press. But what if we need to support multiple button presses? For example, let's say we were developing a text application. Most modern text applications support copying and pasting. The most infamous keyboard shortcuts are Ctrl-C and Ctrl-V. Listening to a combination of key presses is common for application and game development. Unity refers to this feature as composite binding. They are bindings with two or more buttons for triggering an action. Best of all, we can make it optional to trigger an action with two buttons. But why would we want to use a composite binding? Let's imagine the player as a green circle. Similar to our game, this circle can move with the W, A, S, D keys. The W key moves them forward. The A key moves them left. The S key moves them backward. Lastly, the D will move them to the right. It's a traditional setup for a game. Players won't always move in these directions. They may want to move diagonally. For example, they may want to move with the W and A keys simultaneously. This key combination should move them in a diagonal direction. Without composite binding, creating this feature would be difficult. It wouldn't be impossible, but it can be a challenge to implement. Why go through the hassle when composite binding handles most of the work for us? Composite binding was created for scenarios like these. Let's try updating the move action. For the Input Actions window, select the Move action from the Gameplay action map. Next, set the Control Type field to Vector2. Before adding the bindings, we must specify the control type. The control type configures the type of value that will be produced by our binding. Composites are capable of producing vectors. If you're not familiar with vectors, they're a mathematical concept. We aren't going to dig deep into the definition. Just know that Unity uses vectors for the position of a game object. Once we start moving the player, you'll be able to get an idea of what a vector is. The Vector2 type is for moving objects on a 2D plane, whereas Vector3 types will move objects on a 3D plane. So why are we using Vector2? Let's head on over to our game. From the hierarchy, focus on the Player Placeholder Game object. The goal of this section is to move the player across the map. By the end of it, we should be able to move them across the X-axis and Z-axis. But what about their Y-axis? Unlike the other axes, players will not be able to move across this axis. Diving and jumping will not be featured in our game. Therefore, we don't need to produce a 3D value. It'll be easier to work with a 2D vector. Let's head back to the Input Action window. After setting the control type, click the plus button for the move action. As mentioned before, the first option will create a regular binding. The other options create different types of composite bindings. Unity provides us with templates to help us build custom composite bindings. In fact, it's common to create a composite binding for moving the player on a 2D plane. Select the Up, Down, Left, Right Composite option. Next, we can assign a name to our composite. Let's change the name of the composite to Keyboard. After doing so, we can start setting the paths for each binding. Let's quickly go through them. It's nothing we haven't done before. For the up binding, set the path field to the W key. Next, for the down binding, set the path field to the S key. Afterward, for the left binding, set the path field to the A key. Lastly, for the right binding, set the path field to the D key. Great! We've successfully added a composite binding to the move action. The rest of the settings can be left as is. We're finished with the actions for our game. It's time to start writing code. In the next lecture, let's begin moving the player with these actions. In this lecture, let's begin preparing the player. In our scene, we have a placeholder for a player. It's useful, but it's time to replace it with an actual 3D game object. Let's quickly create a player with Unity's 3D models. First, we should update the name of the game object. Set the name to player. It's not going to be a placeholder anymore. Next, change the icon to none. In a moment, we're going to add a real object. The icon won't be necessary anymore. In the transform component, reset the values. The player game object should be a prefab. Before converting it into a prefab, it's considered good practice to reset the transform properties. This will avoid weird behavior in our game. Time to create a 3D object. In the hierarchy, navigate to the Create menu. From this menu, select the 3D capsule option. Afterward, reset the transform component. Next, move the capsule game object into the player game object. Lastly, let's create a prefab from the player game object. To keep our project organized, create a new folder in the Assets directory called Characters. Drag the player object into this directory. Great! We've got a prefab. During this process, you may have had one question. Why are we using nested objects? Let's enter prefab edit mode for the player. The player has two game objects. The first game object has the minimum setup for an object. It's just an object with a transform component, whereas the child game object has the capsule mesh data. Wouldn't it make sense for the capsule to be the parent object? In the programming world, we have a principle known as separation of concerns. This principle is not specific to Unity or C#. We can apply it to any programming language or framework. In fact, we can apply this principle to the real world. Hospitals can employ hundreds of people. There are surgeons, nurses, techs, chefs, janitors, etc. Each person is given a specialized job. Not a single employee performs all jobs. You can apply this concept to almost any industry. Businesses will always assign specific responsibilities to each employee. This principle can be applied to programming. We may have hundreds of game objects and classes. The separation of concerns principle states that we should split our logic by responsibility. This principle keeps our code base clean and organized. Back to our prefab. How does this principle apply to our players? Our player is going to have dozens of components added to it. We need support for collision, movement, quests, combat, health, and so much more. If we were to assign the components to the capsule, this object would be responsible for everything. This can give us trouble. Let me give you an example. In my editor, I've created a new prefab. You do not need to repeat this process. This is purely for demonstration purposes. Unlike the other prefab, this prefab has a single game object, which is the capsule. Seems fine, right? Not so fast. In the future, we're going to swap the capsule with a different object. Let's give that a try. In the hierarchy, create a new 3D model. This time, let's use a cube. The cube is a child object of the capsule, but that's not what we want. The cube should replace the capsule. Unfortunately, Unity does not make this process easy. Child and parent objects from a prefab cannot be easily swapped. Therefore, we must disable the Mesh Renderer component on the capsule game object. This achieves the desired effect. Unfortunately, we're wasting resources. The parent game object must be active for the cube to render. At the same time, the mesh for the sphere is being loaded through the Mesh Filter component. While not being used, the data for rendering a capsule is being loaded in our game. We can use separation of concerns to avoid this scenario. By using an empty game object, the visual information of the player can be easily swapped. In most games, developers will use child objects to handle visual rendering. Parent objects are responsible for the logic of the prefab. If the child objects get replaced, the original behavior and logic for the prefab will remain the same. Thus, it'll be easier to upgrade a game object. This pattern does not need to be applied to all prefabs. For example, our tiles don't follow this pattern. Unlike the player, tiles will not require complex components, nor will we need to swap their visual information. They'll be simple compared to the player. Let's finish working on the prefab. While testing movement, the player should be facing the direction they're moving. At the moment, it's not easy to tell where the player is facing. We can use the Select tool to remind us. However, it would be nice if we could skip this tool. To resolve this issue, we can add another game object to act as the front face. In the hierarchy, enter the Create menu. Create a 3D game object called Cube. Next, let's move this cube to the front of the capsule. You may need to resize the cube during this process. It should be smaller than the capsule. As a reminder, the front side of an object is the direction of the blue arrow. To take this even further, let's change the cube's appearance. In the Project window, switch to the Materials folder. From this directory, create a new material. Set the name to Temporary Player Face. The albedo option will be set to a blue color. You can use whatever color you want. Next, drag the material onto the cube. Great, the player is ready. Let's switch back to the scene. The player may not be visible from the scene. This is because we've reset their position. Let's move the player to the original location, which is the bottom right corner of the map. The player should sit above the beach tiles. It doesn't have to be perfect. As long as they're slightly above the ground, that's good enough. In my opinion, the player is too large for the map. Let's quickly resize them. Head back into Prefab Edit mode. I'm going to resize the player's scale to 0.3. All scale fields should be set to this field. Be sure to modify the capsule, not the parent object. Since child objects are responsible for visual information, they should be affected by our scaling. Next, the cube may need to be rescaled and repositioned. I'm going to quickly adjust the cube again. These changes should create a smaller player. Let's head back to the scene. The player may be elevated off the ground. Let's adjust their position to be slightly above the ground. Lastly, the player is facing toward the cave. I'm going to rotate them slightly to the left. Rather than facing away from the camera, they can face to the left. Fantastic! The player is ready. In the next lecture, we can start writing a class to handle the actions from our game. In this lecture, we're going to create a class for handling the player's movement. We must create something called an event handler to receive the input from the controller. This begs the question, what's an event handler? To understand event handlers, we must discuss the idea of events. In the real world, we have events for all kinds of things. Birthdays, weddings, doctor appointments, and graduations can be considered events. During these events, we may behave differently than on a regular day. We may dress up or go out to eat as a celebration. Events in programs are similar. However, they're not as exciting. In some cases, we may not be interested in executing code immediately. Instead, we may want to wait for an event to occur before doing anything else. Events can be created from anything. For example, we may want to move the player when a button is pressed. Another example would be when the player is defeated. This leads us to event handlers. An event handler is a method responsible for performing logic during an event. There are two steps to dealing with events. First, we must create an event. Second, we must create an event handler. Luckily, by using the input system, events are created from our actions. We can skip this step entirely. Some of you want to create custom events. Don't worry, I got you covered. In a future section, custom events will be discussed. For now, let's let Unity handle event creation. The first step is to create a script. As always, we should dedicate a directory to our scripts. In the Assets directory, create a new folder called Scripts. Inside this folder, create a new C# script. The name of the file should be called Movement. Next, let's modify the script by double-clicking on it. This should open Visual Studio Code. Before moving on, make sure the class name matches the name of the file. If you rename the file after creating it, these names might not match. It's a common problem among students. It's always good practice to set the name while the file is being created. After confirming the names match, let's clean up our script. First, we're going to remove the inner contents of the movement class. We do not need the start or update methods. Next, at the top of the file, remove the using statements for the system namespace. Our editors can inform us when a namespace is not utilized from within a file. If the statements have darker shading than the rest of the file, this indicates that the namespaces can be safely removed. Great! The last step is to create a namespace. Above the class, create a namespace called rpg.character. For the rest of this course, we're going to be using the RPG namespace for all classes. Classes related to characters will be placed in the character namespace. Let's move the class inside the namespace. Our class is ready. Inside the class, define a method called handleMove. This method should have a return type of void. In addition, the accessibility should be public. Going forward, all methods should have a return type of void unless stated otherwise. As for accessibility, I'll let you know if a method should be public or private. In most cases, event handlers should be public. Events are primarily written from an external location. Therefore, the event handler may not be accessible if the event gets triggered. The name of the method is important to highlight. Event handlers should be easily identifiable. Throughout the course, we're going to be creating dozens of event handlers. We should be consistent with our naming. The name of the event handler should start with the word handle. This word should be followed by the name of the event. For example, if we had an event called click, the event handler's name should be called handleClick. These names are not mandatory. You can come up with any naming system you would like. Above all else, you should be consistent. Inside our method, let's print a message to the console. Call the print method with the following message: WASD keys pressed. To keep it simple, we're printing a message to the console. This will help us verify the method gets called during a key press. After ascertaining our method works, we'll replace the code with code for moving the player. We're almost finished. the method is ready. The next step is to add this script to the player. By doing so, the class will have access to the player's info. This includes their position. Therefore, this method will be able to move the player from their current position. Switch over to Unity. In the project window, search for the player prefab. Once you find it, enter Prefab Edit Mode. From the hierarchy, select the parent object. After doing so, add a new component. You should be able to find the movement component. Add it to the game object. Awesome! We've successfully created an event handler. It's been attached to the player. The next step is to inform Unity of our event handler. At the moment, Unity does not assume which events and event handlers are connected. We must manually create this connection. In the next lecture, we'll handle this step. In this lecture, we're going to create a new game object for managing the input system. Let's take a moment to think about this. In the scene, we have a player object with a component called movement. This component will handle the move event. The question is, where does the move event come from? The move event will never happen because the input action file is not in our scene. We've created a file with a complete list of actions. However, Unity does not automatically load this file into our game. We're responsible for loading it onto a game object. The question becomes, which game object? Technically, we could load it on the player object, but I don't think that would be efficient. In the future, we are going to create a menu system. Menus require a separate game object. Therefore, we must load the input action again on a different object. The more objects that require input from a controller, the more times we must load the input action file. Loading this file multiple times will not severely impact the game's performance. On the other hand, it may be annoying to search for where this file has been loaded. In my opinion, we should load this file once on a game manager. In Unity game development, there's a concept known as a manager. Managers are scripts or game objects responsible for controlling other game objects. Most of the time, a script should affect the game object it's attached to. In a few cases, a script may need to interact with a different game object. We refer to these types of scripts as managers. There are different types of managers you can create. Audio managers are popular in game development. Managers can keep track of the player's score. One last example would be creating a manager for tracking enemies on a map. The most popular type of manager is called a game manager. Game managers are thought of as the brain of a game. It manages the bigger picture stuff. There aren't any rules for what can be controlled by a game manager. For our game, we're going to use the game manager for loading the input actions file. Let's create a new game object. In the hierarchy, add a new game object. The name of the object should be called Game Manager. Next, let's reset the transform component. Resetting the transform data is optional. Unlike other projects, managers don't have to contain visual information. Its position is irrelevant. However, I like to reset the transform as good practice. It's a good habit to get into. Next, let's drag this object into the core folder to create a prefab. Great, we've created a game manager. In the next lecture, let's load the input actions file on this game object. In this lecture, it's time to load the input actions file into the scene. We have an object for storing this file's data called Game Manager. Let's enter Prefab Edit Mode for this prefab. Next, on the inspector, add a component called Player Input. This component becomes available after installing the Input System package. Its job is to load an input action file. Let's quickly review the settings. The first setting is the file. Let's click on the button to open a window for selecting an input action file. There should only be one file. Select it from the list. Great! It's as simple as that. We've successfully loaded this file. Let's continue configuring the options. The next option configures the default map. The component automatically finds a complete list of action maps from our file, which are called Gameplay and UI. Let's select the Gameplay action map. The next option is called UI Input Module. This option is for connecting the UI of our game to the file. However, UI is not a topic we'll cover in this section. It'll be covered later. For now, let's leave it empty. Up next, we have an option called Camera. If our game has multiple cameras, we may want to control a single camera with our actions. For our game, the camera won't be controllable through an action. We can safely leave this option empty. Moving forward, the last option configures the behavior of this component. This component is capable of informing our objects that an action has occurred. There are different ways of sending this information. Most of these options won't be covered. Our original goal was to use events. Select the Unity Events option. By selecting this option, the component creates events from our actions. Below the field, a new drop-down becomes available called Events. Taking a peek inside, a complete list of events is presented. We have events for handling device connectivity issues. In addition, events from our action maps are available. By default, the component will use the name of the action as the name of the event. If we have an action called Move, the event will be called Move. If we have an action called Attack, the event will be called Attack. So on and so forth. Let's exit Prefab Edit mode. Before adding event handlers to our events, we should do so from the scene. If we were to add event handlers from Prefab Edit mode, the game manager would expect these methods to exist in all scenes. Initially, that may seem like a good idea. After all, the player should be accessible for every scene in our game. But what if we create a cinematic? Not all scenes have to contain playable levels. You can create scenes to create cinematics in your game. Players should not be able to interact with an object while a cinematic is playing. Rather than adding handlers to the original copy, they should be added for each scene. The process is more manual, but safer than expecting the player to be movable in every scene. Select the Game Manager from the hierarchy. Open the complete list of events for the Gameplay action map. For this lecture, let's focus on the Move event. Click on the plus button. Here's the cool thing about events. A limitless number of event handlers can be attached to an event. We're not limited to a single event handler. That's great. This feature will help update multiple game objects from a single event. After adding an event handler, we can configure the settings for this handler. For example, we can run the method while the game is playing, which is called runtime. Alternatively, we can run the method while the game is playing or while we're editing the game. Lastly, we can disable an event handler. We may want to use this setting for debugging a specific handler. If we have multiple event handlers on a specific event, they can conflict with each other. We can pinpoint the problem by testing one event handler at a time. In most cases, you should always select runtime. From my experience, I have had issues with running methods while editing a script. It's safer to use runtime mode. Next, we can select a game object. Press the button to open a list of game objects. In the past, students have selected the wrong game object. There are two lists. Make sure the Scene tab is selected. Game objects from the Assets tab are not active game objects. If we were to add a game object from this tab, nothing would happen in our game. So, be sure to select Objects from the Scene tab. From this list, search for the Player Game object. Great! The last step is to call the method from this game object. In the dropdown, we are presented with a complete list of properties and methods available from the game object. If we have components, their info is exposed to us. This is why our event handler must be public. If our event handler was private, they might not appear in this list. Select the Handle Move from the Movement component. We're finished. Time to test our work. Hopefully, everything works. In the Unity editor, open the console window. If there are messages written in the console, clear them. Next, play the game by pressing the play button. If we were to press the WASD keys, the message from our event handler would get printed in the console. After almost an hour of work, we can capture the user's input. Before ending this lecture, there's one thing I want to mention. In the console window, reading duplicate messages can be annoying. It can be easier to read the console by pressing the Collapse button. This button will merge duplicate messages into a single log. The number of times a message has been logged is counted to the right. If we have a unique message, that will have a separate log. Throughout this course, I will toggle this feature on and off. Now that we've verified the player is receiving the input from a controller, we can start moving them around the map. In the next lecture, let's begin this process. In this lecture, we need to make a huge decision. Where can the player walk? In our game, we have two tile maps. Players should be able to walk on both tile maps. To get to the second tile map, there's a ramp for reaching this area. At the moment, Unity does not know which areas are walkable. We must update our map to have walkable areas. Typically, there are two features available for accomplishing the same thing. We can use physics or navigation meshes. If you've watched a YouTube tutorial or have taken another course, physics is the most common solution. I think it's a fantastic solution. If an object has a solid mass, players should be able to stand on the object. Alternatively, you can create obstacles with physics to prevent players from reaching specific areas on a map. The next feature is called the navigation mesh. Unlike the first solution, physics is not taken into account. Instead, Unity implements AI for detecting walkable areas. Both solutions are excellent. You can even combine both to create a smarter game. There are pros and cons to each feature. Physics can be unpredictable. One wrong setting can cause the player to fling around the map. However, it can be pretty powerful for creating an interactive game. Navigation meshes are predictable and reliable. However, they can be challenging to fine-tune. Getting the desired results can take a bit of work. By default, this feature is not available in new projects. We must install a package to start using it. Under the Window menu, open the Package Manager. Switch to the registry. Search for a package called AI Navigation. Go ahead with installing it. Awesome! The installation process is pretty straightforward. Let's begin using it. The first step to using it is to tell Unity which areas on our map are walkable. For our game, the beach and grass tile maps are going to be walkable. Under the Window menu, navigate to AI Navigation. There's going to be two options. Select the one that says Obsolete. We'll be using an older version of the navigation system. This option opens a window for configuring the AI. Let's merge this window with the inspector. There are 4 tabs available. The first tab is called Agents. These settings refer to the objects that can move on the map. An example would be the player. The next tab is called Areas. These are a list of colors that will be applied to our map. Unity can show us which areas are walkable or non-walkable. It's a handy feature for helping us adjust the map. The third tab is called Bake. We're going to skip these settings. We'll revisit them in a moment. Moving on, the last tab is called Object. These settings allow us to adjust the settings for objects other than the agent. The main focus of this lecture will be the Bake tab. In the real world, baking is the process of cooking food with heat. However, there's more to it than that. When you bake something, you're typically baking multiple ingredients. For example, you may be baking cookies with chocolate chips. Before baking cookies, you combine the dough with chocolate chips. Neither ingredients are thoroughly ingrained with one another. I can freely remove or add chocolate chips. Once I start baking, there's no turning back. The dough and chocolate chips are baked together to create a new flavor profile. This idea of baking applies to 3D modeling. If you ever take a 3D modeling course, you will often come across this term. The idea of baking in modeling refers to transferring details from one 3D model to another 3D model. As a result, you'll be given a single 3D model with information from the original models. As we know, all 3D objects have a mesh. As a reminder, meshes describe the vertices, edges, and faces of a model. In our game, the tiles and player are created from meshes. Unity is capable of creating meshes on the fly. The navigation feature can draw a mesh. However, this mesh is not meant to be a standalone object. Instead, Unity will try to bake this mesh into our game. Under the Bake tab, we have options for modifying the baking process. Without modifying these settings, let's try baking the mesh. Press the Bake button. After doing so, nothing happens. Why not? Before we can bake an object, we must allow it to be bakeable. Otherwise, all objects would have an unnecessary mesh. Navigate to the Tiles folder. Enter Prefab Edit mode for the beach tile. Next, select the object from the hierarchy. After doing so, switch to the Object tab from the navigation window. Under this tab, we can modify the object's mesh to allow baking. If an object does not have the Mesh Renderer component, these settings may not be available. Let's check the Navigation Static field. If turned on, we're telling the AI that this object can be baked. The baking can be refined further. The Area field can be changed to Walkable, Non-Walkable, or Jump. If the option is set to Walkable, the player will be able to walk on the object. The Non-Walkable option prevents the player from walking on the object. Lastly, the Jump option allows an area to be jumped over. Let's set this option to Walkable. Next, let's exit Prefab Edit mode. Back in the navigation window, switch to the Bake tab. Press the Bake button. This time, things are different. Using AI, Unity was able to draw a mesh over our tiles. During this process, it baked the new mesh with the current mesh for the tiles. The areas drawn in blue are walkable. If the navigation mesh is not visible, you can turn on the mesh by updating the settings in the Scene window. At the bottom right corner, there's a mini window called Nav Mesh. There's an option for toggling the visibility of the navigation mesh. This window is only available when the navigation window is active. Enable this option to view the navigation mesh. Let's work on the other tiles. The process is the exact same. The following tiles will be walkable: Ground Grass Slope Tile and Ground Grass Tile. I'm going to quickly set their mesh to be walkable. Let's go through them. First, enter Prefab Edit mode for the Ground Grass Slope Tile object. Under the Object tab, turn on the Static option and set the Area option to Walkable. Next, let's do the same for the Ground Grass Tile object. During this process, Unity notices that this object has child objects. Previously, we added flowers and grass to the ground. In some cases, you may want the AI to take these objects into consideration. For our game, the child objects will not be static. Next, set the area field to walkable. Lastly, let's rebake the navigation mesh. Be sure to exit Prefab Edit Mode. Under the Bake tab, click the Bake button. The second Tilemap has been baked. However, not everything is perfect. There are a few noticeable problems. Firstly, the ramp is not walkable. Despite being configured to be walkable, the AI has decided it's not walkable. In addition, the cave is not walkable either. Players should be able to move slightly inside the cave entrance. These issues stem from the current configuration. We must adjust the settings of the agent to receive better results. In the next lecture, let's begin tweaking the settings. In this lecture, let's fix the issues with the current navigation mesh. Currently, I'm looking at the slope. These areas around the slope are walkable. However, the AI has decided the slope is not walkable. We can make this area walkable by adjusting the agent settings. In the navigation window, switch to the Bake tab. Under this tab, before baking the mesh, we can configure the size of our agents. This helps AI understand the size of our characters. Specifically, the settings for this section should resemble the player's size. We are given a diagram to help us visualize how our settings affect the AI's understanding of our character. Let's go through these settings. The first setting is the agent's radius. By default, Unity visualizes our player as a cylinder. The radius of the cylinder is based on this setting. In an earlier lecture, the size of our capsule was resized to 0.3. If we were to attempt to calculate the radius of our capsule, it would be 0.15. It's half the size of the capsule's scale. Currently, the radius is too big for the slope. Let's set this option to 0.15. Next, let's try baking the mesh again. After a few moments, the mesh should allow the player to walk on the slope, but it's not perfect. The slope is too steep. Let's keep configuring the settings. The next setting is called Agent Height. As the name suggests, we can change the height of our players. This setting will not affect the slope. However, it will affect the cave entrance. Let's zoom in on the cave. Looking closely at the navigation mesh, it's not going to allow agents to enter the cave. The reason has to do with their height. The height of our cave is 1 unit, whereas the height of the agent is 2 units. Our capsule has a height of 0.3. Let's change the agent height setting to 0.3. Next, rebake the map. This time, the navigation mesh has been baked into the cave. Perfect. Let's head back to the slope. The next setting is called Max Slope. This setting refers to the slope of any object that's not the agent. If a tile is walkable but has a slope, this setting will affect that area of the map. Let's change the angle to 50 degrees. I arrived at this setting through trial and error. You can try experimenting with this value to find a more accurate value. Before baking the scene, let's discuss the last setting called Step Height. If our game has stairs, players should be able to walk on them. Unlike slopes, stairs have angles of 90 degrees. Therefore, the slope setting will not be applicable to stairs. We can allow players to walk on stairs by setting this option. It's how a player can walk on stairs. Unity may throw an error at us. The step height may not be higher than the height of the agent. Let's change this setting to 0.3 to match the height. Lastly, let's bake the scene. Voila! The navigation mesh has been applied to the slope. We're finished configuring the settings. Feel free to adjust the settings. Your values should match mine. If the navigation mesh isn't working, you may need to adjust the values suitable for your game. There are 2 extra sections in the Bake tab. The first section is called Generated Off-Mesh Links. These settings configure the mesh to allow players to jump over large distances. Our game won't allow players to jump. We do not need to configure these settings. The last section contains advanced settings. Once again, configuring these settings is not going to be covered in this course. In most cases, you shouldn't have to configure them. In the next lecture, let's make some final adjustments to the terrain. In this lecture, we're going to finish working on the navigation mesh by creating non-walkable areas. There's one problem with our current mesh. Let's look at the edges of the grass tile map. The navigation mesh appears under the edges of the ground. Since that's the case, players can walk through the walls. Here's what I love about the navigation mesh. We are given visual information on walkable areas. Spotting errors like these are easy to catch. For demonstration purposes, I'm going to move the player near the wall. As you can see, the player is still on the navigation mesh. However, they're slightly entering the walls. We should inform the AI that these tiles are non-walkable. In the project window, navigate to the Tiles folder. Open the Ground Grass Edge Tile Game object in Prefab Edit mode. Next, select the game object from the hierarchy. In the navigation window, under the Object tab, the settings for the object should appear. Same as before, we can turn on the Static option to configure the object. Next, under the Area field, we can select Non-Walkable. The Non-Walkable option forces the AI to avoid this object. When the mesh is drawn, the agent will not be able to walk through or on this object. Let's exit Prefab Edit mode. Next, try baking the map again. This time, the navigation mesh has avoided the edge. Therefore, players shouldn't be able to walk through the walls. That's perfect. Let's do the same for the other non-walkable tiles. In our project, we have two tiles called Ground Grass Corner Tile and Stone Grass Tile. As an exercise, update the settings of these objects to be non-walkable. Repeat the same steps as before. Pause the video and good luck. Welcome back. Hopefully, you were able to make these objects non-walkable. If not, let's go through the steps together. We'll start with the Ground Grass Corner Tile object. Enter Prefab Edit mode for this object. Under the Object settings, turn on the Static option. Next, set the Area option to Non-Walkable. This object is ready. Let's work on the Stone Grass Tile object. Switch to Prefab Edit mode for this object. Same as before, set the Static option to On and set the Area option to Non-Walkable. The last step is to bake the navigation mesh. It does not automatically get updated. We must always bake the mesh to get updated results. Head back to the scene. Under the navigation window, switch to the Bake tab. Click the Bake button to bake the navigation mesh one last time. After making those adjustments, we can move around the scene to verify the navigation mesh has been applied. As you can see, the corners and stone tiles have been updated to be non-walkable. It's exactly what we wanted. In the next lecture, let's begin updating the player to move around this mesh. In this lecture, let's update the player to be an agent. An agent refers to an object that can move around the navigation mesh. By default, Unity does not assume which objects are agents. We must manually assign agents. Currently, we have one object that should be an agent, which is the player. In the Characters directory, open the Player object with Prefab Edit mode. Next, select the Parent object. An object can be updated to be an agent by adding a component. As we discussed before, The parent object should be responsible for the logic of our prefab. Child objects should be responsible for visual information. Therefore, be sure not to apply this component to the wrong object. Click the Add Component button. Search for a component called Nav Mesh Agent. Add it to the object. Next, move the component above the movement component. You can do so by dragging the component by its name. This step is entirely optional. The order of your components does not affect the behavior of the game object. Reordering components is a feature for keeping your object's components organized. I prefer to position Unity components at the top. Custom components should appear at the bottom. It's easier to search for components with this structure. Let's modify the settings of the Navigation Mesh Agent component. Specifically, we're going to alter the speed settings of the agent. There's a section called Steering. Under this section, the speed setting should be set to 3. This setting determines the speed of the agent. The speed is measured in Unity units. The lower the number, the slower the speed. Keep in mind, the size of our tiles is 1 unit. Therefore, the player will be able to move over 3 tiles per second. Feel free to adjust this speed after completing this section. Next, let's adjust the angular speed setting. This setting configures the speed of the agent's rotation. Our player shouldn't rotate fast. For this game, let's use 6. Lastly, update the acceleration to 4. This setting configures the player's acceleration once they begin and stop moving. Smooth movement is preferred over abrupt steering. Let's move on to the other settings. If we look at the scene, a green outline has appeared around the player. You may not be able to see it with the scene in the background. I recommend editing the player while the objects are isolated from the scene. It'll be easier to view the outline. This green outline will be invisible to the player. The purpose of this outline is to help Unity detect collisions with other agents or obstacles. As you can see, the outline is larger than the game object. We should adjust this outline to be slightly larger than the player. Notice how I said larger and not exact. If the outline is exact, the agent may overlap with other objects. That wouldn't look good. Creating a larger outline can help with overlapping objects. We can use the settings to adjust the outline. First, let's move the outline under the player. Let's adjust the camera to look below the player. The outline is drawn from the center of the player, which isn't what we want. It should be slightly below the player. We can adjust the base by updating the base offset field. Let's set this option to around 0.3. The numbers don't have to be perfect. As long as you get close enough, you're good to go. Next, there's a section called Obstacle Avoidance. Under this section, we can refine the shape of the outline. Let's set the radius to 0.3. Like I said before, the outline should be larger than the actual size of the object. Preventing objects from getting too close to each other is an important feature to consider. Lastly, set the height to 0.6. After making those changes, the outline looks better. Feel free to adjust the outline as you see fit. For now, these settings will work. Other than these settings, everything can be left as is. Once the script is finished, you'll be able to fine-tune these settings to customize the behavior of our agents. In the next lecture, let's begin finishing the code for moving the player. In this lecture, let's update our method to receive data created by the event. Our event handler does not have any information regarding the button pressed by the player. We must have access to this information before performing any action. Otherwise, we won't have any idea where to move the player. Unity gives us a hint as to how we can retrieve this information. In the Unity editor, select the Game Manager object. Under the inspector, search for the Move event. Looking closely at the name, there's a pair of parentheses. this information provides a hint. Unity is telling us that our event handlers can have a parameter called Callback context. The question is, what's the type of this parameter? In the resource section of this lecture, I provide a link to the documentation page for this parameter. So far, parameters have been annotated with simple data types, such as strings or integers. C# allows developers to create custom types. It's a widespread practice. Unity has a custom type for storing the information related to the button pressed by the player. It's called Callback context. Initially, the information on this page will feel overwhelming. There are a lot of concepts we haven't had the chance to go over. Let's focus on the most critical sections related to our goal. Before we can add the parameter, we must have a reference to this type. As usual, we need to know the namespace. Luckily, the namespace is written on the breadcrumb navigation. The namespace for a type will always appear as the second item on the navigation. In this case, the namespace is called Unity Engine.InputSystem. You can verify the namespace by clicking on the link. As you can see, the documentation has marked this name as the namespace. Great! In our text editors, open the movement file. At the top of the file, add the Unity Engine.InputSystem namespace with the using keyword. Next, in the handleMove method, add the InputAction.CallbackContext type. From here, we can assign a name to the parameter. Let's set the name to context. Taking these steps is important. If we were to use an incorrect type, our program wouldn't be functional. In the next lecture, let's use this information for storing the movement of the player. In this lecture, let's store the player's movement. The input system has no idea where a player is. They can be anywhere on the map. Therefore, it doesn't calculate a new position for the player based on their current location. Instead, the information sent by the event will contain a direction. If the input system says to move forward, we'll move the player forward from their current position. If they should move to the left, we'll move the player left. Therefore, the first step in our journey is to grab the direction. This information can be found within the context parameter. Let's remove the print method from the handleMove method. It's not necessary to keep it around. Next, run a method called context.readValue. The readValue method will grab the direction indicated by the controller. The great thing about the input system is that it'll return this information in any format we want. We can specify the format by adding a generic. Let's set the generic to vector2. In an earlier lecture, we briefly got into a discussion on vectors. Vectors are a mathematical concept. Luckily, it's not necessary to be a mathematician to understand vectors. At the end of the day, Unity uses vectors to store the position of a game object. There are two types of vectors, which are vector2 and vector3. A vector2 contains coordinates for objects on a 2D plane. Typically, developers use this type for 2D games. Vector2 contains the x and y coordinates of an object. As for vector3, this type is normally used with 3D games. It stores the x, y, and z positions of an object. Similar to the callback context type, these types are defined by Unity. It can be found under the Unity Engine namespace. You can hover your mouse over the type for the full path. Fortunately, we're already referencing this namespace from within our script. We're using vector2 because the player will be moving around a flat surface. They will not be jumping. Let's store this information in a variable. Before running the method, create a variable called input with the vector2 type. The type returned by the method will always be the type of the generic. The next step is to convert the value from a vector2 to a vector3. Sounds strange, right? If we wanted a vector for a 3D space, why don't we update the action to send us a vector3 value? The reason is simple. We don't have bindings for moving the player up or down. Therefore, creating a vector3 would require additional bindings, which we don't have. As a result, we must convert the type from vector2 to vector3. This process is relatively simple. At the top of the class, define a new private variable called movementVector with a type of vector3. At the moment, the variables are local to the method. They won't be accessible outside the method, which can be a problem. In a future lecture, we're going to rotate the player toward the direction they're moving toward. If this information is not accessible to the entire class, this task would be impossible. Storing the player's direction in a variable exposed to the entire class will be easier to work with. Back in the handleMove method, set the movement vector variable to the following value: new vector3 input.x, 0 input.y. A new vector can be created by using the new keyword. This keyword is followed by the type of data we'd like to create. In this case, it's a new vector. Inside the parentheses, we're configuring the initial values of the vector. There are 3 values that we must provide. They're the x, y, and z coordinates. In this example, we're using the input variable to access the x and y coordinates from the vector2 object. The x property is mapped to the x coordinates. The y property is mapped to the z coordinates. Keep in mind, the y coordinate moves the player up and down. Since we're not going to allow the player to jump, they will remain on the ground. We can set the y coordinate to 0. Instead of mapping the y property to the y coordinates, we're mapping it to the z coordinates. Before testing our code, let's log the new vector. At the bottom of the method, call the print method with the movement vector variable. We're not limited to logging strings or numbers. Almost anything can be logged. In this case, we're logging the direction. Let's head back to Unity. Next, switch to the console window. After doing so, play the game. If we were to press buttons on our keyboard, nothing would happen. Why not? Surprisingly, by updating the method's parameters, Unity no longer recognizes it. Let's exit play mode. Next, select the Game Manager object from the hierarchy. Search for the move event from the inspector. According to the editor, the handleMove method is missing. However, our script does have this method. The reason we're receiving this error has to do with our updates. By updating the parameters, Unity thinks we've created an entirely new method. Previously, the method didn't have parameters. It's expecting to find the method without the parameters. To fix this issue, we simply must update the event to use our new handleMove method. Let's quickly update this event. After making those changes, let's play the game. This time, the direction gets logged in the console. We can press a single key or a combination of keys to get a new direction. If we release a key, the vectors get reset to 0, 0, 0. This value indicates that the player should not be moving in any direction. That's going to be helpful later down the line. In the next lecture, let's use this information to move the player in the desired direction. In this lecture, the goal is to grab the agent component. I'm looking at the player game object. On this object, we added the navigation mesh agent component. As we have learned so far, the navigation mesh agent component will be responsible for moving the player around the map. It'll help us detect collisions, thus preventing our player from moving into an invalid area. Technically, we could move the player without this component. However, this component works alongside the navigation mesh baked into our map. If the player attempts to move outside the map, The agent component prevents that from happening. Therefore, we should use this component to move the player instead of an alternative solution. To get started, we must grab the agent component from our script. In the resource section of this lecture, I provide a link to a class called Navigation Mesh Agent. All components are classes. Just like our class, Unity's classes have variables and methods. You can view a complete list by checking the documentation for the respective component. If we can grab a copy of the component attached to the game object, we'll be able to move the object. So, that's the goal of this lecture. We're going to grab the agent component attached to the object with our movement script. Before we can use this class, we must check the namespace. At the top of the documentation page, Unity provides the name of the namespace. It states the following: class in unityengine.ai. You can always verify the namespace of a class by looking directly under the name of the class. Unity will always provide the namespace. With this information, let's get started. Open the movement file with Visual Studio Code. At the top of the file, add the unityengine.ai namespace. Next, at the top of the class, add a new private variable called agent. The type for this variable will be navMeshAgent. Classes are allowed to be used as types for variables. That's a neat feature of C#. If we're grabbing a component, we'll always use the class that creates the component as the type. You may wonder, why aren't we setting the variable to the component? The reason is simple. We should wait for the game object to be ready. In the resource section of this lecture, I provide a link to a documentation page for an object's execution order. Unity goes through a process to create game objects in a scene. It'll execute a series of methods from our class. If we scroll through this page, we're given a diagram of these methods. The first method is called awake. This method is followed by the onEnable method, so on and so forth. Unity calls these methods from our component. You can read through the documentation to learn when a method is called. There are dozens of methods. Luckily, you don't need to memorize all of them. In most cases, you'll be using a handful of them. While the game is initializing, it's possible that we may grab a component too early. If we were to grab the component too early, we might receive an error. We should wait for the game object to be ready. Once it's ready, all components will be available. Let's head back to the editor. At the top of the class, define a private method called awake. The name matters a lot. Unity's methods are always Pascal case. If we define this method, Unity will automatically call it after a game object has been created. Inside this method, we should update the agent variable with a copy of the navigation mesh agent component. Set the agent component to the following value: get component nav mesh agent. The get component method is available through the monoBehavior class. Unity defines this method to help us grab other components from the same game object. We must specify the name of the component by using a generic. In this generic, we're selecting the navigation mesh agent component. This method will return the component's data. By grabbing the component, we can begin moving the player. In the next lecture, let's begin moving the agent through the agent component. In this lecture, let's move the player with the agent component. So far, we have access to this component. If you were to look through the documentation, there's a method for moving the agent called move. Currently, I'm viewing the documentation for this method. According to the documentation, this method will move the agent from its current location. The most important piece of information is the parameters section. Under this section, we can pass in values to customize the behavior of the method. There's one parameter, which is a vector 3. We must provide this method with an offset for moving the agent. Luckily, we happen to have such a value. Let's open the movement file. Below the awake method, define a private method called update. The update method is another lifecycle method. It's similar to the awake method. Unity automatically calls this method. So, what's the difference? The awake method gets called once, which is upon the creation of the game object. The update method gets called on every frame. For example, let's say the player's monitor rate is 60 FPS. This method would get called 60 times a second, so on and so forth. But why are we using this method? Players should move smoothly. If we were to update their position in a single frame, the movement would look awkward. Movement should be incremental. For this reason, Unity adds the update method to help us create smooth movements. Inside this method, run a method called movePlayer. We're going to outsource the logic for moving the player in a different method. Technically, we could define the logic from this method. However, it'll be cleaner to split our code into methods. Let's define this method below the update method. It'll be private. Inside the movePlayer method, call the agent.move method with the movement vector variable. Let's quickly discuss what will happen. The move method will move the player from their current position based on the offset passed in. The player's position is saved as a vector 3. For example, let's say the current position of the player is 10 on all axes. Next, our offset is the movement vector variable. For this example, the vector is 1, 0, 0. The move method handles adding both vectors together. The new position becomes 11, 10, 10. However, there's more to it than that. The move method performs additional checks. Firstly, it'll calculate the new position. Before moving the game object, it'll verify that the new position is within the bounds of the navigation mesh. If it is, the object is moved to the new position. Otherwise, the new position is rejected. By using the navigation components, we can avoid performing these checks ourselves. Let's try testing our work. In the Unity editor, let's dock the game and scene windows side by side. Currently, we're not able to view the player with the game's camera. In a future lecture, we'll update the camera to follow the player. For now, we must view the player's movement through the scene window. Let's press play. As we press the WASD keys, the player is moving. We move left, right, forward, backward, and even diagonally. Thanks to the AI, we're not able to move outside the map. If we were to bump into walls, the player cannot move past them. That's great. Admittedly, the speed is extremely fast. That can be fixed with additional code. If we look at the console, the movement vector variable continues to be logged. I'm going to quickly clear the console. Next, I'm going to move right without releasing the key. In the console, the movement vector variable has been updated to 1, 0, 0. While it's set to this value, the move method constantly attempts to move the player. The moment I release the key, the vector gets reset to 0, 0, 0. But why? The input system will automatically reset the vector after the key has been pressed. This behavior works in our favor. We want the vector to be reset. Otherwise, the player will constantly be moving. Once the vector is reset, the move method will not move the player since the vector is 0. Everything works beautifully. In the next set of lectures, let's begin refining the solution by following the player with the camera and slowing the player's speed. In this lecture, we're going to follow the player's movement with the camera. There are two solutions for implementing this behavior. We can program the camera to follow the player. Alternatively, we could install Cinematic Machine. Cinematic Machine is a package by Unity for creating powerful cameras. Unlike the input system, the cinematic machine feature enhances the current camera. It's not a replacement. The current camera doesn't have many features for controlling it. If we want special behavior, we must program it. By using the cinematic machine package, we can avoid writing code. There are dozens of benefits to using cinematic machine. We can create cinematics, avoid objects from blocking the player, add multiple cameras, etc. It's an extremely powerful package. Like all packages, we must install it. Under the Window menu, open the Package Manager. Select the Unity registry. Next, search for a package called Cinemachine. Lastly, install it. After installation, we can begin creating a new camera. Currently, the camera in our game is using the basic camera. We should update it to use a cinematic machine camera. Before we do, let's organize our cameras. In the future, we're going to create cinematics with multiple cameras. At the moment, our cameras will become scattered throughout the hierarchy. To keep our project organized, let's create a game object to store all our cameras. In the hierarchy, create an empty game object. The name of this object will be called Cameras. Next, reset the transform component for this object. Afterward, select the main camera object. This object contains the original camera. Before moving it as a child of the Cameras object, let's reset its transform data. Move it into the Cameras object. Great, the cameras are ready. The next step is to create a virtual camera. Open the Create menu again. This time, navigate to the Cinemachine submenu. These options became available after installing Cinematic Machine. Cinematic Machine offers different types of cameras. We're going to select the Virtual Camera option. Set the name of the new object to CM Player. A few things will change in our game. Before breaking it down, let's move the object into the Cameras object. Let's go through the changes one by one. Firstly, we're creating a virtual camera. Virtual cameras are the most basic cameras offered by Cinematic Machine. It's very similar to the regular camera. We can view the world of our game through this camera. For the camera's name, it's common practice to prefix the name with CM. This naming convention helps other developers identify virtual cameras. The camera we've created will follow the player. After adding this object, Unity updated the main camera object as indicated by the icon next to the name. Let's take a look at this game object. The original camera has been updated to be the brain for the Cinematic Machine virtual cameras. As stated before, it's possible to have multiple cameras in the game. Unity has no idea which camera should be prioritized. The purpose of a Cinematic Machine brain is to decide which camera should be the main virtual camera. Our new virtual camera has been set as the default camera. If we look at the game window, the game camera has been updated to view our world. Let's move the virtual camera. With the Select tool, you can move the camera to look at the player. Make sure you're moving the virtual camera and not the original camera. This process works, but there's a shortcut to getting the camera in an accurate position. Instead of moving the camera with the Move tool, we can focus the scene's camera to look at the player. I'm going to look at the player from a tilted angle. After finding a decent position, select the Virtual Camera object from the hierarchy. Next, under the Game Object menu, select the option called Align with View. This option will cause an object to have the same position and orientation as the scene's camera. After selecting this option, the game window was updated with a similar view. From here, we can refine the results. Under the Transform component, let's update the rotation. I'm not a fan of the rotation from the scene. Let's set the X rotation to 45. Next, set the Y and Z rotation to 0. These adjustments may cause the camera to not look at the player. You can freely adjust the camera with the Select tool like so. Great! I'm happy with this result. The last step is to tell the virtual camera to follow the player. Initially, the camera will be looking at the player. However, if the player moves off camera, the camera will not follow them. On this game object, a component called Virtual Camera has been added. Under the settings, there's a field called Follow. We can update this option to specify an object to follow. Let's click the button to select the player. In the search field, search for the player object. Make sure you're searching for the game object from the scene. If you were to select the player object from the Assets tab, the camera would become confused. It can only follow objects that are active in the scene. After finding the player, select it. Next, the camera may have lost focus of the player. That's perfectly fine. We can fix this issue by updating the body option. The body option will configure the algorithm of the camera for following an object. Change this option to Framing Transposer. The Framing Transposer option will draw a box with a yellow dot in the center. The yellow dot will stick to the center of the object it's following. If the player moves around the box, the algorithm attempts to realign the yellow dot with the object it's following, thus moving the camera. However, this may put the camera in an unfavorable position. Once again, we may need to adjust the distance with the Select tool. I'm going to do so quickly. It's time to test our work. Press the play button. If we move the player, the camera follows along. That's awesome. Unfortunately, the camera may have a hard time keeping up as the player is too fast. That'll be fixed in an upcoming lecture. As long as the camera is following the player, we're good to go. Without writing a single line of code, we were able to get this behavior. We haven't had the opportunity to explore the endless options offered by the Cinematic Machine package. Don't worry, once we get into creating cinematics, more options will be covered. In the next lecture, let's begin modifying the speed of the agent. In this lecture, we're going to fix the speed of the player. They're moving way too fast for our game. In addition, there's another problem that isn't completely obvious. To understand the second problem, we should talk about frame rate. I'm assuming most of you know the basic concept of frames in games. A frame is a single image drawn on the screen. PCs can draw dozens of frames within a single second. We refer to the measurement as frames per second, or FPS for short. Our script is moving the player on each frame. Every time a frame is drawn, the player moves 1 unit from their current position. Believe it or not, this is considered bad practice. Let's try playing our game to find out why. First, let's merge the game window with the scene window. It isn't necessary to keep them separated anymore. Next, play the game. At the top right corner, there's a button called Stats. Click on it. This button opens a window with the game's current FPS. As you can see, my FPS is very high. Let's say one player has an FPS of 100. Players will be able to move 100 units each second. But what if a player had 30 FPS? They would be able to move 30 units each second. See the problem? Players with better systems will be able to move faster than players with low-end systems. If our game had multiplayer features, there would be an unfair advantage. Our game is considered to be frame rate dependent. Frame rate dependence occurs when calculations are executed without tracking time. By relying on frame rate alone, players will experience inconsistent movement. A better solution would be to rely on time. For example, if the player is moving, they should only be able to move a specific distance each second. Calculating a position based on time provides consistent experience. The question is, how? Unity has a variable called time.deltaTime. This variable stores the time it took for one frame to be drawn. Let's look at an example. If we have a player with an FPS of 4, it takes 0.25 seconds to draw a frame. For every second, 4 frames are drawn. This is an incredibly low frame rate, but for the sake of simplicity, let's use this example. Another player may have an FPS of 2. For every second, 2 frames are drawn. It takes half a second for a frame to be drawn. By using this variable, we can accurately move the player by time. For example, let's say the goal was to move an object 1 unit per second. We can multiply the speed by this variable. In this example, by multiplying the current distance by the time, we'll always produce consistent results. It doesn't matter if one player has a better system than another player. Both players will always arrive at their destination within the same time frame. Fixing our problem is easy. We must multiply the current vector by the time. Open the movement script. Inside the movePlayer method, create a variable called offset with the vector3 type. Set this variable to the following: movement vector times time.deltaTime. If you were to hover your mouse over the deltaTime variable, the variable has a type of float. However, the movement vector has a different type. Regardless, Unity has designed vectors to support basic arithmetic operations. We can add, subtract, divide, and multiply vectors with floats or integers. It's a convenient feature of Unity. After creating this variable, replace the value passed into the move method with our variable. Next, head back to Unity. Let's play the game again. This time, the agent is moving slower. They're moving 1 unit per second. By default, the input system will move objects by 1 unit. While this is an improvement, the player has become too slow. In the next lecture, let's finalize the speed by applying the agent's speed. In this lecture, we're going to update the speed of the agent with a value from the agent component. During the setup of our game, we attached the navigation mesh agent component to the player object. Under the component settings, there's a setting called speed. This setting does not get applied by the move method. For this reason, the player is moving slowly. We must manually apply the speed to the vector before passing it into the method. Luckily, this process is extremely easy. Let's open the movement file. Similar to the move method, the values from the component settings are accessible via the class. Since we're already grabbing the component, we can apply the speed to our offsets. In the handleMove method, update the offset variable by multiplying the value with the agent.speed variable. You can refer to the documentation for a complete list of properties/variables available from a given class. With this single modification, the player should move faster. Let's head back to Unity. Try playing the game. The speed of the player has improved. Overall, I'm happy with this speed. Here's the cool thing about Unity. Since we're using the speed from the agent component, we can modify the value from the editor while the game is playing. For example, I'll lower the speed. Next, if I were to play the game, the player moves significantly slower. Vice versa, we can increase the speed. This time, the player moves faster than before. This feature is incredibly invaluable. If we're working with a game designer, they'll be able to tweak the speed without looking at our code. Allowing others to modify values from the Unity editor can improve collaboration and development experience. Before ending this lecture, let's head back to the text editor. I'm going to remove the print statement from the handle move method. We're finished with moving the player. It's time to start rotating them. In the next lecture, let's begin this process. In this lecture, let's start rotating the player. At the moment, the player never rotates in the direction they're moving. They're always looking in the same direction. We must manually rotate an object. Performing this action will require understanding quaternions. If vectors are used for representing the position of an object, quaternions are used for representing the rotation of an object. The x, y, and z rotations are stored in quaternions. If we're interested in modifying an object's rotation, we must create a quaternion. Similar to before, we don't need to be experts in mathematics. Unity handles most of the complexities. As long as we supply the values, Unity handles the rest. Let's take a moment to think about this. The rotation should be smooth instead of abrupt. Otherwise, the rotation would look awkward. For this reason, we should rotate the player from the update method, which gets called on every frame. Open the movement script. Inside the update method, run a method called rotate. This method does not exist in our class. Let's define it. At the bottom of the class, define it as a private method. Technically, we could have written the code from the update method. However, to keep our class organized, we're going to outsource the code for rotating the object in a separate method. It's the same reason we outsourced the player's movement in a separate method. Not required, but recommended. Inside this method, we need two pieces of information. Firstly, we need the starting rotation. This value would be the current rotation of the object. We must know where the current rotation is to smoothly rotate the game object to the end rotation. Define a variable called start rotation with the quaternion type. This type is available via the Unity Engine namespace. We can start using it right away. The value for this variable will be the transform.rotation variable. The transform object stores a reference to the transform component on an object. Hold on a moment. Shouldn't we grab this component before using its values? The transform component is an exception to the rule. The MonoBehavior class automatically grabs the component for you. It's available as a property. We can start using its value straight away. For any other component, we must use the getComponent method. We can grab the rotation via this component. The next step is to store the end rotation, which is the final rotation of the game object. Define another quaternion variable called end rotation. The value for this variable will be the following: quaternion.lookRotation. The only information at our disposal is the movement vector. However, we need a quaternion, not a vector. Luckily, the lookRotation method can calculate a quaternion value based on a vector. It'll attempt to determine the best rotation based on the vector value passed in. Let's pass in the movement vector variable. Great! We have starting and end rotations. The next step is to smoothly transition between rotations. In the next lecture, let's keep working on the method. In this lecture, we're going to fix an issue with the rotate method. We didn't have a chance to play the game because we hadn't finished the method. However, there's already a problem with our variables. To find out why, let's try running the game. Without doing anything, the console spits hundreds of messages. The messages state the following: look rotation viewing vector is 0. This error stems from the lookRotation method. Open the movement script. In the rotate method, we're passing in the movement vector variable into the look rotation method. Vectors passed into this method must not have coordinates with all zeros. These types of vectors are referred to as vector zeros. By default, the movement vector variable will be a vector 0. Therefore, this causes the look rotation method to throw an error. To resolve these issues, we must check the vector before creating the rotation. Keep in mind, this method is constantly being called on every frame. Therefore, the game attempts to rotate the player on each frame. If the player isn't moving, they shouldn't be rotating either. At the top of the method, add a conditional statement. The condition will be the following: movement vector equals vector 3.0. The condition checks if the vector is equal to vector 3.0. This variable is created by Unity. Rather than creating a new vector, we can reuse Unity's variables. Checking for a vector 0 is a common action performed by developers. If the vector contains zeros, we're going to return the method. There are two things worth noting. Firstly, we're not wrapping the body of the condition with curly brackets. If the body of a conditional statement is one line of code, we're allowed to write it on the same line as the if statement. Secondly, the return statement does not include a return value. Our method has a return type of void. If the return type is void, the method cannot return a value. However, we're trying to end the method from running further. By returning a value, code written after the return statement will not be executed. To get around this, we can exclude a value, which is the same as returning a void value. This line of code should prevent the rest of the method from running when the player is not moving. Let's try testing our code. Switch over to Unity. Try playing the game with a clear console. The errors have gone away. It doesn't matter if we're moving or not. The look rotation method is happy. In the next lecture, let's begin rotating the player. In this lecture, we're going to rotate the player with a technique called linear interpolation. Sounds like a complicated concept. Let me break down the mysteries behind this feature. First things first, we should understand the idea of interpolation. Interpolation describes the process of calculating a value between two other values. For example, let's say we need to grab a value between 0 and 100. We may want to grab a value that's 40% of the way to 100. If we were to do the calculation, the result would be 40. Calculating the value is known as interpolation. Unity provides a formula for performing this calculation called linear interpolation. There are different formulas for performing interpolation. However, those have different use cases. For our game, linear interpolation is more than suitable. Inside Visual Studio Code, open the movement file. Let's focus our attention on the rotate method. At the bottom of the method, update the transform.rotation property to Quaternion.lerp method. Previously, we were reading from this property. It's also acceptable to update the value. This is how we can perform rotation on a game object. By directly modifying the rotation value, the game object will reflect these changes. As for the lerp method, it's short for linear interpolation. There are 3 values required by this method. First, we must pass in the starting and end values. In our case, these values would be the start rotation and end rotation variables, respectively. The last parameter is a value between 0 and 1. 0 represents the starting value. 1 represents the end value. If we pass in a number between 0 and 1, Unity will figure out the respective value between the first 2 parameters. The question is, why are we using linear interpolation? Keep in mind, we're trying to smoothly rotate the game object. This situation requires us to smoothly calculate the rotation values on each frame. We can't jump immediately to the end position. Linear interpolation will help us perform that calculation. Rotating a player should be based on time. Otherwise, we'll face an issue with frame rate dependence. Let's pass in the time.deltaTime variable. Luckily, this variable contains a value between 0 and 1. It'll be suitable as a value for helping us calculate the new rotation. Before testing our code, we should multiply this value by the agent.angularSpeed variable. If you can recall, the angular speed setting can be found on the agent component. This setting determines the speed of an agent's rotation. It won't be applied to our calculation. We should include it to allow designers to configure the rotation speed. After making those changes, let's try testing our code. Head back to Unity. Next, play the game. As you can see, the blue box is moving around. This game object was added to help us identify the forward position of the player. It should be facing the direction you're moving in. At the same time, it should not be moving when we're not moving. Perfect. We've successfully rotated the player by updating the transform component's rotation values. Linear interpolation has helped us by creating a smooth rotation. We're finished. The goal of this section was to move the player. If you made it this far, pat yourself on the back. In the next set of lectures, let's wrap up this section with some final thoughts. In this lecture, I'm going to provide some final thoughts on the code we've written. I haven't had an opportunity to discuss the structure of our code. Some decisions were left unexplained. Let's quickly go through my preferences for writing code. Firstly, let's discuss the organization of variables and methods. At the top of the class, we've defined a set of variables to help us move the player. It's common practice to define variables in this location. Technically, you can define variables between methods. Most developers prefer to define them at the top of the file. Otherwise, it'll be challenging to search for specific pieces of code. In addition, I'm adding a space between the agent and movement vector variables. This space is not required. It's very common to define variables for components. I prefer to add a space between variables for components and variables for other types of values. Once again, this step is not required but recommended. Let's move on to the methods. The awake and update methods are the first methods in our class. The order of methods does not impact our code. I prefer to write Unity methods at the top of the file based on their execution order. Since the awake method gets called first, it's defined before the update method. Custom methods are defined after Unity methods. Their order does not matter. I prefer to structure my code this way for readability and clarity. Now that we've reviewed the structure, there's one more topic I want to touch on called caching. It's not uncommon to interact with external components. Before we can use a component's properties and methods, we must grab it with the getComponent method. It's recommended to cache a component's reference. Component caching is the process of storing a component's information in a variable available to the entire class. By doing so, we can run the getComponent method once per component. The question is, why? In the resource section of this lecture, I provide a link to a page with information on the getComponent method. This method makes it simple to grab a component, but not all methods are created equal. Some methods require more resources than others. The getComponent method is an example of a method that can hurt performance. It takes a while for Unity to find this component. If we constantly call this method on every frame, our game may start performing slowly. According to this page, it's recommended to cache a component from the awake or start methods. That's exactly what we're doing in our script. Throughout the course, We'll be following this practice to optimize the performance of our game. If you can, you should avoid calling the getComponent method from within the update method. If you're interested in additional tips, the sidebar contains links for other helpful information. In the next lecture, let's cover one more topic before getting back into programming. In this lecture, I want to explore the Unity documentation with you. Throughout this section, I've provided links to various areas of the documentation for more info on a class or method. One of the best skills you can pick up is learning to read the documentation. Unity is one of the biggest game engines available. It's not possible to cover every corner from a course. For this reason, you may need to look up information on your own. In the resource section of this lecture, I provide a link to the homepage of the documentation site. Unity's documentation is split into two sections. We can view the manual or scripting API. The manual contains dozens of tutorials for performing basic tasks in the Unity editor. They're really helpful for beginners to explore the various features offered by Unity. As for the scripting API, it contains a complete list of namespaces and classes of Unity. If we navigate to this part of the documentation, we are given a complete list of namespaces. There are 4 namespaces called Unity Engine, Unity Editor, Unity, and Other. The Unity Engine namespace is the most common namespace used by developers. If we look under this namespace, we are given additional namespaces. You may be wondering, how do I know these are namespaces? All namespaces have a section called Classes under them. For example, if we look under the Unity Engine.ai namespace, we'll find a list of classes. These are the classes registered under this namespace. You'll find a similar pattern for the other namespaces. Hopefully, this information helps you find specific information on a class. There's one more thing I want to mention. Some packages have dedicated documentation pages. For example, let's head back to the manual section. There's a section called Packages and Feature Sets. Within this section, there's another section called Released Packages. This page lists an official list of released packages in Unity. The links will take you to a separate documentation page for that specific page. For example, let's open the documentation site for the Input System package. As you can see, the documentation site has a different design than the regular documentation site. However, the documentation pages for packages are structured the same. Once again, we have sections for the manual and scripting API. The manual contains tutorials for a specific package, whereas the scripting API section has information on the namespaces and classes for a given package. With this information, it should be easier to search for information. Let's begin working on creating enemies for our game.
Congrats, you've completed this crash course. Make sure to soak it in, you've earned it. But don't stop your learning here. Take the rest of Luis's complete Zero to Mastery Unity Bootcamp, where you'll dive into advanced C# concepts, animations, combat systems, scene management, all while continuing to build your own RPG game and publishing it like a pro. Also, by enrolling in the complete Unity Bootcamp, you get access to our private community on Discord, where you can get direct help from Luis and other ZTM instructors. Watch the video on your screen to get a glimpse of our vibrant community that just passed 500,000 members. One more thing, if you enjoyed this crash course, help me show Luis some love by dropping it a like and leaving a comment, something like Luis rocks. Alright, that's it from me. I look forward to seeing you inside the Zero to Mastery Academy.